Welcome everybody. We are now live on YouTube. Let me see. Matt, are you in here?
Yeah, I'm here.
Maybe you can introduce our presenters for today, and then we can kick off the conference.
Sure. So this today in room 2, pretty much all day, other than a lunch break, going all the way through 5:30 Eastern time, is going to be the Nars tutorial and workshop and the panel session at the end with a number of intriguing speakers. I'm familiar with Nars. I worked with Pei way back in 2000. And Ben and I were all in the same office in New York City. I've met Patrick, who's now on the screen, and I've never met Peter other than via email communication. Both now at Temple University under Pei, and been working on Open Nars for quite some time. It's a distinct pleasure. So correct me if I'm wrong. I believe Peter and Patrick are going to be kind of tag teaming this morning on a tutorial and demonstration of the Open Nars system. So who's starting? Because that keeps changing a little bit. So
I think Peter will start, assuming he's already here. Let's see.
I see him up in the corner there. So
can you hear us, Peter? I think your microphone is muted.
Right. Yeah, I will start. I will lead the session for the morning. Hi guys, hi everyone, and thanks for joining.
Hi, Peter.
Hey, Chris.
Hey, Chris.
Hey, Patrick.
Hey,
Hey, Matt.
Is Pei here?
I think I have seen him, but
Yes. Yeah.
So you will start, right?
Mm-hmm.
I think you need to activate your screen sharing.
So I'm going to share the screen. Right. So I will start with an introduction, the general introduction of theory behind the Nars. And then later, I will just cover the overview of the Open Nars implementation that we will cover the control and how the theory is being implemented in that particular implementation. Then later, Patrick will basically show his implementation of Open Nars. And after that, it will be a demonstration. And this is until the lunch break. Okay, so let's start. Whenever anyone wants to just design an artificial intelligence system, he will just need to think what is intelligence and need to define the intelligence for himself. And so the same happened with Pei, with us, with Open Nars team. So what's intelligence and what's not an intelligence? So I will start with saying that what is not an intelligence in our opinion, and it becomes that innate behavior or instincts are not an intelligence. So that's something not is learned, that's a given to you for granted. So if a computer system, for example, in exhaustive search, so whenever you try to choose and see every single element, every single item to see if it's the item you need or not, if you in a search, for example, So it's also not an intelligence. You're just doing it one by one, choosing the item. So for example, basic information retrieval is also not an intelligence. It's just similarly to exhaustive search, you try to find the information which is needs for which suits your needs. Now, any repeated routines like computer functions are also not intelligence. And of course, algorithms, they may be very complex algorithms, numerical calculation, sorting, fixed mapping, anything, but they're pre-programmed, they're very efficient, but it's not an intelligence. They just only say how intelligent the programmer or designer is, but the algorithm itself is not an intelligence. So then people try to interpret the intelligence. And what's intelligence according to the most of the systems, most of the people, like in mainstream AI. So basically, mainstream AI treats intelligence as a collection of problem-specific and domain-specific parts. Intelligence becomes applied to the specific domain and to specific problems, like, for example, computer vision or deep learning stuff. It can recognize the static images, sometimes video, whatever, but it only applies to that domain. If you want to apply it to some other domain, at least it has to be retrained. Now, in AGI, the intelligence is basically the general purpose capability that should be treated as a whole. That's what most AGI researchers has agreed to use the intelligence in that AGI context. However, the AGI researchers still include different research objectives and strategies. In our assumptions as OpenNARS team, the intelligence is just the capability of the system to adapt to its environment and to work with insufficient knowledge and resources. So intelligence is nothing inborn, nothing given for granted. It's something basically learned and something that allows a system to adapt to environments to apply to different domain. That's what intelligence in terms of our perspective. And of course, it has to conform with insufficient knowledge and resources assumption. And what is that? It means that basically resources are always finite. We always have finite processing power, processing power and memory. We only have the finite resources. They always work in the real time, and the always system has to be open for anything that to come to it. So system has to be responsive, has to be open to any single task which nor the system knows about it in the future. And after defining that what we really want to achieve, so there is some framework. We come up with the framework. So in the very high level, how the system has to look. So the system has to have some language for representation, for knowledge representation, for example, for environment representation. It has to be some semantics of the language or meaning. So whenever you try to deal with different inferences or different premises or different statements in the language, there has to be some rules for inference rules. And of course, it has to be some memory, such that background has to be recorded and the system has to have any experience. And as a final step, it has to be the control mechanism. Control is something that allows everything to happen, everything to run in the real time under assumption of sufficient knowledge and resources. That's a very difficult task to achieve. However, the advantages are, so there is independence of the domain. So the system can be adaptable to multiple domains, and it has the rich expressing power. So all the rules can be justified, and so the traceability, whenever the inference is made or decision is made by the system, it's traced. And of course, there is a flexibility of the combining the rules. But the control is a very hard thing to achieve. There are issues, however. So theory is good, but the fundamental issues are such that having that insufficient knowledge and resources, we understand the resources are always finite and they cannot achieve the 100% correctness of the derivations. That means that that everything is just true to the point, and that means that basically we have to define what is the validity and rationality, and it becomes really the relation becomes relative to the available knowledge and resources and system background at certain time. So what we want to achieve actually is just to be general, to be really adaptive, flexible, robust, and scalable. Those are really the desired features which we want to achieve in the control of any AGI system. So what is Nars, non-axiomatic reasoning system? It's basically the system consists of two main parts. It's a logic part and the control part. And the logic part is the term logic. Nars is fully based and fully conforms to the assumption of insufficient knowledge and resources. And it has the design meta level, as in null, for example, languages, and it has the object level, which is all the concepts and basically implemented within the control. Now we can start a little bit more detail, but that's meaning that it's a term logic basically. The Nars, it's different from the predicate logic because it uses the categorical statements on sentences, like here, for example, inheritance sentences, and it uses the syllogical inference rules to make an inferences. So the main things in Nars are the terms and the statements in the logic, I mean. So the term is a word, and basically it can be seen as a name of a concept. And the statement is basically the relation between the terms. In this case, in general case, it's a subject copula predicate. So on the left, you see here S and the error to P, and basically error similar to implication, but it's not in this case. It's called inheritance here. This is a relation copula. S stands for subject and P for predicate. In English, it easily can be, for example, seen as the S is P or S is kind of P, which will be introduced later. And the example here is water is liquid. So we can say here that S inherits P. And those types of terms later we will call the Narcisse statements in Nars, which is basically the language which will be operated on the Nars implementation. As a one second, as a very beginning statements, basically they don't have any truth value in this case. And this is the very foundation for all of the logical layers to be used in the future. We can say it as the logical layer 0. So for that, we have to define the experience of the system. So let experience K be a finite set of the statements within the system's memory. And let we have all the beliefs like that K star, which is a transitive closure, which means using the deductive rules, we can achieve all of that, deduce all of that other statements from that experience. And then we can say that the statements similar to S inherits P or water is liquid is true if it is either in the K closure in the master set of all of the statements within the system, or basically the term inherits itself, which makes the relationship reflective. Yes, by the way, inheritance is reflective and transitive. If neither of these conditions is met, so basically the statement becomes false. And this is for the very basic 0 level logic inference. It's also important now to mention that having inheritance relation, the term is important to the system knowledge, but it's much more important its relationship among other terms. And so the relationship among other terms are participate in extension and intension. So there is kind of definition here. So the extension of a term is something, first of all, it has to be within the system knowledge vocabulary, and it has to be before the term. So it has to inherit the term, like on the left here, like for example, S inherits P, and S is an extension of P. The very similar definition of intension, but vice versa. So intention has to be on the right of the term. So if S inherits P, P is said to be an intention of S. And if we imagine all of the concept, whoever has, for example, just introduced inheritance relationship, organize some of the sets of the extensions and intentions, and that's actually the meaning for the system, for the Nars system. That's a kind of evidence the system has acquired. And of course, this theorem is very trivial to prove. Basically, it means that if S inherits P, if and only if the extension of S is a subset of extension of P, if and only if as an intention of P is a subset of intention of S. In the question, we can deliberate it after. So now we come to the evidence. So extension and intention really means the evidence for the system. And now we can kind of see and measure the evidence. There are positive evidence, negative evidence, and total evidence. The positive evidence means basically that if there is extension of S and extension of P, and combined with intention of P and intention of S, that's the positive evidence. So over here, these are the green squares. And as you can see, so this green square can be any term, for example. So it inherits S and it inherits P. And it also, intention of S is that upper top green square. So S inherits that green square and P inherits that green square. So those green is basically the positive evidence for the given statement. S inherits P is a statement. Now, the negative evidence in something which is extension of S not including extension of P, and intention of P not including intention of S. So in this case, we can see just a trivial example. The red squares, like the P, the intention of P is that red square, but it's not in intention of S. As the same as the red square is actually extension of S, but it is not an extension of P. So it cannot be contributed as a positive evidence. And now we have defined the positive and negative evidence. And now we can combine them to have a total evidence. Basically, green squares plus the red squares. That negative plus positive evidence becomes a total evidence. So now we have come up already with a metric just to somehow to measure the experience of the system, to measure the evidence of the statement. And that comes us to the meaning of the sentences or the statements. So in Nars, there is a truth value. But in general case, what is the truth value? Traditionally, the truth value is basically is an agreement with reality. Basically, how close it is to the object in the fact. So we have the description of the world, and we have the truth value or the truth of that statement, and how close objectively it's to the description in the world, to the object in the world. In ours, the truth value of the statement just measures the evidential support. So it indicates how close it is to the evidence. And that's a difference, it's already related to the evidence. Now we come to the how in Nars the truth value is defined. The truth value of the statement is basically a pair of real numbers. The range is 0 to 1, and it measures the evidential support of the statement. So the pair is the frequency and confidence. Every statement is being assigned a truth value. Either is an input or derivation, the mechanism of assigning the truth value for every statement, except for the Golok questions. And frequency is nothing but the positive evidence divided by total evidence. Basically, if we go back, so we have just the green squares over here divided by the all of the squares over here. In this case, probably 2 by 4. And the confidence is nothing but the total evidence divided by the total evidence plus some other constant. For the constant, we have chosen the 1. It's just 1 for the constant. I assume there was a multiple tests for that, and one is probably the best describing constant here. So the frequency is frequency. Just say about that about the truth of the statement, but the confidence really says about the how the matter of belief and the truth value. So how confident the system is in a certain statement, and sometimes the confidence is more important, actually, in more times than the frequency, because this kind of information collection or evidence or knowledge of the system, it can be look like that too. Now, every derivation produce some stream of statements, and those statements are being assigned the truth value with frequency and confidence, also always within the range of 0 to 1. Whenever there are inferences, so there are special inferences rule defined in Nars, and each inference rule has an accompanied truth value function. So inference rule produce the derivation, but the truth value of the derivation is being computed, evaluated by the truth value function. And now we come here to the design, how it will work a little bit. So all of the rational numbers in the system, we try to basically interpret as the Boolean. And for that, we need to extend the Boolean operations, not, and, or, such that they can be mapped and applied in the rational domain. Whenever we have treat them as Boolean, we're just using the truth value functions, and truth value functions under the cover using basically those extended Boolean operations in different configurations to assign a truth value of the derivation. And extended Boolean operations are defined over here. It's basically not, and is a multiplications, or is like that. And combining those would create us the evaluation of the truth values for the derivations. So the very basic three inference functions are deduction, abduction, and induction. And what it does is basically given two premises, as here, M inherence P and S inherence M, we can produce a derivation S inherence P. Here in the left bottom corner, there is basically the truth functions. Frequency of one premise multiplied by frequency of the other premise, and confidence equal confidence multiplied by confidence multiplied by frequency of the one, frequency of the second. This is nothing but the end function, extended Boolean end functions defined over here on the previous slides. And this is basically the truth function for the deduction. There's an example over here. So if bird inherits animal and Robin inherits bird, saying basically Robin is bird and bird is an animal, and those on the right, this is the frequency and confidence value, 1 and 0.9. Those are default. When you enter the system, there is a default, by the way, system assigns itself default frequency and confidence. The system derives that, okay, if Robin is bird and bird is an animal, then Robin becomes an animal too. And that's a derivation statement, Robin is animal. And it assigns frequency, which is 1, and confidence, which is 0.81, using those truth functions on the left corner to get those numbers. This is actually the schema like S inherence M, M inherence P, and just derives it as inherence P. That's for the deduction. For the induction, these are syllogical rules, by the way. For the induction, very similar. So we have M inherence P and M inherence S with some frequency and confidence. Then the system can derive that S inherence P. And those on the right top, those are the truth functions for the induction, how that frequency and confidence are being computed. So the example is here that Swan is a bird, Swan inherits bird, and on the right there is frequency and confidence, which are default values. And also there is another input, Swan is a swimmer, then system basically derives that bird is a swimmer, bird inherent swimmer, with that frequency 1 and confidence 0.445 by using those truth functions. Now the last, important, like basic sociological rule is abduction. It's similar to the inverse induction. It basically, if P inherits M and S inherits M, look like the triangle here goes up and here is going down for the induction. Then basically system can derive S inherits P and assign its frequency and confidence by the truth functions in the top right corner. And again, there's seabird is a swimmer and gull is a swimmer. The gull becomes a seabird with a frequency of 1 and confidence of 0.45. Very similar, but inversed. Deduction, induction, abduction is the example of the forward inference. So we always need the belief tasks or two premises to create the forward inferences. But what if we have premises which have the similar meaning, but not overlapping evidence, come from different background, for example? So we have a revision. There are two premises which are same, but they don't come from same sources of evidences. So in this case, we need to revise them. And to revise them, there is a revision rule and a revision function for the truth value in Nars. So if we have, as here we see, S inherent P, it's one statement from one source of evidence. S inherent P is another statement from another source of evidence. And we have to combine them. And combination is basically made by those frequency and confidence formulas over here. That's how the revision works. The example is here, bird is a swimmer, bird is a swimmer. It becomes the same, bird is a swimmer, but as you can see, here is a positive, here is a negative, basically 0 frequency and 1 frequency of 1, and becomes basically the frequency changes considerably and confidence too. In revision, confidence always higher than in the premises. Revision is part of local inferences. There is also the choice rule. The choice rule, for example, revision works when the sources are different evidences. So there is no overlapping evidence. However, what to do where there are overlapping evidence? That means that two same statements come from the similar evidences. So in this case, we have to choose. And the choice rule, we will explain later, basically using using truth expectation functions is we pick to choose the correct statements for the system and store it in memory for the future. And the revision and choice are basically the types of the local inferences. It's been explained here. Now the forward inferences are, as I explained, two beliefs or two premises believe in a task. Basically, there is inference between them produced by the functions of sociological rules, deduction, induction, abduction, and those being extended for the future nulls. And there is also the backward inference. Backward inference is actually to, first of all, the choice rule is the just one case, special case of the backward inferences. And also the finding the goals, achieving the goals, or finding the answer to the questions is another type of backward inference, such that we can have to find the question, find the answer to the question, which is the question itself, but that the question itself, if we answer that, we can answer that master question. And this becomes, using the forward inference rule, we can now apply forward inference rule to achieve the backward inference. We can cover that like in the later session today, forward, local, and backward inferences. Now, as we defined in the framework for the AGI system, we need some memory structure to hold or to keep all the necessary informations. Whenever anything enters to the system, it becomes a task. So it can be question, a goal, or it can be just piece of new knowledge, which is considered to be a judgment. Beliefs is basically the accepted knowledge. So knowledge enters the system, the being processed, and then converted to the belief. Tasks and beliefs are basically clustered into the concept, each named by the term. So concept is named by a term and has the links to the tasks and the belief tables inside of them. And the concepts are basically prioritized in the memory. So there is a main memory. It's organized like a priority queue, and concepts are being, there is actually the priority value assigned for each concept. Priority value indicates how important this concept to be chosen. And the takeout operation from the memory is taken as the priority, probabilistic priority, priority which is probability to the distribution of the priority of the memory. Basically, what that means that the higher the priority, it has the higher chance to be taken out. However, the low priority items also can participate in resource allocation and can be taken out also. So that data structure is used throughout the systems. Main memory uses that data structure. Basically, we call it bag. It holds the concepts. Inside the concepts, there are also the same data structures called the bag. And the tasks is actually, there is a task bag inside the concepts. And the belief are basically just an array, just a list of the beliefs which are sorted by the higher confidence value from the truth value. So that's how the memory looks. Over here, we can see those like memory can be seen as the graph, where the links are basically the relationship between the concepts. Those concepts like ghoul, swimmer, robin, those are named by the term, and those and those errors means the relationships on them. They can be viewed as the weighted graph using the truth value, but in reality, it's much more complex. There are also links there. But as an easy representation of the memory, it can be just looked at as the concept as a nodes and edges as the relationship between them. In this case, we're only covering the inheritance relationship, which is the very basic level of null. What is important is that the concept is actually the fluid. The meaning is determined neither by reference nor by definition, but by experience relations. So meaning of a concept can change because the truth value can change. Also, the budget of the concept, which is the priority, can change. And that becomes that each relation is mattered to a degree. Also, the meaning of the concept can be changed in the future derivation by the history and the context of the system memory. So it also flows the meaning. It's nothing concrete there. It's always changing in the real time with the system cycles participating in the derivations. This is the very brief and very high level overview of architecture, the routine architecture actually. The user over here can input any task, or it can come from other software, it can come from other protocol. Then task is being entered to the buffer. In buffer, it's being selected by priority and moved to the memory. In memory, the local inference can happen such that it may produce more concepts, and truth value can change in memory. Then from the memory, actually, it's being taken out by priority to the inference engine. Inference engine just makes an inference on the two premises, basically the belief and the task, and produce some derivation. And that derivation task or derived task can be either going to the output or again going to the buffer and repeating the cycle, participate in the cycle. This basically, that's a very high level overview of the system cycles. And system cycles going on forever, like wild true loop, until someone stops it. Producing unlimited derivation, going over in the buffer, in the memory, and vice versa. So as we can see, whenever we enter a task, we're going into the memory, it always interacts with the belief whatever system has. And it does it by applying some rules, inference rules, deduction, abductions, truth functions, and some other budget functions. All the beliefs and all of the tasks are being selected from here, from the buffers, probabilistically based on priority, as I explained. So the higher the priority, the bigger the chance to be selected. However, the lower the priority, it also has some chance to be selected. And the priority is nothing but, actually, priority is, priority is something which is the short term and long term. For the priority stands for the short term, and the quality for the long term importance. And the quality is basically how useful the item becomes in the history, and it's relevant in the current context. So priority of the item over here is not just a single rational number, it's actually the composition of rational numbers. Some of them means a different thing. One means that the short-term importance, how important it's as of right now, and the other one is the long-term importance, how important the item is in the long run, which means that if the long-term importance of the item is really high, that the item is not being forgotten, removed from the memory. And that long-term importance is called the quality. As we described now, we only covered idealized logic level 1 over here, or its implementation null 1. There are 9 levels of logic, each of them added upon the next one. Because basically the system was designed, started from the design null 1, then added null 2, null 3, null 4, and etc. Each of them has the basis of the null 1, but in addition, it adds the truth functions, it adds the inference rules, it adds it's a different functionality for the systems. For example, in null 2, there are introduced the set elements such as instant properties and similarity copulas. In null 3, there are set operations. In null 4, there is regular relation. In null 5, there is, for example, there is already statements as considered to be as a term itself. In null 6, there is a variable. Null 7 is for the temporal inference, such that the statements can be considered as an event. Null 8 becomes that procedural learning, and null 9 is not yet fully implemented, but we're working on it. It's basically self-control. That's what it says over here. So basically, the higher we go, the more advanced the logic becomes, but it still has the basic similarity with the easy ones. So inheritance copula, the variance of inheritance copula is similarity, instance, and property. This is for the null 2. For the null 3, then we introduce compound terms and term complexity, which basically relates to the sets, intersections, difference, products, and images. This is now null 3 and null 4. There are new inference rules added, like comparison, analogy, and some structural and compositional rules, which allows the terms to be restructured or compose the higher complexity terms. Now, as a higher order reasoning, we're starting with null 5. The introduction of the statement as a term. New copulas also introduced, like implication and equivalence. Negation is introduced, conjunction and disjunction introduced. By the way, conjunction and disjunction is introduced in the way similar to the intentional and extensional intersections. Conditional inference as implication. And what else? It's in null 6, we have implemented the variables as a terms, as a symbols. So null 6 is for the variables. Later on, basically, null 7, we introduce the time to the system. So each of the truth value has been assigned a timestamp, and the statement becomes an event. Event and a statement with temporal relations. Either is sequential or parallel. That's a higher level null 7. Then null 8 is the operation as executable events with sensory motor interface. So also the goal and planning introduced in null 8. And the mental operation are introduced in null 9. We have the list of hard-coded operators for the null 8 for the procedural learning. And also in the null 9 is basically the self-control, which is still under work. Now, as we see, the Nars is fully based on assumption of insufficient knowledge and resources. It basically has a unified representational language. It has a complete inferral power. It has reasoning as learning, planning, problem solving, and decision making. It can be integrated with other software, and it has the plugin interface to be available as plug and play for the other software. There are the main implementations of OpenNars. It's mostly implemented the OpenNars for the research is a Java version. So this is the main implementation, which we all work on. There are also their implementation, Patrick done another implementation, OpenNars for application. He will demonstrate it later today. And there are multiple working examples exist as proof of concept for OpenNars. As we can see, the system really shows many people-like, human-like properties, but it's not deemed to be psychological model. So no one really tried to achieve the same level of psychological thinking or cognitive science as a human process. And all of that what discussed really brings Nars to the potential applications. Nars is not defined for anything specific. There's no the specific applications. There is none. It just can be considered as a general purpose tool. It can be suitable for multiple domains where assumption of insufficient knowledge is applicable, where tasks can be expressible as reasoning, and where some other software can have compatible interfaces and require some insufficient assumption of knowledge and resources or tasks which can be expressed or reasoning. So Nars is very kind of adaptive to the environment, can be used in many things, but not for any specific domain. And this is, we go to the end. All the publications and reports can be found over here. Source code is opennars.org. Also on the GitHub, there is a wiki pages that comes in more detail of how things work and describe the functionality of Nars. Any questions? Until we can go, or we can go after having like control overview. Any thought? Okay. So this was the general overview of Nars theory and how it works. Now we can go to the implementation, which is the OpenNars implementation for research. Yes?
In the chat, there is a question.
In the chat, there is a question.
How does the system learn the bottom level concept?
What do you mean by bottom level concept? So basically,
hello, sorry, I mean the bottom level concepts like swan and bird, like which are on the bottom atomic concepts. Are they
those are being entered at the very beginning. The Nars has no information about anything, so it's the knowledge is completely empty. So someone enters the statement like bird, like Robin is a bird, right? And that statement is processing. It's a statement being converted to the task, and task is being processed. So far there is nothing in the system, and the first concept to appear there will be the Robin, the bird, and the Robin is bird as a task. That's how the first input is being entered to the system. Where is that? 1 second. Over here. So basically, this is the input statement, right? Goes to the buffer, and then they're going to be processed and decompositioned in the concepts, then put on into the memory. This is the bottom concepts, as you mean, right? Now the second statement enters, for example, bird is an animal, right? So it enters the buffer, again, decomposes to the concepts and put to the memory. So there are revision mates, local inference mates over here. It may be more concepts created because of the local inference, but now it's become 3 concepts. The bird is already there, so we have to revise that. In another concept, animal, right? So now it becomes a 3 concept over here at least. And it's being then choosing from the memory into the inference engine, right? And into inference engine will do some inference on that using the rules like abduction, deduction, induction with the truth value functions. And then we'll create some derivation like Robin is an animal, right? And Robin is an animal becomes a task again. So task again will be put into the task buffer over here. Then it will be either output or also, or actually not or, and will be decomposed again into the concepts and put into the memory. Does it answer your question?
Yeah, thank you very much. This was a helpful explanation how it works again. Thanks.
Yeah, I have a follow-up question. So when you calculate, well, I'm not sure if it's called the weight or I guess the frequency.
1 second.
When you calculate the frequency, do you use only bottom concepts, or do you mix? I mean, when you're talking about the extensional part, so we have W plus. When you calculate W plus, so here it's going to be this relationship. Well,
I think I understand the question.
Okay.
So whenever you, okay, so that's a frequency. That's this is more of the theoretical explanation on frequency and confidence. So how from theory we go to the implementation, right? So in theory, basically what we mean on the paper on the board, it's that we have to find the positive evidence, and then we have to compute the total evidence, right? And then to divide the ratio by the positive by the total evidence, right? And the confidence is similar. So we have to find the total evidence and divide it by 1, as you can see. So basically, if the total evidence is really high, so that number becomes close approaching 1, right? If W is really high. But if W is really low, so that confidence is approaching 0. How it is done? Go for this diagram. So as you can see over here, I input the statement into the buffer, right? And by default, I have applied frequency of 1, but it's just a default parameter, and confidence 1. With those truth value 1 and I'm sorry, confidence 0.9. Without default truth value, it goes to the concept to the concept memory. Now the next statement also goes with whenever it's an input, for example, that has a default truth value 1 and 0.0, also going to the concept memory. When there is an inference, they already applied the truth rule, the truth function to evaluate the confidence and the frequency, and that truth function is basically nothing but extended Boolean operation. So we treat it, so frequency was 1 and 1, we just multiply them, and for the derivation, we have the 1, for example.
Okay, well, how am I going to explain that? Well, in probability theory, when you want to calculate the probability of an event, I mean, of a concept, which is a set over the sample space,
Okay.
you're going to consider a partition, which is going to be the lowest level partition you can get, and you're going to have a mass function over this partition. Well, you can consider the how to say the members themselves, but if you don't know the sample space very well, you don't have to do that. You just consider a partition. and by doing that, you ensure that you're not gonna count multiple times duplicates. Basically, if you have a partition, is going to prevent from having basically two elementary concepts that would overlap.
Mm-hmm.
And so I have a hard time seeing how that is done in Nars, basically.
In Nars is a little bit differently. So everything is grouped within the concept itself. So the concept is named by the name. The concept has to be unique there. And whenever you choose the concept, right, from that, where is that diagram? So here in the memory, over there, whenever you choose the concept, basically concept inside of it has the pointers. So one pointers point to the task, whichever concept is associated to, and that association was built whenever the task was first input to the system. It may be just input or a derivation. So over here, for example, after the inference engine, the task is created, then it's being decomposed by the concepts, and those relationships are being established. So every concept has a pointers to the task it's associated to. Also, it has the pointer to a term which is associated to. So for example, Robin is a bird. Robin inherits bird. This is a task, and also there is a concept Robin, concept bird, and also there is a concept Robin is a bird, right? And all of them has the pointers to the task Robin is bird. Also, they have pointers to the terms. So Robin is bird concept has pointers to Robin and bird, right? So each of the concept also have the set of beliefs inside of them. So Robin is bird concept has a belief, Robert is bird, pointing to the task. And whenever you select, for example, concept Robin is bird, you select that. You select the task link, and then you select the belief from it. Then you select the term link, and then you select the belief from that point to that term. So there is guaranteed, there is no duplication of, as you said, of that similar concept is happening. Does that answer?
Well, I guess, well, yeah, partially, I guess. Okay, I think as things get more concrete, I might get the full picture, and but yeah, thank you.
Because
for now.
yeah, because it's a beauty of it, actually managing the resources, that formation of the concept, it's happened to be in the very first stage of task processing.
Sorry for interruption, Peter. I think I understand Neil's question. Just answer it in one sentence. The calculation of truth value in Nars is not based on probability theory. And this is something I have debated with Ben for 20 years. We can talk about it later, but we don't have the time to fully explain. I fully understand where your question comes from.
Well,
yeah.
well, that's true, but we have to select the concept probabilistically to the priority.
That's a different story. He is talking about why the truth value is not calculated according to probability theory. Yeah.
Can I answer the next question?
Please.
There's a question: can Nars represent non-symbolic / magnitude values as terms, or does it handle such things differently? It's actually a bit related to the previous question: how does the system learn the bottom level concept? Essentially, what we have is so at the bottom level, so to speak. For instance, there are sensors attached to the system, and those sensors are then going into some kind of encoder, which then uses essentially sensor terms, just terms the sensor can output. It can be something like temperature, low, high, or middle. So it can represent different temperature values with different terms, but only in a discrete way. So you can say that you can have multiple values for a given range of, for a given interval of values. That's possible. And of course, often you could have multiple sensors attached, and the system can then combine those terms to more complex patterns. And this is really where the bottom level concepts come from. It's for instance, in a robotic scenario, you have some sensors, and those give you different terms, and the system can then see certain patterns of terms which appear at the same time, so it can correlate them, and so it can form higher compositions of those terms to represent a pattern, let's say Raven. But it could also be that, for instance, you have already a pre-trained artificial neural network, which already detects something like a cat. So you could have some output label cat, which directly enters Nars as a term. How deep you want to go really depends on the particular architecture, and it's not easy to say, but it seems that in human perception, our representations are to some degree introspective, so we can even reason about edges and things. We don't just see there's a cat, but we can distinguish our cat from a neighbor's cat. So it's difficult to capture this in if you just do end-to-end training from images to labels. So actually, so it's difficult topic. How much granularity do you want to allow for the bottom level concepts? Do you want to use an autoencoder and convert the latent space activations to Narcisse, or do you want to have a direct end-to-end training and only enter terms like cat or car or something like that? Or do you go completely to the sensory levels and say each sensor on the retina has a range of values, and each sensor will emit an event for now to be consumed, which is so. Of course, what we currently don't allow is to say we directly enter a value. But if we talk about computer systems, even a 32-bit number is not really a number, but it's a list of 32 bits. And so it's always a question of granularity. How far do you want to go? Even in Nars, you could have something like a bit vector, but of course it's more difficult for the system to work with such a representation than with a higher level representation. But sometimes you need more granularity, and this is really a difficult topic. And we are currently trying to design sensory channels which allow to work with vision, and we are also open to combine or to use existing machine learning technology, which has proven to be very successful in certain aspects. So we are very open of how to encode information and to our system, essentially. You're welcome. Are there any other questions, or should we continue with the next presentation?
Okay. Shall we continue?
Okay.
So basically, one second. Over here, we have the overview of the OpenRs implementation for research. implemented in Java. Source code can be found on GitHub, on openars.org. Wiki pages are also available on the GitHub. So whenever creating the OpenRs, it has the logic and control parts, and the control is really, really difficult. That's why the development of AGI system is still very difficult task to do. So these are some of the control criteria for the OpenRs for research. It's as we said, it has to operate under assumption of sufficient knowledge and resources. And Nars always expect new tasks to arrive at any given moment in time. That means that system always has to be responsive for new inputs and new derivations. It also means that the space of data structures are always bounded in size, always full. And some eviction policies has to be in place. Also, the control has to work in real time. That means that the operating cycle has to finish in a constant time, roughly in constant time. That means that all of the items has to be important to the derivation context. All of the items has to be important to the knowledge of the system, and some short and long-term importance has to be introduced for the items, such that we can select an item as we need it right now, and we can keep the item for the history as we will need to select it like in a while. But it should not be. It should be there. It should not disappear. However, if the data structures become full, there is no place to put the item, so it has to be implemented some mechanism to forget the items, but the item has to be forgotten such that we make sure that the item is no longer needed. So that all lead to the creation that's of the high-level overview of the control mechanism. So it has multiple buffers as of right now. We're currently working on the implementation of the global buffer design, but as of right now, the code is implemented in this way. So we have the input buffer, derivation buffer, main memory on the right here, all of the functions, truth, Boolean, budgets, functions, rules, local logical rules, inference rules, local inference, compositional structural, and of course the inference engine. So this is the more detailed diagram that was on the previous presentation. We have the event back for the for the events. And this, now we will talk how it all works. So the memory on the right here of the concepts, as we see, is basically as a memory of concepts. It stores the concepts, and the stores in the data structure we call bag. It is priority queue, and it has operation defined as put, get, and get by the key. Now the get operation gets the item probabilistically by priority, proportional to the priority. So the bigger the priority of the item, the bigger chance for the item to be selected. And however, the low priority items also can be selected. So they also can participate for the resource management, for the resource allocation. The bag is limited in the size. And whenever the bag becomes full, the data structure becomes full, the lowest priority item is being removed from the bag. And that happens quite often because the Nars derives multiple hundreds or even more derivations during the cycles, and the bag actually becomes full and elements have to be removed. There's no space to store them. The bag actually is just a data structure we choose throughout the system. So it's in the memory, it's main memory, I mean, it is the concept inside, is in the buffer too. So basically the most important data structure used in OpenRs for research. We didn't speak about budget values, so all we mentioned is the truth value. We know that truth value is frequency and confidence. It's just basically a set of two rational numbers. We chose the positive evidence for the frequency and the reliability for the confidence. But how the item has to be selected from the memory or from the bag is basically the work of the budget value and budget functions. So the budget value is a set of 3 rational numbers. They are also in the range of 0 and 1, and they are assigned to each data items. They're only not assigned to the beliefs, but they assign all the links. So over here, we have the memory of the concepts. And in the previous presentation, we've seen that they connected by the relations, like Robin is a bird, inherits bird, and that's a relation that connects to concepts. But in the real world, I mean, in this implementation, actually we have many links that connects throughout that concepts: term links, task links, belief links. And the priority in the budget value is being assigned to everything but not the beliefs, because beliefs are sorted inside the concepts by the confidence value. So the priority of the budget value of the item basically means that how important the items right now. Whenever I need to select, I'm going to select this proportionally to the priority. If priority is high, I'm going to select it as a very high chance for the item to be selected. Quality, on the other hand, that indicates the long-term importance of the item, and that the bigger the quality is, the ideally it's not being, the item is longer not being forgotten. Now there is a durability also. What's durability? Whenever the item using the priority being picked out from the memory over here, right? It's then the task and beliefs and participate into the inference, so they become 2 premises, and inference happen to be on those two premises. Now they are returned to the memory, back to the memory after everything is done, after decomposition of the derivation task is done, as we described previously. So eventually they return back to the concept memory. However, the item has been already participated in the inference, so the priority has to be decreased, otherwise it will be picked up again. So the durability is basically a hard-coded hyperparameter. It's basically a decay rate, which is multiplied by priority, is also in the range 0 to 1, and it just decreases the priority of an item after each of the inference cycle, such that priority decreases until the priority reaches the minimum, and if the data structure is full, this item is being forgotten, removed from the bag. Now, each concept can be represented as on this picture. So we can see, we can see in the main memory, there are dots, actually the concepts. And each concept is have 2 things. So concept is the way of storage, and constant is also the inference entity. As described before, so concept is taken from the memory, and it has all of the necessary items to accomplish inference within it. So it has the task link back, is basically the data structures similar, the same data structures that used for the concept memory, but it stores the links to the tasks. We will go over it later. There are term links, whereas basically the links to the terms. For example, Raven is bird, that's a concept, and it has a term, which is also a concept, Raven and term bird, and the term links going to point it to the Raven and bird from here. And the task link is going to point to the Raven is bird as a task. And that really makes the efficiency of the choice. We don't have to exhaustively search all of the concept network to find for the elements which has to participate into the memory. We just select the concept, and following the links, we select the premises. Then whenever we do the derivation or inference, we put all of the constants back with adjusted budget value. That's how the derivation works. It also has a table of beliefs and table of goals. So for the beliefs, all of them are basically sorted by the confidence value. So there is no budget. We just take the one from the top, the heap-like structure. And that would bring us to the cycle, how it's going to happen. So Nars always operates in an infinite cycle. So it gets something from the memory, does a derivation, puts something back to the memory, gets something from the memory, creates some derivation. If the derivation is true to the is a relation, and then puts back to the memory. So that's how it works in particular. So from it puts the derivation or inputs to the global buffer, which we're going to implement into the memory, then triggers the local inference, which is revision for the related concepts. The next, basically, we select the concept from the memory, from that memory, the right dot. After that, we select the task link, which points to the task from the concept. So from the task, we selected the concept, when we select the task link from here, which points to the task, then we select the term link that goes from the back over here, that goes to the term. And then from the term, whenever the term link points to, we select the belief. And the belief, so that basically term link points to another concept. Inside the concept, there is a belief table, and belief table has the beliefs associated with that concept, which are sorted by the confidence value. And we inevitably select the highest confidence belief. And this becomes the second premise. The first is the task, and the second is the belief from the concept where the term link points to. Then we do some inferences on those two premises, applying all of that inference rules and truth functions to modify the truth value. Then we do apply some budget functions to apply the budget, to modify the budget value, which is priority, durability, and quality. Priority has to decrease, and quality has to be recomputed, depends on the situation. And then basically we also input the conclusion into the global buffer. Then it's going to be again created, again processed, put to the memory, and the operating cycle starts again and again. And that's operating cycle, we call it, it completes roughly in a constant time. Because of that selection, because of that grouping, everything is inside the concepts and the pointers, it always kind of does it in a roughly a constant time operation. This is how the time is being measured in OpenNARS. Now, I want to say the difference between the task and the belief. So sentence can be stored in the memory as a task or a belief or both. So however, the belief can be only judgment. So judgment needs to be processed and absorbed by the system and turned into the beliefs. So belief is a judgment that already has been absorbed by the system and will be used to process the task. It is be used as a premises to participate in the inference. And the task is what to be processed by the system. So system processes the tasks. And this is example of the task processing by the system. So the sentence can be entered by the user. It can be derivation, can be anything. So it enters the system the sentence. For example, a raven is kind of black thing. Over here, the system attaches it the truth value. In case of input, there's going to be default. In case of the derivation, the truth value has to be computed using the truth functions, which are associated with the derivation functions. Now, the task object is being created. The task object has the same name as the sentence. Raven is black. Task is being put to the task buffer over here. Okay, over there in the derivation buffer, or in global buffer for the future. So then the sentence object is created, and there is a pointer from the task to the sentence object. So all the terms within the sentence are parsed, and concept related to the terms are being created or updated. So for the raven is black, there is terms raven and black. The concept for them are being created. If the raven, for example, is already existed, so it's being revised. And all the links, as I mentioned, task and term links are being created, or budget on the links are being updated. Then the budget value is being derived for the tasks, or it can be default if it's an input tasks. And then task is actually put into the concept memory and it's ready to be selected. That's how task is being processed in an OpenNARS. This is an example that make it clear what's the difference between task and term links. So over here, we have the task entering the system Raven is bird. This is a task in the orange. And the bird is an animal. Two input tasks we have, for example. Those truth value is default because it's an input. Now the concepts are being created. Task concept being created, Raven is bird, Raven and bird. And also for the right task as bird is animal and animal. From Raven as bird, there is a task link. And from the Raven and bird, there are also task linked to corresponding tasks. So from the Raven is bird, there is a red link, task link to the Raven is bird tasks, the same as from the Raven and from the bird. But from the bird, there is another task link to the bird is animal. And the same from the bird is animal and animal. So whenever I select this concept for the participation in the for the inference, I would have two items into the task bag to select from. Then also the beliefs link, term links are created. The term links is basically in blue here. From the Raven as bird, it has the two terms inside of that related to that concept, which is Raven and bird. And notice that have the two, it could be bidirectional links, but it's actually two different links. So from Raven and bird, there are two different links from Raven to the Raven is bird and vice versa. The same is for the Raven is bird and bird and bird and animal, and bird animal is an animal. The reason for having two different belief links is because everything but the beliefs itself have the budget value attached. So I'm sorry, it's not a belief, it's a term links. The budget for the link from Raven to Raven is bird often differs from the Raven is bird to Raven. That allows different participation or from the inference within the inference cycle. So this is the difference between task link and term link. Now those are the basic up to now 5, I would say, syllogistic rules which are used into the inference cycle. Each of the rules has the related truth functions. It can be found online, the exact formulas. There is no sense to put them here. But whenever we select concept, we select the task and we select the belief from that concept. So basically, we apply one of those rules onto premises, and then we compute with the corresponding truth functions. We compute the truth value of the system. After that, we basically adjust or create the budget value, attach the budget value to the sentence. What also there is in the system, there is extended Boolean operation, which we mentioned. Every rational number is treated as a Boolean number, and we try to try to make an operation similar to the Boolean and, or, and not. And also there is like utility functions also, like some of the special cases of the maxes, mins, or truth expectation, for example. Truth expectation is not basically the utility functions, but something which allows the choice rule to function properly and the budget value to be computed properly. So truth expectation is, although the truth expectation can look similar to the truth values is summarizes the evidence in the past which is collected by the system. However, truth expectation is basically can predict in future how the statement will be valid in the future. So if the truth expectation also in the range from 0 to 1, if truth expectation approaches 1, it means that a certain statement is always be true in the future. If it goes to 0, it's not being true. And that's how it's computed, being that formula over here. And it's used as a choice rule. So the higher truth expectation then means that that statement is being selected whenever the choice is being from the statements with overlapping evidence. Truth expectation is also used to create, to compute the quality from the budget functions. So that's over here. Quality. There is a utility functions called truth to quality. It can be considered as a budget functions, but mostly utility functions. So having the truth value of the item, we can apply truth expectation to create a single a single truth representation of the statement, and then having that, we can create the that we have computed to quality. Now we come to the budget functions, because budget functions is really important stuff in the Nars. So basically, the meaning of the statement, it's evidence summarized by the truth functions, and its importance by the budget. If the statement is not true, it's useless. It gets only negative statements. If statement has the low budget or low priority or quality, it would never be chosen to participate. So nothing will be derived using that statement. So the meaning comes from the both truth value and the budget value. And the budget functions are the functions that modify the budget value. So the main function is the budget and inference, which creates a budget for derived task and also updates budget for selected concept term links. Budget value is a little bit tricky because, if you can see here, budget value is attached to the concepts itself, to the sentences, I mean, that's up to the term links and to the task links. And computation for them is really different because it's really different in terms of what is premises, what are the premises in a certain inference. For example, for the term links, it updated differently than for the concepts, and for the tasks link differently than for the term links. That is kind of active research as of right now, to really choose the correct budget functions that allow the item to stay as long as we need it and make the item important. So the main is the budget inference function. Then merge, we have to merge the budget values, activate. They have to activate the budget value of the concept, revise. For example, same concept comes and they have to revise the budget of the concept. And as we mentioned, there is truth to quality, which basically converts truth value to the quality of an item. That is a brief overview of the implementation of OpenNars. Any questions, participation is welcome. And more detailed formulas and everything is available on wiki pages, and the code is in the source code. Any questions? Chat. 1 second.
From YouTube, there's a question from Pablo Mena. What's the input format type? Plain text?
No. I forgot to mention. So Nars has a formal language called the Narcisse, and the Narcisse has a special grammar, type. I can go on over the wiki pages to see Narcisse grammars and annotations. So basically, if you want to input anything to the system, it has to be conformed with the format. And they have all the copula defined, which is a relation, and the truth value in a special format you have to enter. So basically, there is a language which always has to be used to as an I/O for OpenNars. I can put it to the chat over here, the link. It's actually under the construction, under development, how to translate the natural language sentence to the Narcisse. It's also one of the active research area, such that anyone can communicate with the system. Did it answer the question?
I guess so. Well, so the answer is yes, right? It is plain text, but you have a homebrewed grammar.
Right. The format has to be compliant with the Narcisse grammar.
Could Nars learn to use English?
we actually kind of try to figure it out, how to apply Nars for the natural language processing. Do you mean by learning English? What do you mean by that? Such that we can just type in English and it will be converted to the Narcisse?
Yes, I mean, if it's good at learning and it's good at learning patterns and concepts, couldn't it just be rigged so that it continues to get better and better at English?
Patrick, did we experiment with that? I remember.
Yes. In principle, we expect that natural language should be something which can especially be well handled with non-axiomatic logic, because in language you often have ambiguity and other issues where a sentence is not complete or a part of it is missing. And in the past, we tried some experiments where we essentially tried to let the system establish a meaning, a represent relation between a sentence and the concept, and so that we just give more examples, and the system essentially learns the meaning of a certain fragment. But it's so far where we failed so far is mostly from a control perspective, because the inferences get more complicated when the language structure is more complex, and so in theory it should, the logic should be very suitable to reason about language, but from a control perspective it's difficult to handle it properly.
I just post a link to the chat window. You can see there is a technical report about our plan for natural language processing.
Great, thanks.
Additionally, what we also did, because there's also a conventional technology, we also have created a shallow semantic parser, which simply maps simple English sentences into Narcisse. This is not the full story because it's parsing, and we think the idea of parsing, the idea that a sentence has only one meaning, is wrong. So this is only a preliminary, or it's something which should make the interaction with the system easier, but it does not solve the full problem of natural language understanding, where certain phrases or word combinations can have multiple meanings and mean different things in different contexts. So it's still a lot to do, but later actually you will at least see the shallow semantic parsing thing working.
Mm-hmm. So another question, can system automatically update beliefs in a way to disambiguate terms? So do you mean that there are multiple beliefs in the different concepts to the same term? Is that what you mean? So example, split automatic peacock into.
Yes, I wanted to ask if certain point you can recognize maybe that there is no consistency in the way that the beliefs are given to the system, and the most logic explanation is that the term is ambiguous.
The beliefs comes from the judgment. So I'm actually not getting the question. Terms are always, yeah, I mean, term has its own, term has a concept, right? And the belief table is inside of the concept. So it's sorted by the confidence value inside of that, all of the beliefs of the certain term.
I guess he's asking for the relationship between concepts and words. In Nars, they're separate, so there is a many-to-many mapping between concepts and words. So one word can correspond to different concept, and one concept can be related to different words, and the relation are context sensitive. So it will be updated from time.
Mm-hmm. Yep.
Okay, thank you.
Mm-hmm. Anything else?
Could you come back to the expected
Truth
something else?
expectation.
Yeah, and explain how you intend to use it. I mean, when I see it, I see that it is basically it's the mean of the second order distribution in some cases. When it's completely flat, for instance, the confidence is 0, and it's the result is 0.5 no matter what is the frequency. And so like exactly how do you use this formula?
So the semantic of that is that if confidence is 0, that becomes 0.5. You're absolutely correct. And 0.5 means that the system is not really, there is no, the system is not sure. It's completely uncertain. Either it's true statement or it's not true statement. That's what the 0.5 is. For example, when evidence is 0, then the frequency is 0.5 also. The system is like unsure. So whenever there is 0.5, there's always like uncertainty of the system. Closer to 1 is that the true statement has to be hold for long. Closer to 0, basically it means that it does not hold. It's not true at all.
Right, but what about the situation where the confidence is very high and the frequency is 0.5? How are you going to make the difference?
But it's very. I see what you say. But it means semantically. That means that we have huge evidence saying to us. So many examples has been collected saying to us that that truth of the statement is not really. The truth of the statement is uncertain.
Right. It has maximum entropy.
Right.
Okay. And so
and that becomes the same for us because truth expectation needed to make a choice and create and really compute the budget.
And so okay, so the truth expectation, so its return is used in local inference and budget. So you said that the budget is basically the amount of attention
quality,
you give to something.
Amount of quality, which is a long-term importance. So truth expectation is something to predict, well, something to predict the future.
So
actually.
Truth expectation is equal to quality?
There's a bigger than that. Over here, it's not equal to, but it used to. It's one of the main thing to compute the quality. So whenever we need to create a budget function and we don't have it in any, if for example we just initialize it, we need to come up with something, and we treat its truth expectation, we convert it to quality. In this case.
And is there something else than truth expectation to calculate the quality?
Yes, there are, for example, budget inference over function calculates everything, priority, durability, priority and quality. Okay, maybe can. One second.
Can I add something?
Yeah, you can add while I open. Yeah, please.
There's this issue of how which quality should a concept really have, and there are some innate or intrinsic aspects, like how complex is the term which names it. So the complexity plays a role. on the other hand, also the truth value of the beliefs in it. So if it has something which is very true, it maybe is more important in the long term than something which has little truthfulness or even contradicting evidence. So so there are some learned aspects of quality, but there are also some intrinsic aspects based on, say, the complexity. But there are also some other factors. Quality calculation is really a large issue. There are also in Cox literature, there are many different considerations. What makes a concept more important or less important than another?
This is the high-level table. I mean, high-level. There are many special cases of that inference, but it's a very high level how to compute the quality. So, and it also becomes on the data type you're dealing with. So for the tasks or the terms are different. And this is basically how it's done. But for the initialization, the truth to quality is always used. Because first we have to initialize the budget value.
This is also one aspect which is often criticized about the system, because the logic makes easily sense, but the control mechanism is a very complex piece with many different components. Where even something like the quality calculation for concept is already something complex by itself, and so it's not easy.
Okay, so you're saying that basically the coherence of the logic requires the control mechanism. I mean, that's what I'm sort of taking.
Or at least basically the control mechanism is what decides what to pick to create further inference. Which premises do you want to retrieve from memory to derive results? And so the system needs a way to prioritize certain information over other information, and also in different contexts. And this is a difficult issue, how to make sure that what the system works on is really contextually relevant to what the system currently wants to achieve. And that's a big issue. We also have a new implementation which uses much simpler considerations, much simpler budget values and budget calculations. It works for most cases, but in the long term, especially if you want to get to human level intelligence, there might be some factors which this more complex budget system or those more complex budget functions capture, which a simple treatment may not capture. For instance, in the new implementation or application related implementation I'm currently working on, we simply say that the quality equates to usefulness in terms of how often was a certain concept used and how recently was it used. But this is not the entire story. To some degree, you also want to incorporate other aspects like the complexity of a concept, because if a concept is more complex, it also demands more time to get something useful out of it by inference, because all the activity in the system is performed by individual inference steps, which can transform some piece of information only step by step. And so if something is more complex, often you need more inference steps to come up or to use the information you have. And in that sense, you want the budget system or the control mechanism overall to favor more simple representations, which can easily be used, and it's it's essentially like a form of compression where you want the system to find more simple representations. Because if it would only work, if it would work with more complex ones, it demands more resources, and it's also more unlikely that it will be able to get something useful out of it. So there, in our experience, it makes sense that we bias the system towards more simple representations, which is also related to Occam's razor. But we don't just say simple things tend to be more true than more complex things. Instead, we justify it according to the resource usage, in terms that simple representations demand less resources to work with. And so it could be that sometimes a complex concept could be equally useful in some cases, but already finding it will be very resource intense, and so we don't buy the original form of the Occam's razor, where we say simple is simply better without a real explanation. But we say simple representations are better because they demand less resources. So from an insufficient resource perspective, we want the system to find simpler representations which are workable, and especially also if you take the real-time aspect into account. When the system works on a problem, there might be new problems appearing at any moment. So it has to take into account that each inference step it takes is itself taking some time to be complete, and so it can't just arbitrarily reason in any direction and assume that it will have.
Does it take into account the time and the resources of the inferences via reasoning itself?
Oh yes, exactly.
Oh well, that's great.
So that,
okay,
so
that's excellent.
The time is itself a factor in the resource allocation, and this is actually a very tricky part. In some sense, for instance, the back structure we saw before, where items are simply ranked according to the priority, and higher priority items have a higher chance to be selected, and if they are taken back into the structure, their priority is decayed. If you do this, even if you don't know what operations you will do on the items you sample, if you just do this to decay items priority whenever you use them, you will have the effect that that the current items in the structure tend to be contextually relevant, because the old ones have already been selected and decayed in their priority. So there's already by this mechanism where you decay the priority of items, you get this effect that the items which currently have a high priority tend to be new items, and hence to be more contextually relevant. But of course, it's not the entire story, it's just one aspect of this entire picture.
I have maybe one final question. How do you balance exploration and exploitation?
That's a good question. We believe that essentially the right balance between exploration and exploitation depends on the context. So it has to be something which is context dependent. For instance, we don't want to say to give the system a certain search strategy where we pre-design the depth and maybe in what width it searches, and we don't want to do that. Instead, we simply have this reasoning mechanism which is data-driven, and the data items and the priority themselves decide how much the system will explore and how much it will exploit. So if, for instance, in the back structure, if you have the situation that only a few items have a high priority, then the system will naturally exploit, because only those few items will get selected most of the time. While in another situation where you have priority values, where you have a lot of high priority items on the top of the bag with similar priority, they will all have a similar chance to be selected for inference, and then you have automatically the effect that the system will explore because those have similar chance to be selected. So the idea is to leave explore versus exploit to be completely or mostly data dependent property, but it's not fully data dependent, because essentially you also want to define a mapping which maps from the priority values in the back to the probability to be selected. And so there's the question, do you want a linear mapping, or do you want something like that there will be, that the low priority items have almost zero chance to be selected, out of being in range 0.1 or something. So there's also an intrinsic aspect of how you design this back structure, how much it favors high priority items over low priority ones, but else that most of the balance between explore and exploit is actually a data-driven thing, which is context dependent based on the priorities which are existent in the back. So from this perspective, there's also no fixed algorithm which, for instance, would apply a planning up to a certain depth or something like that. It's part of the system can plan, but the planning process itself is performed by doing those individual inference steps. And so sometimes when the system, say, applies some deduction rules to plan ahead a bit at the same time, then it might select some other inference to find some analogy or some similarity between those structures. It's how, so there's no predetermined algorithm which says now the system should plan, or now the system should find analogies or something like that. Instead, it's completely data driven. What will be done depends on what will be picked, and what will be picked depends on the priority of the items in the bag. That's the general idea. The only thing is it's not difficult. It's not easy to get it right, because you want this system to be to some degree self-organizing, and so you don't want to impose any task-specific biases, and you want to have a general way to control the system. So, which, how to say it? So it should naturally be data-driven, but it's not easy to get this right. But overall, I can say the system Peter has now shown, which is the current or the Java implementation we have, which tries to be a complete AGI system. This is very difficult to understand, but we also, almost everyone in our team has his own implementation. So we also have implementations which are simpler, and it's interesting to see that even simpler implementations can already do impressive things. And but you will see this soon, because my talk will be about a simpler implementation.
still have more questions, but I'm worried to not give enough room for the others. So, well, if nobody is asking, so you mentioned that exploitation versus exploration is determined based on the priorities, and do you characterize priority by a single number, or do you have a confidence associated to priorities because it feels that it could be useful in terms of well, assessing a good balance between exploration and exploitation?
We have something called durability, which is kind of like confidence for priority, because it says how stable is maybe not the right word in this context, but at least how fast the priority should decay over time. So it can be that a certain data item will have the attention for longer than another one. And then additionally, there's also this quality parameter, which indicates long-term importance. So if the priority of the items, say it didn't work on an item for a long time, or the priority is low, let's just say the priority of 2 items is equal, then the item with if it's a low priority, then the quality will still give the item with the higher long-term importance a higher chance to be selected, because how it's actually implemented is the priority will not fall below quality times some constant like 0.1. So if the quality of the item is 1, then the quality will not sink below 0.1. So a high quality item will not go below a certain this priority barrier. So if the items are not really, if there's currently nothing the system has to do, it will still prefer the item which has a higher long-term importance to work on, because its priority barrier is higher than the other one, than of the other item. That's an additional aspect here.
Hey, a silly question to see if I'm really understanding things right. Suppose that this Nars system was running for a while and people inputted a bunch of facts. And then suppose everybody stopped inputting facts, but Nars keeps running indefinitely. Then would it eventually just go through and exhaust all the facts that had previously been inputted into it, and then perform all possible calculations from them, and then achieve some final fixed truth values, and then just sit there indefinitely until further input was received? Or would some of if enough inputs had been received before the users stopped using Nars, then is it possible that some of the very old inputs would sit around forever and never be used?
That's a good question. It is that it's actually related a bit to the previous. So if you, as you say, you let the system run indefinitely and you don't enter something new, you will still have the different priority values of the items, because some of them have a higher quality value, and the one with a higher quality value have a higher barrier under which the priority cannot fall below. So in the long term, you will have the effect that the higher quality items are still processed more often than the ones with lower quality. but still the lower priority items have still a chance to be selected, even though the chance is lower than for one which has a higher priority, or in this case, validity. There's another aspect. It will not store all the statements which it received over its lifetime, because it only has a fixed storage. So the insufficient resource assumption is really inbuilt in the system. It can only consume up to a certain maximum amount of memory. So it has a eviction strategy which is very simple. So when the bag gets full and a new item wants to get into, it simply removes the lowest priority item. When this happens, the lowest priority item will be lost, so to speak. So this is how it manages to keep a fixed size memory. And what this means in your scenario is that that a lot of input which has been given over its lifetime before it was run for some unspecified time without new input, that it's likely that a lot of information is not in the system anymore, because the memory is likely already full, and a lot of the inputs have been forgotten. So it will only think about the items which it still has in its memory, essentially. And the idea here is there are multiple things which have to be taken into account here. Ideally, we want the high quality items to be beliefs which are really useful for the system in terms of fulfilling its goals or to answer user questions. So it should keep the information which has historically been important. And ideally, this is the information the memory will fill up with over a long time period. And or the other information the new information will be there for a short moment, but if it does not turn into something useful, it will be eliminated. I hope this answers the question.
So I suppose an obvious way to tie this in with certain other AGI topics would be to introduce some sort of compression mechanism to run in the background, so that maybe Nars could compress old things to try to store them longer. And of course, this, as you all obviously know, is a rabbit hole that goes infinitely deep, and probably whole entire tomes of books could be written on the subject.
I agree. Compression is an important aspect, of course. There's also another. I mean, the counter mechanism naturally should tend to compress information because it has this complexity bias. So concepts which are more simple and more generally applicable tend to survive better than other concepts. So there's naturally some pressure for the system to compress its experience. And the thing is, it's a bit more than just compression, actually, because if we how to say, because the information it wants to retrieve is not only describing a lot of experience, but experience which is relevant for fulfilling its goals and answering user questions. So it's a very directed form of compression, because it tries to maximize its capability in terms of goal fulfillment, essentially. And this is what the control mechanism tries to achieve on a global scale.
I have a question about how do you, I mean, does it enable multiple models of the environment, or do you have just one big model? I want to compare that, for instance, with a Solomon induction, or more generally Bayesian model averaging, where you just have an envelope of our models. So yeah, how does that work in that respect?
I think the best way to look at it is to see each statement in the system as a partial description of what it has experienced. So it's not trying to build a complete model of the environment in the sense that there is one model and it has to maybe adjust this one model and replace it with another model if it doesn't work. It's more like it has a lot of small tiny pieces which describe small aspects of the environment. Like if I can describe something like how can I open the door? I need to use the door handle, and this does not describe the room around me, but it describes a small aspect of the situation around me. There's a door on the other side of the room, and I can use this information to open the door. And I think this is really on the heart of, this is really the heart and soul of this conceptual representation idea. To have partial descriptions of the environment which are at the same time composable, so you can build other things with using the concepts you already have, but at the same time the concepts represent only a small aspect of what the system has experienced. And it's all those different concepts with the different priority which essentially make up the system's current understanding of its environment. So it's like a lot of tiny micro models which the system has. But the essential thing here is that the model does not really describe some external coherence like Newton's laws or something like that. Instead, those statements simply describe relationships between the patterns it has experienced. How did it experience them? Depends on how it's embedded, depends on the sensors it has, and the modalities, and so dependent on how it retrieves, or how it retrieves information from its environment, and how this is structured, it will form concepts based on those experienced patterns. And so what this also means is that if you have one system which, for instance, has only vision, and the other system we only give it a microphone, and then there's a cat, one system sees the cat with a camera, the other system only hears the meowing of the cat. And one could say both both systems have some kind of concept of a cat, which is this experienced pattern of what the cat looks like in one system, or for the other system, what this pattern sounds like, or what the sound is composed of, so to speak. But even though those both concepts, we would say, refer to this external cat, this is not what the system actually needs to assume, that it really corresponds to this external entity. It's more like it only needs to summarize the patterns it experiences. And so two concepts in two different systems can be composed in very different ways, even in cases where we could say it refers to the same entity in the outside world. So it actually, it solves a bit of this problem of traditional symbolic AI, which is that each pattern or each symbol has an external entity to refer to. in Nars, this is not the case. It's the relationships it builds are simply between experienced patterns without the necessity to have some one-to-one mapping to some external entity.
Well, I mean, if you consider Solomon induction, I mean, if the binary sensor is considered to be internal, well, then it's also some sort of introspective induction mechanism. But so I have a follow-up question. If you have contradictory patterns, predictive patterns, so for instance, you have one pattern to predict that the door is going to open and another one, how do you, I mean, that would be the equivalent of having multiple models for this restricted context. How do you aggregate these contextual models in order to make your final prediction?
That's a good question. Essentially, it comes a bit back to the control mechanism itself, because somehow we want the system to activate the right hypothesis when it, for instance, experiences a door. Then we want the system to retrieve the relevant knowledge. For instance, if it wants to get to the other room, it needs to retrieve the knowledge, which is this model, or this partial model, or how we would say statement about how to open, or multiple statements about how to open a door via a door handle. And what we have here is essentially, here we can make use of the compositionality of the concepts, because when the system sees a door and it sees the door handle, this door handle pattern is actually a sub-pattern of the more complex pattern, which is to say, if I press the door handle, then the door will be open. So the idea here is to make use of compositionality. In Nars memory, the system never really has to search for anything, because how things are composed together, it naturally gives the system a way to prioritize the right things in the right moment via its memory structure. So when it sees the door handle, it will automatically activate or increase the priority of related concepts. And so it will then have a high chance to inference on how to open the door if its goal is to reach the other side or the other room. So essentially, we try to avoid search, we try to exploit composition, and that's essentially how we try to address this.
So basically, by using composition, so if you have, I mean, I don't see exactly how all that works, but like I guess there's some kind of spread of importance, a priority, and you might be in the situation where from the handle you could spread equally to two different situations. Well, I can't give a concrete example because I don't know if there are multiple ways to use a handle, but well, yeah, I mean, for instance, you could have a door where you have to turn clockwise and the other one where you have to turn anti-clockwise, and you have to decide which way to go. And if you have so I mean, how do you deal with competitive predictive models? Basically, I'm still I'm still not seeing that very clearly.
The idea basically, if we think about activation spreading, as you mentioned it, it can be seen like a form of voting. At the beginning, it doesn't really, it isn't bad if we just distribute the same priority to the links, meaning to the components. So, and as long as there are multiple items which vote for it, for instance, it sees this door handle, it will activate a lot of knowledge about door handles. A lot of this information it will activate is not really relevant. Some information like how to open it will be relevant for reaching the other room. But now there is also this score to reach the other room. And this itself will prime for this door handle concept. And this is where the difference happens. Even though initially it spread the activations equally among the related hypotheses, there are multiple tasks in this case. One is it sees this bottom-up pattern of the door handle. On the other hand, it also has this score to reach the other side of the room, which via implication statements also has this door handle as a component. So this door handle will now have the highest priority among a lot of different information about door handles, which only has been activated by the experienced pattern, while how to open the door handle has been reinforced 2 times by the current observation and by the intention of the system. So by what it essentially, by its score. And this is how this is essentially done. It really tries to use this activation spreading as a voting. And this activation spreading is also not simply spread among all the links. That's also happening. But there's also spreading by inference. For instance, if the system derives by backward inference, so it wants to reach the other room, and it has multiple hypotheses how to reach this other room, and there are multiple candidates, and one of them will be to use the door handle. And so in this case, it's a backward inference, which causes the derivation of a subcore, which will then additionally prime this concept of a door handle and the related information how to open it. That's the idea. And also another relevant part here is because you mentioned this, what if you have multiple competing hypotheses? Because clearly it's not only the priority which matters. It's not just, is this currently something I see, or is this currently something I might want? This is not only the important thing, it's also important if, how true is it? Is this what I see really a door handle? How sure I am based on the appearance of this object I see? How much do I believe that opening the door handle will allow me to get to the other room? And so it's also the truth which is relevant, not only the priority, which comes to the next consideration, that whenever we derive a task, it's not just the priority of the task which led to its derivation which matters, but it's also the truth expectation of the task which matters. So if something has a so the hypothesis which has a higher truth expectation essentially will tend to be the one which causes the actual behavior. And just one moment, I will get the water.
Okay, but yeah, thank you. That was interesting.
You're welcome. And in the architecture, I think I will now already switch to my presentation. There's a simpler system we currently work on, which tries to make certain simplifications. And one of them is, for instance, if you have multiple hypotheses to reach a certain goal, simply select the hypothesis with the highest growth expectation, for instance, and which has the precondition currently fulfilled. And this is something which also the Java OpenNAS does, but there it's less restrictive. The Java version is essentially leaving it to the back selection, while in this new system, there are some pragmatic design decisions we made to make it work better for application purposes. I think I will press screen sharing here. Can you see my screen?
Mm-hmm. Yep.
Perfect. So we have developed a new implementation, especially suitable for applications. It's still meant to be a general purpose reasoning system. It also uses the non-axiomatic logic, but it makes, as I said, a lot of pragmatic design decisions. And it tries to combine only the stable aspects of the theory and has a strong focus on agency. And also we have chosen C as implementation language. It performs very well in terms of computational resources and speed. Overall, this new system has some desired capabilities, which is, of course, we want to use the non-axiomatic logic because we think it's the right truth calculus and we have achieved a lot with it. Another thing is it should be able to learn from event streams in real time. So you can constantly bombard the system with new information. It should not cause trouble. And when you do this, it should be able to extract sensory motor contingencies. So if you have events from sensors and maybe also events from actuators streaming into the system, it should be able to form relationships like if I see this plus symbol there and I drive towards it, then my battery will get full. For instance, if it sees the loading station and in front of it, it knows, okay, if I turn the actuator or the motor to move forward, then it will reach the loading station and the battery will get full, for instance. Or kind of sensory motor contingencies, it should be able to extract simply from a stream of events. So this is the major paradigm here is event streams. We don't assume a state like in reinforcement learning where we say this is a complete cognitive state and you have to find a mapping from state to behavior. We don't do this. We say we have different events representing different information coming from different sources, from different sensors, from different users. We don't care. So different events coming from different sources. And this streams of events, we want to see certain patterns. And this could be something like something traditionally precondition operation leads to consequence. And it should be a major aspect of this new system is to make it really effective in learning those sensory motor contingencies. And it should be able to use them to predict the future and to be able to plan ahead to reach goals. So it's a system which really tries to focus on agency. It doesn't completely focus on the AGI aspect like the Java implementation, because this one is meant to one day hopefully become more human level in terms of what it can reason about and introspection and so on. In this system, there is no introspective reasoning in this new pragmatic design. It's just a simple design which focuses on a system which can learn behaviors and can reach outcomes and plan ahead. And And I want this system to become a core for autonomous systems, including robotics. We are currently experimenting with robotics, which can learn new behavior on the fly. Unfortunately, our results are still being made. So maybe for the September conference, we will already have some impressive results. But Francesco Lanza will talk more about what we already did in the afternoon. So this new system still follows the foundation of Nars, which is the philosophy that intelligence is the ability for a system to adapt it to its environment while working with insufficient knowledge and resources. This is the idea. If you already know everything, then you can simply compute the solution. If you have a data set which is large enough, sure, you can increase your detection accuracy. There's no magic. If you have the resources and the knowledge, you can do it. We know it. If we have seen it several times, including in very impressive machine learning successes, including the AlphaGo system, which is to some degree impressive. But if you really look at what was done, the system already has a perfect simulation available. You can exploit the simulation how long you want. You just throw enough iterations at it, and then you will end up with a system which gets better, hopefully. But we try to focus on something else. We try to make the most out of insufficient knowledge and resources. So if the system does not have the knowledge yet how to achieve a certain outcome, it should be able to gain more information actively, for instance. It should be able to, it should not simply say, I don't have the information, I cannot do it. Or if it doesn't have the resources to compute the optimal solution, it should still be able to suggest a solution. If I look at the Go board, I cannot tell you what is the optimal move. No way for me. My brain cannot do it. But I still can see certain patterns, and I can find some behaviors which I, in my few times I played Go, found to be more useful than others. And so I can try to play Go. And maybe with 10 games, I can already play a bit better than someone who plays it for the first time, maybe. But in any way, we want a system which can deal with the situation where it doesn't have the knowledge to calculate the optimal solution, or it does not have the resources. If you give the system only half of the memory, it should still work. It cannot store as many concepts anymore, only half of the amount. But it should still be able to do something and to find concepts which are useful, and hopefully the most useful concepts still survive, even though it can only keep half as many as before. Also, the system should always work in real time, so you can really bombard it with information. If it works on something, we expect the system to be able to interrupt its task. For instance, we don't want a system which calls a planning algorithm for a certain amount of steps, and then it's not able to react within until it's done or found, or can say it didn't find a solution. Instead, we want a system which can plan ahead one step, and maybe new information comes in at the same time, and it can reprioritize what it's currently doing. So if for some reason this new task happens to be judged to be more important, it should be able to interrupt whatever it is doing. So for instance, if there's a dangerous situation, we don't expect it to be stuck in some kind of algorithm or fixed procedure. It should always be able to react and to reprioritize what it is doing, to maybe give up doing what it is doing for something more important. So this is also the key philosophy here, that all system activity is done by atomic inference steps. Sure, an atomic inference step cannot be interrupted, but on the other hand, it only takes 1 to 2 milliseconds. This one cannot be interrupted. Okay, but you can interrupt a process which takes multiple inference steps to solve, like seconds or even half a second or 100 milliseconds can already be interrupted. And the good thing here is if you work with atomic inference steps, it means you can have a currency for computation or for computational effort. This is one way of how I look at this. Maybe it's also the reason why Dr. Bong called it budget. The idea is that you can know how much effort or at least you have a measure of effort. So if some algorithm or if some task demands more inference steps, there's a way to handle this. And yes, that's essentially the idea here. To have some kind of resource currency so that different computational processes can be compared. So if the system works on something more difficult, it can interrupt it at any moment. And why is this important at all? The reason is, and here I really almost missed the point, the most important thing is when you are thinking, the time does not wait for you to finish. The world changes, the circumstances change. So if you think or when the system thinks, the world will already be different. And so it needs to have a way to deal with this. And this is really the heart of this real-time aspect. Another aspect is that new information can always challenge existing beliefs. So there is no hard-coded truth in the system. Whatever information you give it, it can challenge it. It can collect new positive or negative evidence for the statement. So there is no axiom on object level. There is, or beliefs the system have are reversible by new experience. Yes. And also, maybe important is that the different cognitive functions are simply a side effect of the reasoning process. There's atomic inference steps the system takes. Some of them might correspond to planning, sometimes some to some kind of analogy making, or to some compound construction. It really depends on what is inferred. So, but enough philosophy. So another thing is the decision-making paradigm we are following is fundamentally different in some ways to what we see in traditional AI. For instance, this system, openness for applications or ONA, solves the temporal credit assignment problem for multiple outcomes. So there is not a single reward signal, and you want to only associate, okay, in this state, if I perform this action, I will get this reward. We are not only doing it for a single reward outcome, but the system, for every event it experiences, it will be able to find ways how to achieve it, for instance. Even when it's currently not a goal and it just watches the event stream, you want the system to be able to learn, okay, in these circumstances, this event will happen under those different circumstances, another event. And later, if you then enter a goal, likely it will already know what to do, for instance, even though it just watched and didn't even receive any rewards so far or any goal being fulfilled, because there was no goal. It was simply watching its event stream, and it was essentially finding certain patterns. Yes, but the point here is also that goals can change. Even in biological systems, if you look at even simple insects like a bee, they don't learn a single state action mapping. They don't do that. They have different internal drives. It could be something like bring the powder from the flower. I'm not sure how it's actually called. but there are different, often even different day cycles or certain how to say so the behavior of the insect depends, for instance, on the time of day and whether it's currently hunting or not. It depends on some internal core. Is it currently hungry? Is it currently thirsty, or something else? So it's not really helpful if you learn a single state action mapping if what you really want is to have something which behavior depends on the actual internal cores you have. So if you're hungry, you want to find some food. But if you're not hungry, what's the point? So why use a behavior to retrieving food if you already have enough food, for instance? So you want a system which can handle changing cores effectively. And you don't want the system to go through training or even the system learning and relearning its entire Q table just to be able to deal with the situation where the utility function changed. Why did it change? Because the core is different. Because, for instance, in an organism, as I said, you have different drives and different urges which are active at different moments, dependent on their fulfillment. And yes, in this sense, this system is more general than reinforcement learning. We will see it can deal with the situation where you really want to achieve one outcome and one reward, but it can't do it. To find one state action mapping, but it can also do tasks, or it's expected to be able to solve the temporal weighted assignment problem for multiple outcomes. Hence, it should also be able to do it for a single outcome. So it should be able to.
Sometimes your microphone, I think, hits something. Can you check?
Oh, yes. Oh, maybe now it's better. I hope at least.
Yeah, it was good. We just heard it in the last couple of seconds, couple of times hitting something against the microphone. Thank you.
Okay. So what this system still, even though it's not really intended to be a human level AGI, it's a high core. Seriously, we don't know how to exactly reach easily. And so this system has a lot of pragmatic decisions, but its decision theory is still fundamentally not reinforcement learning, because we think reinforcement learning cannot even explain the things we see in insects. And this is a big issue to us. So the system can really try to have a more general, a multiple outcome dependent way. So for instance, we want the system to be able to learn from observation and then apply this knowledge it has gained from the observations, even though there was no reward at all involved so far. And this is essentially what we want. We don't think AGI has much to do with reinforcement learning decision paradigm. The next thing, of course, the system should still be able to plan ahead. Or ideally, it should be able to plan ahead. But here, there's no exhaustive search, which, for instance, says we plan ahead for 10 steps to keep in resource bounds and say then if we didn't find a solution, we're screwed. No, it's attention-driven, data-driven selection of course and of events overall. So it has some kind of inference loop similar to what Peter described, and this system a bit simpler. And what it works on, or which course it picks, depends on the priority again. So if it has a higher priority, it will tend to work on it. And so again, the explore and exploit thing is essentially data-driven. It depends on the priority distribution in the data structure. There's no exhaustive search, and this planning process can be interrupted at any time by changing circumstances, by changing course, or anything, or another important task which comes along for some reason. So essentially, It's a bit like a mixture between belief, desire, intention model and reinforcement learning. We have this gap in traditional AI. At one hand, we can learn state action mapping, some reactive behavior. On the other hand, we have this belief, desire, intention model applied in autonomous robotics. They usually don't use reinforcement learning. They use a model which can represent different cores and has a plan library where the agent can select different plans dependent on the circumstances. And that's good. But ideally, we want a system which can do both, right? Which can learn behaviors, but at the same time, plan ahead to reach different outcomes, and a system which does not struggle when outcomes do change. And so essentially what this system is really like, we can do reinforcement learning problems, but it's not restricted to them. It can learn by observations. It can learn how to achieve different outcomes. It can learn different or new behavior on the fly, and it can use this behavior to plan ahead multiple steps, as you often want in robotics, because there it's a bit more issue if you run into a war or something, so you want the system to be more sample efficient. And it's good if you can plan ahead and find something which likely will lead to the outcome you want to achieve. So why is it more general than BDI model? The reason is it can learn new procedure knowledge on the fly. Why is it more general than reinforcement learning? Because it can learn to predict multiple outcomes, not just reward. Also, the system can be used for question answering, as we will see. I hope I don't. Oh, okay. So the current state of the system is it can show everything I have talked about. This is not wishful thinking, but it's actually a released version you can try on a variety of tasks already. The special thing here is there's no example-specific hyperparameter tuning between examples. So this is a way to ensure generality. We don't think it's a good idea if you have a model and you do hyperparameter tuning for one task and hyperparameter tuning for the other task. How general is this then really? If you change the hyperparameter, essentially you have something else. You don't have the exactly same thing anymore. In the human brain, you can't just change to some brain surgery for a new task. You have to find a way for the system to be self-organizing in such a way that it can deal with a wide variety of tasks on the fly without any hand-based or human-based hyperparameter tuning. This is one thing. Another thing which you will find unusual here is that this you will see this is like a bit like a black box if you use it. We don't call special functions for special tasks. We don't load special modules for different problems. It's really a unified system where we intend not to change parameters across tasks. I think this is really a bit of the heart of general AI. You want it to be general. You want it to not have a human in the back who adjusts parameters or calls different functions for or configures the system in a different way for different tasks to perform. So overall, Nars or any Nars implementation is not a software toolkit where parts are invoked separately, but you will see it's a system where you can interact with Narses. So there's a formal language behind it, yes, but the good thing is it's not domain specific. So unfortunately, so far you only have seen the overall philosophy or the things the system should do. And ideally, I would like to show you now all the internals. But the thing is, on Thursday, I will talk only about the internals of the system. So to use the DEM effectively, we will now learn how to use the system and what it has to offer. And how it works internally, you will see in my talk on Thursday. That's essentially this. Is because I want to give you a way to use this system. And in previous tutorials, Nars tutorials, we really did not do this, but I think it's a bit of a mistake because you should be able to have a way to use this system. And how it works under the hood, you will see on Thursday. For many examples, it will not even matter because it doesn't work. Or how to say it? It works good enough for most of the examples, so often you can just use it without knowing the internals. But on Thursday, you will know everything about how it's actually done. So for now, we will focus on the usage. So as I said, the system learns by a stream of events. Events can be beliefs, scores, and questions. They just enter the system. How they are produced depends on the application. Could be sensors, could be humans, could be some social network where whenever someone posts something, it will enter as an event. What's the output of the system? Operations and answers. Operations could be something like invoke a motor action, turn an actuator on, or it could also be something like write a message to a user or say a word, something like that. So different operations with which it can interact with its environment. Also, you will see answers because you can also ask the questions about things. It can also answer you in Nars. So this is the overall way how you interact with pretty much any Nars implementation. You don't have any special task-specific plumbing. Instead, you have just events which enter the system, and you will get operations and answers in return. This is ideally how we think an AGI should work. You give it information, it gives you information back. That's how we set up this thing. So what is an event? So event is essentially a Nars term. It could be something like cat is an animal, which is already quite high level. It could also be something low level, like the temperature is low, or temperature is above 10 degrees Celsius. Then there's a truth value attached to this. For sensory events, it will simply encode the quality of the signal. For instance, if you have a sensor which is not very reliable, you define a lower default truth value. But if you have but in most cases, for inputs, it doesn't really matter. You just use some default truth value. That's also fine. But the truth value for derivations will vary dependent on the inferences which are made. But for input, it's most of the times fine if you just use a default truth value. So you don't need to care about this. So you only need to care about what information do you want to encode. Temperature values, or do you want to have some higher level input, like from a convolutional neural network, some detection you want to encode as Nars, maybe something like pattern 1 is a cat, and pattern 1 is left to the other detection, which is a fridge, or something like that. You can be very creative in what kind of information you enter into the system. Then the occurrence time, this one is not really set by the user. Whenever you enter an event, the occurrence time will be the current reasonable time, which is an internal clock. And then there's a priority value, which for inputs is also just some default in this system. Then what's an operation? It's simply a function with arguments, which executes, and that's important, in small constant time. So it's not allowed for the system to execute an operation like a planning procedure where it's not clear when it will end. Here, only operations which execute in small constant time are allowed to make sure that the system can keep on reasoning. So like turn your finger or something like that is okay, but complex invoking another reasoning system, not so. or some algorithm which you don't know when it will terminate is not okay here. This is also very, we saw this before. This is not really, what's really different here. What's going on in Nars is an open-ended process. It does not converge to anything. It does not terminate with the answer and then stop. It can work on multiple problems parallel, and it just goes on with its reasoning process. There's no time where you can say no, where the system then stops. It just keeps going. One thing is missing, the answer rate. So answer is simply an event which is reported as the best answer to a question event. So those is everything. This is the entire IO of Nars. Some information in with some most times default truth value and default priority, and the occurrence time is simply the current time. So you just have to give it some information, and the system can then call certain operations like motor actions. The answers are also simply events given back by the system, which are identified as the best answer to a question of a user. So we will finally get to the hands-on part. As I said, the internals of the system will be explained in detail on Thursday. And so let's go to the hands-on part. So this is a C99 implementation. So you can use any C compiler like GCC, CLang, DCC. Whenever it's C99 compliant, it will run on any POSIX OS, including GNU Linux, Mac OS, Android. It doesn't really have any more dependency. The only dependency is some POSIX API, because we also have a UDP interface for network communication. But other than that, so you can run it pretty much on everything except Windows. But there it's also possible via Sigwin or WSL, some new development where you can run a Linux subsystem on Windows. That's possible, also runs. As a versioning system, you will need Git, or you can unzip it from GitHub, also works. And optional, the test system and other things are programmed in Python. So if you want, for instance, to try the English to Narcisse converter, you will need Python 3 with natural language toolkit. If you just want to run the tests, if you just want to run the system tests, you will not need Python at all. But I will show you part by part. But anyway, what's very important before we dive into this is evaluation measures. We have multiple implementations of this system, and the big question which is always behind our back is, how can we really say one system is better than the other? Ideally, we would compare with other methods for certain problems. Issue is this is highly domain specific. If we compare a general system which can tackle a lot of different kinds of problems and compare it only with a specific, say, algorithm on a specific problem, most times the specific algorithm will be better. But this does not really tell us much, because the system was intended to be a general system which can be applied on a variety of different problems. So we need some kind of way, even if we often cannot compare directly with a domain-specific method, although sometimes it's possible, that's good. But if we cannot do this, we should at least be able to compare our own implementations, right? It would be good. So we thought a lot of evaluation measures, which in this system is taken very serious. For instance, there can be different general purpose measures. Can be something like the answer rate. How many correctly answered questions did the system give in return over the total questions? We can compare this among different implementations. Then we can say, yes, this system gives more correct answers, and so it tends to be better. Or we can look at the average confidence, which gives a measure of the evidence which has been accumulated for the relevant hypothesis. The system which is able to accumulate more relevant evidence is usually better. Not always. You also have to take care here to compare this among a large variety of tasks and not just one particular problem or dataset. That's very the key. If you only compare it for one dataset or one task, you will not get any information about how well the system performs as an AGI system. Next thing, you can do something like average answer time. What is the time demand? How long does it take for the system to give you an answer to certain questions? Or the competence, the rich scores over the total scores. Or sometimes you can also use, of course, you can use domain-specific success rates. For instance, for a particular data set, or something like in Bong, you could simply define the hits plus misses, like here. And all those measures matter. And you want to collect those measures over a large variety of tasks. Then you will get some information about is one Nars implementation better than the other. And many of those are actually also applicable to other AGI systems. So I hope that in the future they will also give us a way to compare also different systems. But often if you compare it just for one specific data set or problem, it doesn't really give you much information if the system you compare with can only solve this particular problem. However, there's the issue if you have a lot of metrics. There's the issue how to keep track of it. You make a change. Some metrics will get better, some will get worse. It's a problem. But you can at least do, it's not a complete solution, but you can combine certain general purpose measures. So we have, for instance, the success rate. So we combine the answer rate, the average answer confidence, how much evidence was collected, and the competence in terms of score fulfillment. And so when it answers more questions, it's better. If it fulfills more scores, it's better. But of course, this is also sometimes problematic because maybe this new system is just only better in question answering, but is not really good in decision making. But this is at least one way you can combine those different aspects in terms of question answering and decision making into one value. And yes, and then you can create a combined loss values. And here the restriction is you want the hyperparameters not to change between tasks. This is really important. If you want an AGI, don't touch the hyperparameters. Find values which work for a large variety of tasks. Maybe fundamentally, mathematically, maybe there will always be environments it cannot handle. Maybe it is that way. But it's sufficient maybe if it can deal with the environments we humans are used to. Maybe that's enough. So this is not really touching on the theoretical issue if there is even a general AGI which works for all environments. I mean, there are theoretical models like AXI, but this one is not computable. So if you make it computable, you have to make certain compromises, and that's a difficult issue, how to avoid biases. I would say that it doesn't really matter. The biases are not that important. You need biases. As a human being, you have inherited a large bunch of biases over thousands, millions years of evolutions. You have inherited those biases. Those biases are not the core of your general intelligence, but they at least let you distinguish your brother from your father. And so we are not really against biases. As long as they are not task specific, as long as they work in a quite general way in the environments humans are exposed to, it's not too bad. So we don't depend on some theoretical fact that would be to that AGI has to work in any environment. We don't claim that. And I think it's a distraction of what we really want to do, to have a system which enhances autonomous systems overall, systems which can learn by their own experience in environments similar to the one we live in. So this result section, actually, we will not capture now because it's also part of the talk on Thursday. There are different examples we have used the system with. Maybe I will touch one just to illustrate how we use metrics. For instance, because metrics really matter. And for instance, we did one project with Cisco, and here we will just, for instance, look at the prediction. In this scenario, the system watches a live stream of cars or traffic. So, and it has a convolution, or it has a sophisticated tracker as a tool, which gives it the information about what is a car. Whenever it detects a car, it will know, okay, this car 67 in this case is at this location, and it receives this information as input events. And after some time, you will see the system derives expectations of where the object will be in the future, which you see here with the pink arrows. And here it's already important to have metrics. You want to be able to measure how well the system predicts, right? How can you do that? One way is to compare with ground truth. Does the car really reach the predicted location in the predicted time, or does it not? So you have a measure which simply tries to see if the object really reaches the predicted location at the predicted time. And you can do that, and then you can capture metrics of how well the system predicts over time. What we found here is with this combination of this tracker, which uses ConfNet under the hood, we combine it with reasoning, so we don't have to train the entire neural network to predict. It simply has to give us the detections and the locations, and then the system can learn very data efficiently in a matter of seconds. It can learn, for instance, the movement of cars. And I think that's impressive, and I think that's important for AGI. It's not really that important if you can increase your accuracy over many years of training them. It's important if the system can work under insufficient knowledge and resource, if it can make the most of the limited smart data it has available. And this is what we focused on so far. Yes, and so metrics are important because else you cannot measure progress. And so we want to be able to compare different implementations, and we also want to be able to compare if we make a change, is it then, how does it make the system better or worse? The more information we have here, the better. Yes, but now let's jump to the hands-on part. So you will need those things here, so you can most likely, on Windows it's a bit more difficult, sorry. You could use your phone if you want. There's an app called Demox. It has a terminal inside. This is one way you could also run the system on your phone. But other than that, if you already have a Linux or a Mac available, this would be best to use this one here. Sorry if I use some Windows users here. Yes, and any compiler will do. So let's just do this. So I'm just now let's open a new terminal. So we make a new directory called workshop 2020. go into the directory, and now we clone the system. I hope you can see it because the text is a bit small. So the system is now cloned. So we see a folder where we go into. I will give you some time to replicate this, and then you need to execute build.sh, then it will build the system. I would say in the meanwhile we can do some question answering in case that a question popped up, because I want to give people some time to. Some people might want to follow this, so they have the time. So if there are any questions in the meanwhile, you are open to ask.
I'm very interested in this mechanism that does the interruption of a task. So while it's not, I mean, I could bring specific questions such as, well, how do you guarantee that this mechanism is still reactive over time? I mean, that it doesn't basically take longer and longer over time. I mean, overall, I'm just curious about this whole mechanism. If the tutorial touches upon it a little bit, that would be great.
So you want on Thursday there will be a very detailed presentation about this. So now I can only give you a very short illustration. CMD plus, that's a good idea. Whoops. CMD plus, maybe I'm the wrong. Let's try here. Oh, CMD plus, thank you. That's better. Now the screen is larger. In case you want to make a screenshot now, make it, because I will answer the question now. So git clone, then it was go to the directory, and then it was build sh. Okay, sorry for the waiting of answering of a question. So the idea here is that there is no explicit algorithm. So we really want the system to operate in a very data-driven way. So events come from sensory channels, then they can be combined from multiple modalities. And what's important here is this thing in the middle. This thing in the middle is pretty much like the bag Peter described. So events are ranked according to the priority value, and the high priority events are selected for inference. So they will be selected to form concepts and to select beliefs from the memory structure. So for now, the details are not that important. Really important is we select the first premise here from the attention buffer, or cycling events queue as occurred. So we have the first premise. Then we somehow sample the second premise from the memory. This one you will hear on Thursday. So now we have two premises, which we can do two kinds of inferences. We can do syllogistic inference, for instance, based on a common subterm, which I called here semantic inference, or it can be something which uses implications. Then here I use sensory motor inference here in the system, and it's related to a temporal. If you want the system to predict an outcome, it uses some implication of the memory. So the implication is the second premise, and then it goes here. But in any case, it's always this loop. To select the first premise, to select the second premise, to do inference, to give the result back to memory. To select first premise, to select the second premise, to do inference, and to get the results back into the attention buffer. So it's always this loop. In this new system, it's actually 2 loops because I separated the concern of dealing with implication and with inheritance. I think it's the best way to look at this way. So this is mostly inheritance related reasoning, and this is mostly implication related. But in any way, it's just a reasoning loop. It's just selecting based on the priority value, deriving tasks. If the derivation has deriving event, I mean, if the event has a higher truth value, it will tend to have a higher priority. If it's, but it cannot exceed, in this system, the child task priority cannot exceed the parent tasks. So here is a very simple budget system, much simpler than in the Java version. It simply multiplies the truth expectation of the result with the parent task priority. That's the new priority to go here. At the same time, the selected event will also go back to the attention buffer, but with a, like in Java Nars, reduced priority. So whenever we use an event, we reduce the priority when it goes in a loop. And whenever we derive an event, when a derived event enters here, its priority is simply the truth expectation times the parent priority. So it's a very simple budgeting. So the priority of this child is lower than the priority of the parent here. And the priority of the items decays over time. That's all it does. And which kinds of inferences it does? Maybe I have something here. Can give you, so for instance, semantic inference would be if S is a M and M is a B, then S is a B. So if Garfield is a cat and a cat is an animal, Garfield is an animal, for instance. It also has abductive and inductive ones here, but then it also has this sensory motor inference which deal with implications, like if it has the first event is a and the second belief sample is a B, then we can, if this one happened before B, if B happened after A, I mean, it can derive an implication. And it can use this implication then in the next inference step if it selects A and it selects this implication, a second belief, it can predict B, for instance. Similar thing, it can do subcalling if it has a G and it has an implication link between concepts. So if it G enters, so if it uses this as a second premise, it can derive A. And here, what's relevant, when there are competing alternatives, it always selects the one which has its precondition already fulfilled the most and which is also the strongest link. So it tries to use the truth expectation to select the candidate which precondition is most fulfilled and the link is most strong. And this operation it will then choose to execute. But this will be explained better on Thursday. This is just very quick way. So it can derive belief events to predict the future, and it can also predict. It can also generate subcores to go back into this queue. So instead of an algorithm which plans ahead or something, we only have this attention buffer. We select first premise from here, then a related one from memory, and the result go back into the attention buffer. It's only this attention loop. And all the examples we have only use this picture. There's nothing else.
So it's not exactly that there is an interruption mechanism. It's more like something that is not interrupted. It's just the continuation is selected over and over, right?
Exactly. Mm-hmm.
Right.
So the interruption is reached by not having things to interrupt in the first place, essentially, because each inference step is just an atomic thing taking a very small amount of time. You don't have the issue to have something you need to interrupt. That's the idea here. So it goes step by step, always selecting what's currently contextually relevant to do some inference. And so if it plans ahead, it's usually, it can be many inference steps which are necessary to find the solution to a goal, or to plan ahead for a certain outcome. So the entire process of planning ahead is reduced to inference steps, which are realized with this always select the most relevant thing. Things to select a belief, infer some other events or sub-cores you can work on. And this repeats and repeats and repeats, and or the prediction behavior you get and sub-coring behavior is just a result of this picture. So I guess at this stage you have followed. Maybe I should look into the chat if I did not miss something relevant. Okay. So we cloned the repository. We changed into the default of the repository, and now we build it. Just build sh. Now it will compile and write some warnings I did not yet eliminate. So now we have the system. And now we can see if it works by simply executing the nar. So simply type /NAR and then press enter. It will run dozens of test cases. And if successful, it will say all tests run successfully. If you wish to run examples now, just pass the corresponding parameter. So so far, I did not really want to bother with any graphical libraries and stuff. So all those examples run in the terminal. So let's just pick an example. So for instance, we have Bong here. So we can simply pass Bong. Some of them don't have a visualization yet, but Bong has a ASCII visualization. I hope it does not flicker too much over the zoom, but let's see. So it does not know how to play it. It just observes some stuff. It sees the bar is on the right. It notices when it executes an operation. Now it sees the bar is on the left, maybe. So it just different things happening, streaming in as events, but it has the goal to hit the bar. It does not yet know what the score means or how to achieve it. But sometimes it hits it, and it sees maybe, hopefully, some temporal relationships to the state of hitting to hit the bar. And so it learns, okay, when the bar is on the right side, maybe I need to invoke right. If it's on the left side, maybe I need to invoke left. And if it already got it, it looks that way. You will see the hits and misses ratio to increase. So the ratio is actually hits divided by hits plus misses. So you will now see this ratio getting closer to 1 if you let it run longer. So it really understood how to reach, how to get the bar to the bed in different circumstances by invoking left and right operations. Of course, we have to make sure this does not only work here, but also in other. We also have a slightly more complex version of Bong, also with slightly different sizes of the bed, just to make sure it's not just luck. Of course, we have also a way to randomize the initial. How can I make it smaller? In this case, I need to make it smaller. So, and here, this is a slightly more complex one because here it needs to invoke a stop operation. because else it will just keep going. If it executes right, it will just keep going. If it executes left, it will just keep going. But there's a stop operator it can use. And as you see, also has learned it very quickly how to do this. This is just one thing, but Bong is for many not too impressive. So maybe we can show something else, something like test chamber. Now test chamber. What you see here is a ASCII visualization of a room, and the room has a door, and the door, so there's a room. The room has a light in it, L0. This one has currently state 0, meaning it's off. Then there is a switch, S2, which, as you can see, is supposed to turn on the light. Then there is a door in the room, it's S1, and this one has a switch to open the door. Currently, the agent is this one, this arrow. It's at position S0. And now I can tell the agent, for instance, I want to show learning by observation. So I will control this thing by myself now. I will say, why is it not showing? Go to S1 is B, go to S0 is 1, so I can press A, B, enter, A, B, enter. And so I just let it walk between S0 and S1. And I could now ask, I could give it the goal that it should be at S1, which is B in this case. And so you see it walked there based on what it has seen before. A similar thing I can do with the door now. I can activate and deactivate this G and H. So I can open and deactivate the switch to open and close the door multiple times. Then I can manually walk back to S0. If I now say the door should be open, it's already a multi-step decision-making experiment, because it has to realize, okay, it's currently at this location. It needs to reach this switch 1 first, and then it has to invoke the activate operation. So if I say door should be open, so it needed 2 inference steps, but it went there and activated the switch 1. So it has already learned how to get to the position of the switch for the door, and it has already learned that the switch to the door opens it. So you can try simple experiments here in this domain. If you spend more time, you can also teach it how to get from here, to open it, to go to switch 2 and to turn on the light. So it will also be able to learn more complex behavior, like go into a room and activate the light in there. This is one example, very basic example. What else can I show? Another example, which is maybe a bit more interesting to some, is a simple robot simulation. The idea here is simply to collect food. There are also wars in the environment, which, of course, if you're stuck, the system needs to turn, and also it needs to learn how to collect food. And here, the vision of the system, it's in bird view, essentially, but the system sees the world from a robot perspective. I will show you here. So it sees the arrow indicates the direction it's looking. It's the red thing here. And now it's looking to the right. Now it's looking into the war. At first, it just invokes motor babbling, trying random operations. Here it sees there's a green object in front of it, another green object left to it. And it doesn't take long for the system to figure out how to collect those green things. And also, you will see it avoiding wars often. So it also just sees what's in front of it. And so it's a one-dimensional retina, one could say. And it has to learn what operation to invoke in what situation. If it sees the green thing on the left side, maybe it should invoke the left operator to make it appear in the middle. And then maybe try the forward operation to drive towards it. And you see it often takes a bit of time, but there were already a few examples where it seems that it got what it should do. Usually it just takes a minute or two. But the idea here is the same. It just receives events. Those events give it information about what it sees. And if there's a bar in front of it or a green object in front, or what's on the left side, what's on the right side, and I think now it got it. So as you see, it collects stuff it sees and tries to avoid the obstacles in the way. But it's, of course, if this is all you want to do, a reinforcement learner is maybe more effective. But point is, it can also do it. So you don't need to go back to reinforcement learning. And what I want to do with this environment is to make it more complex, to add, like in the previous example, to add a door here or maybe a switch at another place. So it has to learn to use the switch in order to get to the other room and so on. This will be the next step to make the environment a bit more interesting. So yes, but it seems to get it. Sometimes it takes a few inference steps where it does nothing. This is just the natural thing which happens with this inference loop. Sometimes it selects items which might not be too relevant. So, and valid reasons, time is already going. So whenever it waits, it's essentially thinking about what to do next, essentially. So it's not like in a reinforcement learning environment where the agent is expected to output an action in every frame. That's not the case here. And also sit back and reason, and when it's ready, it will invoke the next step. That's the idea here.
If you set the default confidence to 1 instead of 0.9, is that going to make any difference, or?
1 would not work because confidence essentially is the total evidence divided by total evidence plus 1. So it essentially confidence 1 would mean it would have infinite amount of evidence for the truth of that statement. So this is a case. So default confidence does not really matter much. It could be 0.9, it could be 0.5. As long as it stays the same over its lifetime, it will work. But it cannot be 1. It just has to be some unit of evidence. So you wanted to add the same evidence for the same observation. And
is that going to make, I mean, is the default confidence is going to make a difference in the truth value of the internal relationships that are being built, relating the inputs and the goal, or?
It's a bit like, mostly it's like currency. For instance, I could scale up all the prices and for all different things by a factor of 10. It would not change the money flow essentially. It's as long as the relationship between the things, like a car should still be, say, 10 times as expensive as a computer on average. As long as the relative measures don't change, I could add a scaling factor to the currency and it would still work if it's happening on a global scale. And here with confidence, it's a bit similar. What really matters is to give it a certain amount of positive evidence for a certain input. And so I just give it a certain amount of positive evidence. And this amount of evidence I give it, I just give it some fixed value, which does not need to change over its lifetime. So each sensory value has a certain amount of evidence when it reports the value. As long as the relative, so important are the relative numbers. Those are really what matters. So if I set a different default truth value while the system is running, if I change it, this can cause issues, of course. But most times, if you just set a certain default confidence at the beginning, this will, and you don't change it, then you're good. It doesn't really depend on any particular default value, as long as it's larger than 0, meaning there's some evidence, and larger than 1, meaning it's less than infinite evidence.
And if, for instance, one of the input, for instance, Ethan is actually provided with some noise, would you benefit by lowering the confidence of that input?
That's a good question. It's one way. For instance, if you have an unreliable sensor, you could make the reliability, use the reliability of the sensor as the confidence. That's good. It will improve it, but only if you can really be sure that this value you use is really reflecting the certain,
right,
how well the sensor performs. Else it's better to just use a default. But if the sensor doesn't always report the right value, the system will learn that the hypothesis it builds based on this sensor pattern will not be reliable either. So it will automatically, if the sensor is not reliable, the hypothesis on top of it will also not be very reliable. So you get it for free to some degree. So it does not need to be
right.
input.
Yeah. I mean, you can view a sensor as never being faulty, basically, because what's faulty is your abstraction of the sensor. What you, right? Okay.
Exactly.
Interesting.
Maybe one more thing I can show is there's also a way to interact with the system directly. There's a shell. With the shell, you can directly use Nars for communication. So you can even introduce higher level terms like Garfield, like the example I mentioned before. Garfield is a cat, and cat is an animal. You will see derivations like Garfield is an animal. If Garfield is a cat and cat is an animal, hence by deduction, Garfield is an animal. And with a lower confidence, you will also get conclusions which are not intuitively read, but this is reflected in the low confidence value. Also, you can simply enter events like A, B. Let's open a new one, else we have intermediate derivations and it's different to interpret the output. We say we have A, and we have some steps later, we have B, and we have C. And you see, it derives certain hypotheses like A leads to B. This is not something the user has started, but the system has simply seen by the events it has experienced. And more important, more interesting, like a sequence belief that A and B together leads to C. And so it forms all those competing hypotheses. So if, for instance, it has A, B, C, A, B, C, A, B, C, then it has an A, but there will be no C, or it has a B alone and there will be no C, then it will get negative evidence for B gets C, and it will get negative evidence for A gets you C. And on the other hand, this pattern will then prevail, because if it happens to be that way, that always C happens after A and B, then it will be this hypothesis, which, even though it will not be the hypothesis of the highest confidence, it will be the hypothesis of the highest proof expectation, because the other hypotheses have negative evidence then. So you can play with different input sequences and see what the system will predict. So for instance, if we enter now A, I would want the system to predict B, right? Right, for instance. You see, this means event. Maybe this one I should have explained earlier. This is simply a meaning event where you also see the occurrence time when it predicts it. So when now I enter the A here, I entered this A after I have shown it ABC a single time. It predicts B with our occurrence time of 10 and a C with our occurrence time of 12. So it has, from this B, has predicted B and C with C happening after B, which is red. So you can use it for sequence predictions. But to show you a more interesting example, I will show you an example of the old version so far, because I'm running out of time. Is there any question here?
Yeah, so it's able to predict the occurrence time, but wouldn't there be some kind of like different possible times? I mean, I didn't have time to like follow everything, but in general, right, you could have C that could occur at time 12, but maybe also at time 11 and at time 13 with different frequencies and confidence, right?
Mm-hmm. That's true.
And so it is going to derive all the possibilities, well, given that the loop of selecting the next inference can go that far, but right.
Mm-hmm. So the key here is for the system to learn the timing between the events. So what's not visualized here, in every implication, there's also implicit timing information. So for instance, we entered this A at occurrence time 1. Then we entered a B at occurrence time 3. And so in this implication, there's some metadata, which is not shown here, which is +2 steps. A leads to B in 2 steps. And so if I now enter A here, which was 8, occurrence time 8, because reasoning system has already done some inference steps, the internal clock has progressed to 8. So now it needs to take into account that there is a difference of 2 here between, oops, what did I press? Okay, we see it here. So A we entered at 8, and B then occurrence time 10. So it took into account the experience timing between the events. So it also, that's also relevant. So for implications, it also learns the expected timing. So for instance, it learns that if you have an energy saving lamp, it will take longer for the outcome to be achieved, for the light to go on, than maybe for LED LED. So it can learn those kinds of relationships.
And so you say that the timing inside the predictive implication is hidden, it's not represented. How is it represented internally, and how do you deal with having different implications with different timings? I mean, the same implication with different internal timings.
Mm-hmm. That's a good question. The idea here is to use what we call temporal projection. So there's a similar issue if you have, for instance, event A, so say a sensory reading of temperature 40, then 10 milliseconds later, you get another 40, then another 40, another 40, then you get suddenly a 0, then a 40 again. What you want is the system to be able to revise events as well, right? So that it can, for instance, so that it can combine the evidence. But the thing is, the occurrence times are different. So how to do this? Similar with implication, you have A implies B with a time difference of say 1 second, and then you have an energy saving lamp, and it takes say 5 seconds between pressing the switch and the light going on. So how do you combine those hypotheses? And the idea here is very simple. We just penalize the confidence based on temporal distance. So if the closer two events are to each other, the more can those evidences to be taken to happen at the same time. While if one happens far apart, then if I penalize the confidence of one based on the distance, it cannot affect the other much anymore because it will already be low. So it's a very simple idea to penalize the confidence based on the temporal distance before revision. That's the idea here. So the higher the temporal distance, the less can the evidence be taken for the other event to be accumulated.
It makes sense. I mean, it certainly intuitively makes sense. I'm wondering, because it is based on some assumptions that seems to be a little bit hidden. I mean, implicit. Do you have like a more explicit, I don't know, mathematical justification for the way the scale, the scale, rather the distance, not the scale, affects the confidence? Or is it more like, you've tuned something and that seems to work, so it's good enough?
That's a good question. It's more intuitive, I would say. It's essentially, I mean, the entire non-axiomatic logic is to some degree based on the intuitive idea that the hypothesis can have positive and negative evidence. And of course, then you can define a ratio like the positive evidence divided by the total, and you get the frequency value, or you can say to map the total evidence to a value between 0 and 1, and you get the confidence value. So it's, I would say, even though there's a formalization, the idea behind the formalization is actually intuitive, and I think that's the right approach. It's questionable. I don't think we can prove. We can say this proof calculus is the only valid proof calculus to deal with uncertainty. I don't think there will ever be such a thing, but we can create some formalization, and which, for instance, makes sense according to some interpretation, like in probability theory, based on probability spaces, and we can formalize our ideas, and we can see how they work for different circumstances. And non-axiomatic logic is designed for the case, for instance, where we don't know the exact form of the probability spaces. So what can we then rely on if we don't have information about the probability spaces? Multiple approaches. We can use statistical estimation techniques to somehow find ways to infer somehow the shape of probability distribution from our data, or we can find another way which doesn't have a direct or intuitive mapping to probability at all. For instance, in probability, I guess there's a similar issue in the open-cock system. You cannot have a global probability distribution because it's computationally expensive to update it, even though it's possible. But you can do something else. You can allow for local probability spaces. But when you do this, how do you decide? How do you take the confidence? In our case, the confidence, I'm not sure if it's also called like this there. It might be called strength or something. But how do you take this measure, this additional measure into account? For instance, let's go to a very simple example. You have a coin and you flip it, and you have 2 times head and 2 times tail. Somehow you don't want this to be the theory that you get head and tail 50%. You don't want this theory to be as strong as, say, when you tried it 400 times instead of 4 times. You want somehow to have the total. You somehow want to take the size of the sample space into account. How many samples did you already take? And this idea is outside of probability. This cannot be, is outside of the axioms of probability theory when you want to take the size of the sample space into account.
Well, yeah. I mean, in OpenCog, it's not exactly outside, but we have a second order probability. So, well, it is outside in the sense that it's a meta distribution, but it remains within the theory of probability.
I'm not sure if remains inside is the right wording, because in the moment where you add additional axioms, you're extending the structure, right? You're not, the truth, the statements you derive, they are not justified only based on probability axioms.
Well, I mean,
there are additional theories you can put on top, like second order probability and something like Dempster-Shafer theory, but they are not, how to say, you cannot prove they are right. You can put some axioms together where you think it makes ultimately intuitive sense. You cannot prove the axioms are right.
Well, yeah, sure. I mean, yes. I mean, yeah. I agree.
Mm-hmm. And it's a bit counterintuitive that null does not at least try to extend the axioms of probability theory, which is, I agree, this is also difficult. Why don't we also use it? And the thing is, let's say, actually, for instance, if the confidence values are very high, ideally we would want it to use probability theory. Because if you look at the formalization of probability theory, you have the limit case. For instance, if you want to work with empirical evidence, you could say amount of heads for the coin case among the total times you throw it. But if you want to say this value is a probability, you actually mean you have tried infinite amount of times, because the ratio is defined as a limit. And so in Nars we don't have it, and I don't think we can justify it. We cannot just treat it as a probability value, because we cannot throw the coin infinite amount of times. So what can we do? And that's a good question. And I'm not saying that the thing null does is the only right one, but I guess there is not much more left than say, let's find some things which make intuitive sense and let's try to formalize them and see what we can make with it. It's difficult.
Right. Yeah, I see the rationale.
Mm-hmm. How much time do we have left?
15 minutes.
Okay. Mm-hmm.
Yes, you're allowed to go over a little bit into the break if it's needed. So.
Oh, okay. Mm-hmm. The difficult thing is really how to deal with uncertainty. This is really a key issue, and because if you cannot prove that the axioms are right, what can you do? And but at least you can define some proof calculus which can work under uncertainty, under certain conditions.
Yeah, I mean, it seems like, well, from some even preliminary experiments with PLN that actually you probably need not just a second order distribution, for instance, but you would need an arbitrary order distribution. I mean, if you really want to be accurate. So, but
and are you currently using second order?
Yeah.
Oh?
Yeah. So that's how confidence is mapped into how the second order distribution is going to look like. So if the confidence is 0, then it depends on the prior. But if you have a Bayesian prior, it means that each probability of the event are going to be equally distributed. It's going to be a uniform distribution. And so if you take, for instance, a coin, if you have no knowledge about this coin, the probability of getting head would be anything between 1 and 0. And as measured as you're going to throw the coin, you're just going to narrow the second order distribution to an actual probability. But of course, as you said, in order to have an actual probability, you need to throw an infinity, of the coin, an infinite amount of times. When you have something which is just a binary, something that has a binary state, and all you have is direct evidence, it works pretty well. But as soon as you start to reason, then first the distribution that we use, which is a beta distribution, which is perfect for a binary event with direct observations. Then when you start to combine reasoning, then the beta distribution is no longer so good. And the more you reason, the less the beta distribution is going to approximate the actual second order distribution. And the thing is, I'm not sure yet, but maybe it's just a lack of resource, but it feels that, at some point you're going to have to approximate the confidence itself. And then, well, if it's an approximation, well, then you have a certain, you need to have a confidence over the confidence. And so then you need a third order and so on. So these are tricky questions. Yeah. Yeah.
Agree. Very, very difficult.
Yeah.
To handle uncertainty properly. And I'm also not sure if it's the final story what we use here, but it's just at least a formalization where we can at least make sure that we don't violate at least the null axioms, so to speak, because the way truth value is defined in Nars, we do not need to assume that we took an infinite amount of samples. So we don't have an assumption we possibly break. So we stay mathematically valid, so to speak, to our axioms to some degree. So to the formalization of the non-axiomatic logic. Which does not imply that it's also the perfect truth calculus overall to deal with uncertainty. Yes, so it's really justified according to this intuitive thing that hypotheses can have evidence evidence which votes for it and evidence which votes against it. And this is really what the system tries to utilize when it makes its decision. It tries to, its decisions, it tries to, for instance, it tries to rely on the most, on the most truthful hypothesis, because often the system might not even know a good solution, but the worst, the best solution is still better than none. So even though it might only have a clue with a low confidence, it might still be better than nothing. And this is, so it can happen like in the beginning of our procedural learning examples. The system only has a very low confidence for the hypothesis, and it will simply, in this implementation, it will simply tend to pick the best, or the hypothesis which has the precondition most fulfilled and which has the strongest implication in terms of truth expectation. So actually, it's a form of deduction, but how this works exactly can be read in the non-axiomatic logic book. So it essentially it wants to always use the hypothesis which, to its own knowledge, is the best one currently available, even though it might be a crappy hypothesis. But how can the system know? Another thing I want to show you, as we have some minutes left, some simple English example. So we have the script called English to Narcisse. It makes it easier for people to interact with the system because it can pass simple sentences to Narcisse essentially. If we call it like this, it will only do the Narcisse translation, the translation. For instance, if I say then it will generate this Narcisse. But in this case, it only acts as the translator, but we can invoke it a bit differently. We can use a Unix pip to say, I want to pipe this output into the Nars shell, which you can do like this. So you launch the English to Narcisse translator and you pipe the output to the shell of Nars. This you can do. So I think it's already ready. So what did I write? A cat is an animal, I think I wrote. And if I say something like Garfield is an animal, they could then ask another thing. If you don't want to see the derivations, you can simply put star volume is 0, then you will not get distracted with derivations. And I could ask the system, is Garfield is an animal, for instance, and it gives this answer. It again translates the question into Narcisse, and it answers in Narcisse. But at least it lets you interact with the system more easily because you can simply write a simple sentence and it will map it to a Narcisse statement. Doesn't make much sense. The dog likes hot potato, but it directly maps it into the corresponding Narcisse statement. You could ask who likes hot it says, for instance, I can ask who likes hot potato, and it says, the dog likes hot potato. At the beginning, the Nars is a bit hard to read, but the language interface is also a way to make it easier to learn to use the system, because you can type something in, and then you can see how it would be represented in Nars. So then you can also have understanding of how you could encode something similar yourself. Like in this case, in this case, we have an inheritance statement. So the dog is something, this inheritance. The dog is a special case of something which likes a hot potato, essentially. This parenthesis indicates a property which it extracted from the adjective in front of the noun. So what this does is very shallow semantic parsing. It does not really try to find a meaning for the terms or for the words in terms of meaning or grounding in terms of meaning. It does only translate it, and the system has to relate it to the other events, and this is what gives those terms actual meaning. So we do not try to have a deep semantic labeler, which something like a semantic raw labeler. We don't do this. We simply translate it into terms, and the meaning of the terms has to be learned by the system itself, based on the context, based on the other events which are happening. And we have, for instance, some story understanding examples.
I'm sorry. What difference is that going to make to the inference system that hot is an adjective that it's between brackets as opposed to, say, potato? Because both are concepts. I mean, I guess that. I mean, they have a conjunction, but why? Like, yeah.
That's a good question. This is like a set. So I could also have multiple properties, like dog likes hot, yummy potato, something like that. So for instance, as an example, I could also say a cat. It doesn't have a meaning for a cat. What is a cat even? Let's use dog, because we use dog here. I could say dog is meowing, barking, barking, annoying, for instance. So you can have multiple elements in this bracket. So it's like a...
It's like a conjunction?
Oh, yes, exactly.
Right.
Intentional intersection, or actually intentional set.
Oh.
Exactly. So you can have something like a dog is barking and annoying.
It has to do with intentional knowledge.
Exactly. So those are properties, essentially, barking and annoying. So I could ask, yes.
But I mean, why is that different? Why is that different from potato? Because I mean, potato is also a concept. Can be as abstract as hot, depending on the environment, right? Well, I mean.
I see what you mean. The difference is also to distinguish the thing from the thing having the property. Like you can think of color as a concept. For instance, you can say red is a color, red, for instance. But at the same time, you can also express that something has a color, like dim. Let's just call it colored. Let's just use the intentional set. So I could say red is a color, but at the same time I can say dim has the property to be red. The difference is, imagine if this one would be missing. It could infer that dim is a color, But that's not the case. You want to distinguish the concept of the color red from something having the property of this, the property this concept represents. This is the basic idea.
Okay, that sounds very interesting. Okay.
And this is also interesting from a natural language perspective. Actually, what I found is that many, at least simpler natural language maps, often maps in very natural Nars statements, like here, dog likes hot potato. You could almost read it from left to right. It has a very natural representation. And so we hope that we can soon do more on natural language. So far, it was not our main priority, because at least for me, always sensory motor contingencies were the main thing. How to learn from event streams, how to learn to reach certain outcomes you want to achieve, how to plan ahead multiple steps, even though you don't use an explicit algorithm, and so on. But here, the language domain also, I think there are a lot of low-hanging fruits which we should explore, because to some degree, at least English, I'm not sure if it works for every language that well, but most English has a quite natural encoding in Nars, which is something to explore further, I guess.
Patrick, I have a question, if I may.
Oh, yes, sure.
I understand that this is quite experimental and not really a product yet, this natural language thing, but I'm intrigued by it because you're approaching it from a very I think practical and interesting perspective. The way I like to think of it, and correct me if you disagree, but it's kind of like saying, okay, we're going to give Nars caveman language properties. You can grunt and you can point, and you can talk about things here and now, sort of, but maybe not really complex things. Now, the reason that cavemen talk, or if you're in a foreign country and you try to ask questions where you're not very familiar with the language, is sort of a comparable thing. The reason that it works is that a lot of knowledge is shared with respect to the context. So there's some reasoning that happens. They couldn't be asking about some ancient philosopher, because they're standing here and they're talking to me and they seem to be going somewhere, kind of, if you're asking for directions. And so my question, if I can get to it, it is sort of about, have you thought about how Nars might be able to do that? I started to, just to explain, I started to think about like wondering whether this natural language interface, if it's so simple, if it's really brittle, because then it's not really that useful actually even for a newcomer, because then subtleties in how you phrase things, even if it's valid natural language, might not work for Nars. But if Nars had this sort of caveman ability to think, okay, here's the context, and so let me use reasoning to figure out like what is the most likely thing that this could be about, etc., then that would be actually very useful. So I guess my question then is, have you thought about that, and is that sort of how you're approaching this, or where are you on that, in that line of thought?
Well, I'm actually very close to this line of thought. For me, for instance, many people in AI try to solve letting the machine understand very complex sentences. But I would already be very happy if I could just tell a robot something similar, something simple like, bring me the newspaper. Something with 4 words maybe. So if maybe the robot at first doesn't understand newspaper or some other word, I want to have a system which is able to ground those words incrementally based on what it experiences. So that, for instance, the caveman dog you mentioned, so that things like this becomes possible. I don't want the system to speak perfect English or something like that. For me, it would already be very impressive if it, like a child in early development, if it can acquire the meaning of individual words and associate them or relate them to something they experience or to something they have experienced around them. So in the sense, it's also close to this event processing paradigm. You just throw in events, and some events of them come from your auditory sensor and correspond to certain words. And you want the system to be able to associate those words in a multimodal way with other things which are ongoing. And this is really what I find most interesting. I don't think, I'm not very interested in having a system speak or understand perfect English. I think that's a very long road, but I would already be happy if it could understand the meaning of a few words and relate this meaning to what it sees and to what it does, and so that the meaning or the grounding issue of words goes simply away by the relationships the system creates in itself with other things it has seen, with other things it has heard, with other things it observes to be happening. And so I'm actually very close to this philosophy that let's start with simple language. And
that's excellent. Yeah, that's sort of language in the service of intelligence rather than intelligence in service of language.
Exactly. Mm-hmm. And I'm personally, for instance, I don't like to introduce much complexity in this system. I want to see how far can you get by keeping things simple and see, for instance, even when this system does planning, for instance, I can show a quite interesting example.
Patrick, I have to interrupt you.
Oh, okay.
Let's move all this discussion to the afternoon because we are supposed to start at 1:30 for the workshop. Okay, now it's already too long, I guess, for everybody. Let's take a break and resume all this discussion at 1:30. How about that?
Sounds good.
Peter, what should we do for this channel? We just leave it here, or we need to shut it down and restart it. I have no idea, but anyway, let's resume it once.
Right, but we can just connect anytime. We're back.
Oh, yes. Then see you later and have a good break.
All right, so we'll see you back in about 20 minutes.
Wonderful.
Okay, well, thank you very much, Patrick. That was very interesting.
Thank you. You're welcome.
Yeah, thank you. It was good.
All right, so we will now be resuming the conference. Christine, are you here?
I am. Hi.
Yes. Hi, you can kick it off.
Okay. Good to see you all, and thanks for inviting me. It's been really fun so far. Now, I have a big screen here on my side, and I'm going to be looking at my slides over here. And let me see if I can share. Yes. That looks good. Can you see my screen?
Yes.
Yes.
Good. Okay. So I just to verify, I have about 30 minutes, right?
A bit or not? Let me check real quick.
Well, I did plan on that anyway. So if we have more time, we can talk about it. But if we have less time, I'm in trouble.
Oh boy. Well, let's see. I think trying to keep it down to 30, and if you go over, we'll forgive you for it.
All right, great. So let's not waste any more time. So you've seen the title, I assume, and that's probably why some of you are here. So here's an overview of the things and roughly the order I'm going to be talking about these. We're going to start talking about intelligence and some background assumptions. Then we'll get to the heart of my talk, which is causal relations, reasoning, and learning versus seed programming. So just to start off with the main top level goal here, we're all here probably because we want to create a general machine intelligence. And the way I think about this, and a lot of my collaborators, is that an agent is the composition of a controller and the body which acts as the interface to its world or its task environment, in which it achieves complex goals and where there's plenty of novelty. This is the relation between the knowledge that the agent has or the controller and the environment itself. So we assume complex task environments. We're not really interested in toy environments. And that makes the challenge harder, but more fun. In our target task environments, we are talking about the existence of large numbers of variables with all sorts of relations and transformation functions that create complex spatiotemporal patterns. And again, novelty is common. That is, things that the controller or the agent has not experienced before. So we kind of have to start here at the top level to talk about what kinds of theories we have so far. Because any learner, any system that's trying to figure things out, to learn something new, has to deal, comes into a world with a lot of, there are a lot of sides to the learning that we know from both human experience and in the animal kingdom, that that involve these 5 things that we have put here in my PhD student has put into a pentagon, which makes it really nice to draw diagrams like this. Now, so we have a learner that is doing a task in some sort of a task environment. And to get good at this task, it needs training. It may or may not be able to use the guidance of a teacher. But in order to know what a learner knows, we test it. And there's all sorts of relationships between these. To have a proper theory for doing AI, we would actually want a theory for all these corners. We would want a proper learning theory, a proper task theory, a proper training theory, a teaching theory, and a testing theory, and they should all be within the same conceptual space, sharing background assumptions. So what do we have so far? Well, we have the non-axiomatic reasoning theory by Pei Wang, which is really, in my opinion, the only coherent, broad theory of learning. Anything else is either half-baked or has huge gaping holes. Now, just don't take my word for it. You can bring up some questions and comments, and hopefully we'll get to talk about that. On the task side, myself and my colleagues have started to try to build a task theory from a fairly fundamental level, but I will put a very small, these are not relatively appropriate. I just want you to see the green mark here. So someone's working on this, and as far as I know, with this approach we are taking, we're feeling quite alone, although I'm sure we're not all completely alone. On the testing side, do we have any theory? Not really. No, we have a bunch of ideas. Wozniak's coffee test, the toy box problem, Piaget MacGyver rule. You know, the list is very long. IQ tests, etc. But there's no really any theory behind it. So I will put a question mark there, and I will put a question mark on the others as well. You know, really, to get proper grounding for AI, we will need to fill all of these theories up. Now, there is a really good definition of intelligence, and if you haven't read Pei Wang's paper from late last year on the definition of AI, I strongly urge you to read it. It's brilliant. In short, this is the compact version adaptation with insufficient knowledge and resources. Rather than going into detail on that, and I'm assuming, actually, I'm guessing, and I know for a fact many of you have already read that stuff backwards and forwards. I will replace that with my own favorite way of saying that same thing for the moment, figuring out how to get new stuff done. So if you were ever confused about Pei's theory, that's exactly what it is. This is what it means. Figuring out how to get new stuff done. Figuring out new stuff, figuring out new, it basically means something's missing. You don't have everything. You don't know everything, which is the assumption of insufficient knowledge and resources. It's new because you haven't done it before, or certainly not exactly the same way. So that's that part. Now, get stuff done, and this is really speaks to the heart of my short presentation today. To get stuff done, you need to make something happen. And if you have any preconceived ideas of what that stuff is supposed to be, you already have an assumption of the existence of causal relations. Because even if you know exactly what you want to do, if you don't have the slightest clue or even the possibility of knowing how to get that done, if you don't have some building blocks that allow you to start, you won't get them done. In any large task environment, the combinatorics completely preclude a random search or even systematic exhaustive search. But why non-axiomatic reasoning? If there are some people here who are new to Pei's writings and the work on Nars by the Nars team, you might be wondering, you know, what's this big deal about non-axiomatic reasoning? So non-axiomatic comes from the fact that there are no givens. When you do new stuff, you cannot possibly know if it will work. So how can anyone act in such a world? Well, that's just stay put, and we'll get to that. Reasoning. Why do we need reasoning? Can't we just do it in some other way? Well, frankly, Not at the moment, because there are no known solutions other than reasoning for dealing with giant, complex environments. If you have a world that is even partially rule-oriented or rule-governed, then your only chance of getting anything done in a semi-efficient way is through reasoning. It's the only way. So how does that proceed? Well, and this is, now we're getting closer to the heart of my talk. We do that via hypothesis generation and testing. Modeling the world from experience and then checking how well we did. So learning means modeling, and there's no way around that. An agent controller is a modeler. If you have an environment made up of variables, transformation functions, relations, and initial state, the controller here implements a process that models experience. So what is involved with this loop? So you got a sensor and you got an actuator. The sensor can measure some things and the actuator can affect some things. So this is the loop. Conant and Ashby's good regulator theorem states that every good controller of a system must capture a model of that system, or as they say, it must be a model of that system. What does a good controller mean here? Well, actually, it's a very useful concept. A good controller actually achieves its goals. And I will remind you that it's not really a controller if it has no goals. Then it's more like an art piece. So some of the requirements on the controller are listed here. On-the-job learning, on-the-job modeling, on-the-job verification of the quality and the usefulness of its knowledge. Through reasoning, because this is really the only way that we know so far, the most efficient way to do anything with information where you don't have time to check everything. Which of course, as you know, if you've done any machine learning, is very, very often the case, in fact, in modern so-called machine learners. So learning, we're throwing in one more thing here, goal seeking. So it's adaptation through experience in the service of goals. And we're getting a bit closer to what I mean by the term seed. And we'll get to that in a minute. So here we end up through this reasoning path with the question, why do we need to talk about causal relations? Well, it's very simple, actually, when you think about it. If you want to get stuff done, if you want the light to come on in the room, or if you want to go to the store and buy some bread, you need to know some things about the world you're in. You need to know how things hang together. Not everything, just a few things, the few things that are relevant for that goal. Okay, in your world, you have some variables and patterns that are manipulatable at some times and not others. And you have some variables and patterns that you can observe and at certain times and not others. And this is what you need to relate. This is what you need to connect in ways that are useful for your purposes. So this is essentially what we call causal relations. That's what it means. And frankly, we don't need to go to put on our philosopher's hat and talk about whether causal relations really exist and whether there can be a true cause for something, etc. Because intelligence is a practical solution to practical problems. So all we need is to talk about practical things. And that's also why I share the goal of, I think, most of you, which is that we want to make machines that actually work. we don't want to do just designs on paper as so-called theoretical ideas that are not implementable. I'm gonna throw some hypotheses at you now. These are, yeah, I should be halfway through. I cannot slow down for a second, so bear with me. So I'm going to throw some hypotheses at you. I'm not necessarily going to answer these thoroughly in this presentation, but bear with me. I've done a lot of thinking about these, and this is what I've come up with so far on the subject. Knowledge acquisition in a general intelligence needs to be able to identify relevant relations. It's not just causal. What I'm arguing is that causal relations cannot be ignored. They absolutely are a necessity. They're necessary, but not sufficient, okay? This is done by creating models of observed relations, comparing subsets of knowledge and percepts in the form of models through reasoning, evaluating the relevance of any acquired knowledge at any point in time, bringing it to bear on the situation and apply it. And if you want to learn incrementally and cumulatively, such that as you go and as you do more stuff, you learn more stuff, then you have to know causal relations. This is an absolute necessity. And these are bootstrapped via correlations, but I will not go into that today. So, causation. Let me talk a little bit about causation. Again, to get anything done, you must know some useful relations of the form A, then B. Something particular results in something else particular. Otherwise, you can't really predict. But you don't want that to be particulars. You know, if I lift this yellow glass, you know, the yellow glass will be lifted. You know, or if I grab the yellow glass and I lift my arm, the yellow glass will lift with it. That's a very particular thing. You don't want to just be that particular. You also want to have general knowledge. So that means you have to generate useful general relations from your experience. So that's another reason why we need reasoning. We need induction to create these rules. Now, doing something is not the same as observing. And I could observe a robot lifting this glass and assume that the robot is thirsty, but my assumption then would be wrong. I could, and the only way to know that that was wrong would be maybe to withhold water from that robot for about a week, which is, or what is it, 20 days, which is the absolute maximum for any living organism to be without water. And then noticing that the robot does not die, assuming its charge is still there, I would disprove that model of the world. Now, forgive me for that silly example. I just made it up on the spot. So, causal relational models. This is this is the name I'm giving these information structures that hold information about causal relations. Now, again, they're based on experience. We've said that several times. They capture relations between observed patterns, and they model relations between variables and patterns and elements in any environment. So they are of the form generally, you know, if you have alpha at time t1, then you will have beta at time t1 plus some delta, because a cause cannot happen after an effect. That is not a true causal relation. So the process of creating this knowledge involves coming up with a bunch of ideas for how things might be related in the world, and then testing them to evaluate their usefulness. If I have this crazy notion that grasping a glass and then lifting my arm, other things being equal, the glass will be lifted. I can test that. In fact, it needs to be falsifiable for me to be sure about it. It needs to be such that if I do that and the glass does not lift, I already know just by observing my action, the effect of my action, that that model is wrong. The more accurately these models help a controller achieve goals, the more useful they are. So that's a very simple bookkeeping. And I just already jumped the gun on this one. So the models must be falsifiable. They must be in a form like scientific hypotheses in a comparative experiment. You need to formulate, so Karl Popper was right. You need to be able to formulate things in a way that can be falsified. Otherwise, you cannot be sure that they're correct at all. Or take that back, that they are useful. Now, that doesn't mean we can walk around and just create hypotheses about everything. You know, yes, there might be a lot of subliminal, subconscious processes that we are not aware of consciously that are going on, but it's clearly bounded. There's no way that we're doing all hypotheses possible for about everything we know. So there must be some way to bound this. And the way you bound it is by practical concerns. Again, intelligence is a practical solution to practical problems. So co-temporal, co-spatial is more important than anything else. That's how you stay alive, anyway. So let me just run through real quickly here how you can, what the process is for creating such useful causal relations. Well, let's assume that the world only consists of alpha, beta, and gamma. We're going to say that this is an actual, well, it doesn't matter if it's an actual phenomenon or not. Let's just say that this is a paper and pencil example. I just told you, this is the world, this is how it actually is implemented. It could be a simulation I wrote and run on my laptop. And I know the code, I wrote the code. So that's, I can tell you, this is truly how it is, okay? Now I bring an agent in and I say, observe this thing. The agent sees a lot of, events, it sees an alpha, and then at the same time, it sees a beta and a gamma, and then it notices there's a beta again, and lo and behold, there's an alpha and a gamma at the same time, or roughly at the same time. And so let's just say that this agent is a bit sloppy and it doesn't quite pay attention to the timing of events. It comes up with a set of models about the relationship between these phenomena in its world. Whenever I see an alpha, I also see a beta. Whenever I see an alpha, I also see a gamma. Whenever I see a gamma, I also see a beta, and vice versa. 4 models. Are they useful? Hell yeah. It can use any of these models to predict what's going to happen if it sees any of these events. Okay. It sees a gamma. It says, oh, I bet you'll have an alpha and a beta too. Yeah, lo and behold, that's true. So any one of these models will predict this world. But if the agent wants to do something in this world, it wants to stop seeing beta. It wants to never see beta again, ever. Well, it could try to use model 3, try to get rid of gamma and see if beta goes with it. Well, no, it doesn't. Even if it managed somehow to get rid of gamma, that is not how the causal relations work. So it would have to, so this is a way to test its models, essentially, how useful they are. Not just useful for prediction, but for getting things done. So in order to get rid of beta, you have to get rid of alpha, because that's how the world is rigged. Now, this actually means that CRMs are bidirectional. And that's a very useful property, because when you read them from left to right, they mean that A may cause B. When you read them backwards, it tells you that that B may have been caused by A. So if you see a B, you can predict that maybe A was there to cause it. Now, we are familiar with this from AI, because from philosophy and AI, because reading them forward is deduction, and reading them backwards is abduction. And deduction is very useful for prediction. And abduction is exactly what we do when we plan. In order to get to the goal, I have to do this first. In order to do that first, I have to do and so on. So that's reading backwards. Now, someone asked me a while back, okay, so that's fair enough for rules. Okay, so the CRMs are rules, but what about history? What about events, etc.? You know, how can I talk about events when I have rules? Well, the way you do that is you instantiate the CRMs and you timestamp them. So you have a general rule that says whenever I see some A, I will see also some B because that's a causal relation. So you instantiate that model and you bind the variables and you bind it temporally. Oh, yesterday I saw an A and lo and behold, of course, B happened as well. And so instantiated CRMs can be put in your memory as a history trace. So this is what it is in fact. It's like a comparative empirical experiment. You come up with some hypotheses, you test them. When they start to predict well, you perceive the result, and you use reasoning to weed out the models that only predict but do not allow you to act, because those are no good for planning. And so try telling that to the central bank of many countries in the world, because they seem to have all of this jumbled up and they don't understand what empirical comparative experiments mean. But that's another completely different story. Now, so here are the six last slides in my talk. Let's see if I can do under a minute for each one. Maybe not quite. So here is what happens when you learn. You have an agent in the world. Some things are novel, and it sees a phenomenon. So this is a phenomenon in the world. It can only perceive certain aspects of the phenomenon because some things are observable at certain times and not others. And the things that it's not familiar with, it creates hypotheses about. And as it learns and creates hypotheses and creates models using this hypothesis to, generate and test methods, basically, its familiar aspects of the world grows, and it may or may not change the buffer of hypotheses. Some would say, as you grow older, you don't have to create as many hypotheses if you don't want to. So and that's why maybe it's harder to teach an old dog new tricks. But be that as it may, that's essentially how it goes. And so the models, because they can be manipulated by reasoning, allow you to grow this in a very compact, sensible way, systematic way. Now, what about seed programming? Well, I contend, and I submit to you, that this is simply a special case of novelty learning, as I've outlined it, where you start off with some sort of a seed. This is what you're born with. So you're born with, something in your repertoire of action and perception, and this helps you generate hypotheses in the beginning. But by and large, it's exactly the same process as you go on. It's just that as you grow more knowledgeable, you use less and less of what you were born with, and more of what you have already learned, new stuff. So learning, in this view, is the systematic creation of knowledge from experience. You're all familiar with that and probably agree with me on that. It's bootstrapped from existing knowledge, whether that's a seed or not, using reasoning to model causal relations and more. And seed programmed learning is a special case of learning, bootstrapped from a seed. So the autonomy here comes from the ability to bootstrap causal modeling. It's the only way that you can grow. If you don't learn any causal relations, you cannot possibly get better at learning. but you are assuming that you always have insufficient knowledge because you're always learning new things. Remember, figuring out how to get new stuff done using a combination of whatever reasoning method makes sense, ampliative reasoning, and systematic testing, recursively using it in subsequent actions and knowledge acquisition. So, so our second to last slide, generality comes from the ability to generalize causal models. Using ampliative reasoning again, especially induction and analogy. Oh, this is sort of like that. Let me see if that works. And test it out by doing stuff in the world through falsifiable actions via abduction and deduction, mostly. In summary, causal knowledge is fundamental for practical intelligence. And I submit to you, what other kind of intelligence is there than practical intelligence? For any agent that must figure out how to do new stuff, causal knowledge is critical. So is reasoning, and this is how you enable autonomy and generality. Thank you.
Thank you very much for this very insightful talk. I hope everybody enjoyed it. Anyone has any quick questions?
I saw there were two questions in the chat. The first one is, Kristen mentioned gore seeking. Where do those gores come from?
Say that again?
He said you mentioned gore seeking, and where do those gores come from?
Goals.
Where they come from?
Yes. In the beginning of the talk, you talked about goal-seeking behavior, and I was just wondering where these goals come from.
Yeah. So if you are an agent that's born into a world and you have no built-in goals, you will not learn anything. You will have to have inside of you some sort of a bootstrapping mechanism or drive that essentially bootstraps the learning behavior. Otherwise, you will not learn anything. So whatever you call it, there needs to be a mechanism that gets the learning, the knowledge acquisition process started. Now, for an AI, we could easily foresee giving a learner anything from a very simplistic goal or drive like that to highly complex, survival skills, etc. If you look at nature, you see how the difference between some animals and humans is quite stark. At birth, a human baby will die if there's no caretaker, whereas this is not true for many animal species. And possibly, or I could be wrong on this, but possibly that's because our learning skills are targeting more general aspects of the world than any other animal species. So in other words, you have to, if you want full, let's hypothesize that there's such a thing as full autonomy. And if we think of full autonomy as basically just being born into the world and from then on just doing whatever you need to do, there will have to be some sort of a survival goal there. Otherwise, a complex, dangerous world will just kill you. So that's not fun to talk about. So let's limit ourselves to the agents that are born with a learning bootstrapping method or mechanism built in. So they start to learn. Now, how much do they need to learn depends on a lot of factors. If it's an AI, presumably you built it for a purpose, you would want to put into it, if you're going to send it into outer space, there may come a time when you can't really send any useful information to it. And all you can do is just receive its transmissions. And you would want that system to be fairly autonomous. You might want to give it full autonomy, but you don't want it to mess with its top level drive, because that is an undefined state. That is sort of like, when people do silly things with their own lives, like taking it. But so that is yeah, that's all I'll have on that for now. I can talk forever.
Thank you. That was a good explanation. The other question I had was, it seems that the words hypothesis and model are very similar in your mind. Is there any distinction that you have between them?
Oh yeah. You can have all sorts of models of anything for any purpose. And the purpose of a model is kind of inherent in its form. If it's a useful model, it has to reflect its purpose somehow, like an architect's paper model of a skyscraper. Its purpose is not to test, how strong it is. It's not. You're not going to put some weights on it and see if it holds up. That's not the purpose of a paper model. The purpose of a paper model is for people to look at it. So a model always has a particular or several different kinds of purposes that it serves. A hypothesis, a model that's a hypothesis that is in the role of a hypothesis, is a model that is being considered for its usefulness. Just like a hypothesis in a comparative experiment.
All right, thank you very much. Just checking, is Antonio Cella here?
Yes, I'm here, thank you.
Yes, all right. So now we will be listening to Understanding Scenes with Nars.
Okay.
Antonio Cella.
Thank you.
Yes, I'll share my screen. Maybe Chris, you should...
Should work.
Okay. Okay, can you see my screen now?
Yes.
Okay, so thank you. So, good afternoon, everyone, and thank you all. Thank you, Patrick and guys, for inviting me. I will present. I will outline a research topic that we are investigating, and it is a collaboration between University of Palermo and Temple University. And in my talk, I will briefly outline some of the ideas we are considering in this kind of collaboration, while in the subsequent talk, my colleague Francesco Lanza will outline more, will enter more in detail in the implementation aspects of these collaborations. So my talk is more high level, let's say. The general topic of the general scope of our collaboration is really in put in real rough words to embody Nars. So to have some sort of embodied version of Nars in a robot. A main aspect of this problem is, for example, to understanding scenes. So a robot interact with people. There is a scene which is made up by people, made up by object, and the robot should be able to really understand the scene. So should try to understand the situation. A main point in this kind of research is the role of the focus of attention. We live thanks to the focus of attention, of course. So we want to understand scenes by implementing a kind of focus of attention which should be driven by expectation. And another scope, another goal of our collaboration, as I said before, is to embody Nars in a sensory motor perception system. The general goals of this project is to, as I said before, to allow a robot to navigate inside a scene, to generate expectation about perceived scene, to implement some predictive planning techniques, and the robot should also be able to imagine the effect of the interaction with object, possibly before performing any kind of action. So those are the aims and scope of the project, of the collaboration between my laboratory and the group of Temple University. Okay, according to the principle, to the AI-KR principle mentioned before, even by Chris, the role of focus of attention is obviously an important one. In fact, a finite agent has limited resource, and so an agent cannot carry out a one-shot exhaustive analysis of the data coming out from the scene within reasonable time. So there are time constraints, there are memory constraints, and so on. Because, of course, some collected data and the relationship between data are more relevant than others. So it would be a complete waste of time of computational resources to detect useless details. So in order to allow a robot to understand scene, it is necessary to implement some kind of sequential scanning that acts as a kind of focus of attention. We take some inspiration from the biological focus of attention, but up to a point, I can say. From the psychological literature, a focus of attention is generally described in terms of a spotlight beam that scans the visual field. Very simply, a very simple view of seeing the focus of attention is a kind of a beam. So objects falling inside the spot are processed. There is some computational resource allocated to the objects falling inside the spots, while the other objects are ignored. This is a very simple view, of course, of focus of attention, because subsequent theories consider the fact that there is a space-based attention, in the sense that attention may select even empty region of a scene, or the focus of attention might select a region containing object of interest. And there are, of course, some kinds of hybrid theories of the focus of attention, which are, according to these hybrid theories, the focus of attention is partly based on space, partly space-based and partly object-based. Anyway, all the theories of focus of attention take into account the fact that the focus of attention is typically a serial process. It's a process that is based on seriality and selects only a few items at a time, and it moves from one object to another. I may remind many computational model of the focus of attention. The most famous one is mostly the saliency map by Etienne Koch. Okay, in our view, the role of the focus of attention is driven by expectation. So we imagine a system, a Nars system that generates expectations, and the focus of attention then is driven by this kind of expectation. So the focus of attention may select relevant aspects of a scene, which may be represented by a set of low-level assumptions, and the expectations are generated, and in turn, these expectations look for specific aspects of the scene, and then assertions are added to the Nars knowledge base. Of course, not all true assertions are generated, but also the assertions that are judged to be relevant based on the attentive processes. And in these aspects, the ideas of all the ideas related to the certainty, related to the frequency and to the priority, which are inside Nars, are very useful because it is able to, all these mechanisms are able to weight the usefulness of assumption, not the fact that assumptions are true or not, but the fact if the true assertions are useful or not in this general framework. So, for example, when the vision system of our robot, we use one of the robots that we employ is the Pepper. When the vision system of the Pepper is useful at recognizing a single object, which may be a component of a more complex object, let's consider, for example, the hammer, and the focus of attention looks for a cylinder, which may be the handle of the hammer, then there is an expectation is generated for an hammer, and then the focus of attention looks for the other part of an hammer, the hammer head, for example. A similar example may be a chair, for example, or a person. So if the focus of attention look for an object which may be a leg of a chair, then it looks for it generates an expectation of a possible chair, and then it looks for the other aspects or the other parts of the other part of the chair. So in this case, there is some casual beginning, in the sense that a big object, for example, captures the focus of attention, and the focus of attention starts by generating expectation, and this expectation generation is useful to drive the focus of attention, so the search for the other useful objects. So, for example, considering a network router. So we work in a computer laboratory, so we have many network routers. So, for example, initially the system, the robot centers its focus of attention on a pattern of pixels, which corresponds to a set of low-level assertion in Nars, or a pattern of pixels representing, for example, the body of a router, so a box. This simple, the fact that this is a simple object, which is a box, may be consistent with the fact that this box may be the body of a router. And then the focus of attention, we generate expectation of a router, and then we scan the neighborhood of the object in order to find a couple, for example, of thin antennas, of thin cylinders, which are the antennas. And in this sense, the system eventually generates the recognition of a router. And the fact that there is a box, there are two cylinders, which has the role of the body of the router, and two cylinders, which have the role of antennas, in some sense, alter the frequency, the expectation of the fact that there is a router. So once the system generates an expectation, this expectation is satisfied. In some sense, this fact has a role in the frequency, in the certainty of the whole system. So this is a very simple example. The very simple example I mentioned. There is a box. The box may generate the expectation of a possible router, but the router is made up by something which is a box and two antennas. So there is a generation of an expectation, something which may be a cylinder, which has the role of the right antenna. The right antenna is found. Then the robot looks for a left antenna, and so on. And then a router is recognized in terms of a box made up by two parts which are related to some with some geometric constraint, of course. In this sense, the system recognized a complex object in terms of expectation generated. Of course, the generation of expectation might be driven by the, for example, by the context. We take into account two kind of sources for the of expectation. So where do expectation came from? We take into account two general sources. One source is what we call a kind of linguistic expectation, in the sense that somewhere in the database, in the knowledge base of the robot, there is a description, a kind of dictionary. There is a description of a router as something which is made up by a tick box and a couple of thin cylinders with some characteristics and some relationship. And then, because a router is defined in this way, so a kind of prior knowledge, let's say, something like this. And so in this case, a router is described in the knowledge base of the robot as a kind of in this way, and then as soon as an object is recognized, which is a part of a router, then the system will look for the other parts of the router. And in this way, you may also consider, for example, more general description as a context, as I said before. For example, the context of an hardware store or the context of a robotics laboratory, which you may expect to find objects related to a robot and so on and so forth. And another source of expectation might be the associative expectations, in the fact that suppose that the Nars learned that when there is a router, there is also a cable which is plugged into the router, or together with a router there is a hammer, because in the laboratories, in our laboratory, there is a router and there is also a hammer, then the robot is the robot learn to associate this object. It is more a kind of associative expectation. So it's not related to the general description of a router or general description of an hammer, that a hammer is close to a router or a fork or whatever. But normally, during the life of the robot, let's say, the robot looks for learn to the association of these two objects. Let us consider the fact that this problem may be related to the hot problem of bias, which is a really hot problem in every kind of learning system, the problem of bias in training sets. Anyway, the border between these two kinds of expectation is not crisp in some sense. So let's say that the linguistic expectations are mostly related with a priori knowledge, with the prior knowledge of the robot, while the associative expectations are the knowledge learned by the robot during the life of the robot itself. Okay. The level of certainty in Nars are important in this scenario, because only the most relevant expectations are taken into account, and this is in some sense may be related with the frequency in Nars. And moreover, when an expectation is satisfied, the certainty associated with the object and the part may be revised, in the sense that this may be related to confidence, for example. So in the sense that if I really confirm the fact that there is a router, then the full confidence on the object and is changed in some sense. So the fact that there is a box, there are two cylinders into situation, into position, and so on and so forth. So the level of certainty, how Nars treat the concept is important, because it is the role of relevance, the role of importance of the entities to be considered with respect to other entities is important in this kind of scenario. So, as I mentioned before, a robot is a kind of embodied focus of attention. So in our experiments, we use a paper robot and a now robot. So the focus of attention is driven not only by considering a camera moving and so on and so forth, but a physical object, which is a physical robot moving into the scene. So the focus of attention is related to the movement, to the body motion, of the robot. So, for example, when the robot finds a router, it may physically move its own body and its own head to search, for example, for a cable attached to it. And so the robot will explore the scene, is inside the scene, and will explore the scenes driven by the focus of attention controlled by the system. If in the case that expectations are not satisfied, for example, in the case that the robot finds a router which one antenna only, or a router with a detached table, for example, the robot might alert a supervisor or whatever. So we have to consider also the fact that the expectation might be satisfied, but expectation might not be satisfied. In this case, the robot should take into account the possibility to consider alternate routes and so on and whatever. The important thing is that the movement of the robot might be, so the generation of expectation allows the robot to imagine or to simulate the possibility of interaction before the robot really move into the environment. So the robot may imagine and so may reason and anticipate future interaction with the object in the environment. So the interesting part is that generating expectation, if you generate expectation, you may reason about this expectation. In this sense, you may also generate a random expectation, and even physically impossible expectation. You may reason about, like in case of dreams, for example, which you generate expectation, which may be physically impossible in some sense. So the robot might expect to fly, for example. So in the case that there is an obstacle, the robot may generate the expectation on avoiding the obstacle by flying, which is something that happens during dreams, for example. So the robot might not only generate expectation and reason about expectations, but the robot might also generate physically impossible expectations, and the robot might also reason about impossible expectation. But this impossible expectation may have a role in the knowledge base of the system. This is a huge strange topic of the role of dreams in our cognition, and maybe there are some counterpart in artificial cognition. Anyway, an important part of this general project is to investigate the role of imagination, the role of anticipation, and even, let's say, the role of, dreaming. So imagine random interaction, physical interaction, not physical interaction, so on. So predictive planning. Predictive planning is planning by imagination. So the robot, in order to reach a goal, may generate expectations on possible interaction with the environment and choose observing the desired input and choosing the right way, the right path, by taking into account the reasoning about the generated expectation. So the predictive planning is observing the desired input, considering the goal, considering the environment, and to generate expectations that take into account even adversarial conditions. So, for example, the lack of knowledge, the lack of appropriate model, conflicting goal, redundant goal, and so on. So predictive planning is planning driven by imagination. So, for example, a trivial example, in the case of a missing antenna, the robot can generate a plan to search for another antenna, Pick up a new antenna and mount it on the root. So in the case of predictive planning, the robot may imagine may generate a goal of searching for a new may generate a new goal. So search for another antenna in the environment and to pick up the new antenna on the root. For example, in the case of a simple case of block words, the robot may imagine an higher tower of blocks, the good old blocks word. The robot may imagine a tower of blocks made up for 4 blocks, and then he may imagine the fact that the robot should pick up the red block and complete the tower. In the case, the focus of attention is dreaming by the search of a new box, because the robot imagined the possibility to put another block to the block tower. Going further, we may imagine the possibility of considering dynamic scenes. So the generation of expectation may not only be related with objects, so for the fact that there is an object and you can complete the object, as in the case of a chair, as in the case of a block tower or whatever, but also considering the action of the people in a scene. So for example, if a person is grasping an object, maybe the robot may recognize the action of grasping, and then the robot, for example, may change its own position to get the object grasped by the other person, for example. Or the self-monitoring. So the robot may imagine and may recognize the action performed by its own body, like if the robot looks at itself from the outside, for example. So if the robot is able to recognize the action from simple actions from another person, he may also recognize and reason about its own action. And finally, a really intriguing goal concerns the concept of affordance. So do not recognize an object because of the shape, but recognize the object by the action to be performed on the object itself. Like, for example, the case of a chair is typical. So you recognize a chair because it's something that you can sit on. So it's difficult to define the concept of chair. But a chair may be considered by taking into account the actions which are related with the object. So a further investigation in brief, might take into account the typical problem of recognizing not only objects, but recognizing action performed by external people, by other people, by the external environment external to the robot, but even to the robot itself. Okay, I stop here, and thank you for your focus of attention,
Awesome, thank you very much. Sorry for the background noise if you hear any. Okay. So does anyone else have any questions? All right, I think then Francisco Lanza, are you in the chat right now?
Yes, I'm here.
Hi, welcome. Now, then we can move on to your talk.
Okay.
All right, let's go.
Do you see the screen? Not yet.
Not yet.
Yeah. Okay. Now?
Something is happening. Yes, we can see it now.
Thank you. So.
Good luck.
So, good afternoon. I am Francesco Lanza. I am a PhD student at the University of Palermo. Today I will talk about learning plots with Nars. Before starting my presentation, let me introduce myself and my research interest and my research field. since I started my my PhD, I was fascinated by human-robot interaction and the robot too, clearly. Specifically, I was fascinated by cooperation and collaboration of human and robot at every level. In this talk, I will discuss a method based on Nars for letting robot and agents create plans at runtime. Clearly, for increasing and enhancing the quality of human-robot interaction, and specifically in the teaming domain, we should endow robots or in general intelligent agents with the ability to plan at runtime. This led us to define novel skills and to reproduce human skills such as self-adaptation and imagination. Clearly, these skills are not simple to realize, but if we want to move a step toward this direction, we should think how to reproduce it, and clearly a step toward is letting agents to plan and learning plan at runtime. But we will see what means and what I intend for learning plan at runtime. Following our previous work, clearly, on multi-agent architecture for human-robot teaming interaction, we will discuss a system able to learn plan using Nars. This system merged the qualities and the characteristics of BDI agents with the logic underpinning the non-axiomatic reasoning system. And we will see why. In this slide, it's reproduced an outline, very simple outline of the talk of today. In the first part of the talk, I will describe the instrument and the logic that conducted me and the collaboration with Patrick and the Temple University in general to produce this kind of work. In the second part, there is the description of the work, so how to compose, how to write plans, and how to let the agent writing these plans, and so learning plans with Nars. I say that when I started my PhD, I was fascinated by human-robot teaming interaction specifically. And clearly, before to start to develop a system, human-robot interaction system, software system that let robot interact with human in the proper way, I started studying actually the human-robot interaction system that clearly was developed during this time. And I try to find which points are mandatory to build a human-robot interaction system. After studying these systems, I focused on the implementation part. So I focused on which instrument, which tools is good for implementing a human-robot interaction system. I'm not focusing on now human-robot interaction impact on humans, but I'm focused more on how to build a proper human-robot interaction system that is able to cooperate and collaborate with others. So I extract some points that in some sense are relevant for my software architecture. And I thought about that if I work with someone, clearly, so if I am in a team, the team member has to know the overall goal of the team, clearly to work together, the team move toward to reach a specific goal. A team member on a knowledge base that contains facts and concepts about the world. What this means? This means that me and the rest of the team has to share our knowledge. We should talk with the same language, and we should give the same meaning to the same concept to understand what we should do. A team member is also aware of the surrounding environment. I should know, or at least I should be able to understand what are in the surrounding environment. A team member is to be able to communicate with other teammates. Clearly, for letting communication, collaboration, cooperation between human and robot, they should speak the same language. They should interact and using vocal or other kind of languages that are common for the human and for the robot. The team member has also to be able to delegate or to adopt actions or tasks by other teammates. It's clear because let's try to imagine that I am a robot and my teammate that is a human delegate me some tasks. The human has to know which limitation, which constraints I have, ethical constraints, but also physical constraints. In the same sense, I am a robot, and if I have to delegate a task or an action to a human, I should know how it is, its physical limitation, ethical limitation too, and everything that clearly it's relevant for reaching the target, for executing the task. A team member so has to be autonomous in decision making, to be proactive and satisfy the overall goal. This means that the team member has to be exactly proactive in the sense that it should take decision without asking everything if it's right or if not. It should be so aware of itself, and so it should show self-consciousness abilities, but also theory of mind abilities, because it should be aware about abilities, limitation, and behavior of the teammates. So this is important for building a software architecture that, in some sense, is able to realize a human-robot interaction software architecture. In general, this is a standard scenario in human-robot interaction. When certainly a robot that has to collaborate with a human use its abilities to cooperate and collaborate for reaching goal. We can see the cloud. When inside the cloud there is a kind of simulation of the world. This is how to realize a kind of imagination. We want to endow the robot with this facility, this ability to imagine what happens in the world. And in some sense, this should let the robot also to try to find to understand how the world will evolve during the time. But I talked about multi-agent architecture, software architecture, and so on. But how I can realize a software architecture that is able to implement a natural software system. And that led me to define all of the points that I showed before in the slide. Studying and analyzing the agent-oriented software engineering, I see that the multi-agent paradigm is clearly and certainly one of the most proper methodology, and it suits with everything that I defined. But what is a multi-agent system, and so the multi-agent paradigm what involved? A multi-agent system is a form of machine-to-machine communication. It enables different type of AI system to communicate with others. We can consider it as a consequence, a direct consequence of the agent-based system. And according with the definition that we give for a multi-agent system, it enables agents to interact and exchanging relevant information for producing behavior that are not only processed by a single evaluation. What I mean? I mean that if an agent-based system, so an agent could communicate with other agents and let communication between AI system, and an ABS system is also implements communication with agents implementing a set of rules and constraints. It implements a kind of communication that is not directly. So, agent-based system that is able to communicate with other agents, but it shares results, not methods and how to reach the results. This simple change into the paradigm basically change completely the framework, and this change completely how the agent work. This is a simple agent that clearly sense the environment, produce some action, and this will act on the environment, performing operation and modifying it. Clearly, this is a loop, and each time the agent percept, reason, and act on the environment. Which is different with a multi-agent system. A multi-agent system is different because we have the environment that it presents a problem to multi-agent system, and the system interface of our multi-agent system will distribute this problem to all agents deployed into the multi-agent architecture, and all learning AI systems that are into the multi-agent application are able to communicate with others, basically, and try to find altogether a solution that best fit the problem. So we can compare an agent-based model with a multi-agent system, and we could say that a multi-agent system is an evolution of the agent-based model, and it implements everything that is that could provide a better solution respect an agent-based system. It is decentralized, lets interconnectivity, are autonomous, robust, reliable, efficient. So we use this paradigm to implement our software architecture. But there are several types of framework that implements multi-agent system, which I can use to develop. Basically, we moved our attention to the JSON framework. JSON is a multi-agent framework based on Jade platform. Jade is another framework that let developers create multi-agent application. Specifically, JSON. The difference with Jade basically is that we can define agents that employ the BDI paradigm. Clearly, the BDI best fit with our concept of human-robot interaction, because each agent inside the multi-agent framework follow this kind of model, and so all agents inside the multi-agent system move toward this model, and they exploit goal, desire, intention for reaching clearly try to reach the solution and try to accomplish the overall goal. So JSON use the agent speak as a formalist, so as a language for implementing and the logic that underpins the agent reasoning system. JSON is written in Java and use classes for rendering plans, agent architecture, belief base, message, whatever. But what are inside an agent in JSON? This is the reasoning cycle that is developed is deployed into an agent, an JSON agent, and it starts, as we can see from our perception, to produce an action applying clearly the reasoning process that here is figured. We can see that we have beliefs defined after the block, the perception block. These beliefs are handled and events are generated, and after that, a process, a unifying process, will select a plan that best fit with current perception for produce an action or a message through an intention that is clearly executed. Which is the model, how the model is built. This is an UML diagram of the agent framework. The JSON framework is open source framework, and we can customize it, and we can use it, and we can extend it as we want. Basically, in this UML diagram are figured all classes relevant for implementing and for extending the JSON framework as we want. The agent implements clearly all functionalities, all methods that are relevant for the agent, like so just select message, select event, select option, that if you look inside the reasoning cycle are the action that led, are the function that led to choice which intention should be selected to be executed, and at the end that act into the environment. And we have also the age arc class, the agent arc class, that contains methods for acting and perceive the environment. We have also other classes, such as the belief base or the plan library, that we can customize and we can build and we can extend as we want. So now we will talk about the how to learn plan with Nars. The main ingredients that we need to know to work with to produce this kind of method are beliefs, plans, and reasoning system. So basically, beliefs are information that the agent has about the world. Decide are all the possible states of affairs that the agent might like to accomplish. Intention are the states of affairs that the agent has decided to work toward. Okay, perfect. Generally, belief in programming language based on logic are represented as a collection of literals. But if we want, we can also define a different type of structure that contain the belief base, and we can use as belief base, database, a text, a simple file, simple text file, or everything. Decides, what are desired? Having a decider does not imply that an agent acts upon it. So potentially, a design may be not accomplished never during the agent life, but it's a potential influencer of the agent's action. Sometimes some designs could not be never reached during the lifetime, as I said, and also could collide with others. Intention may be goals that are delegated to the agent or may result for considering option. So what are intention basically are the way how to act to reach the goal. Okay, so what is a plan? And now Nars could create a plan using agent speak, because we said that to program agent, we need to know agent speak language, and clearly an agent programmer has to define a plan library that represents the reasoning system that underpins the programming, the logic of the programming that I'm writing for letting agent operating into the multi-agent architecture. So I mean, the plan uses the first order logic. It is composed by of two parts: the head of the plan and the tail of the plan. The head is characterized by two other parts: the triggering event and the context, and the body that contains other subplans, internal actions, communication actions, belief-based revision actions. What are these? We start from the triggering event. The triggering event tells the agent which are the specific events that trigger that plan. So I mean, when an agent see a specific event is raised up, so it knows that this is the plan that is to be launched, that is to be executed. So once the event is triggered, the plan is executed if preconditions are satisfied. These preconditions, we will see that are into the context. So when a plan is triggered by an event, this means that the plan is relevant with the event. So high confidence. Pay attention to this term, high confidence, because this term is at the base to create plan with Nars. This concept is at the base because Nars will exploit this kind of high confidence for producing plan, but also for retracting plan. Context. What is the context? The context is the last element that match with the head of plan. It represents all precondition that has to be exist for executing the plan. Clearly, dynamic environment and changing contexts are complicated to deal with. Clearly, for facing this problem, an agent programmer generally write alternative plans. But you know that it's impossible to predict all possible plans. And sometimes the agent programmer has to write some recovery plan that, for example, put the robot in a safe mode. Clearly, what means this during an interaction with a human? This means that the robot has to stop its execution, and so the interaction is not so an interaction, no? Because the robot stopped to work, and the human that is cooperating with the robot see a robot that is stopped. So this is not good, because a human expects that the robot try to find a solution for accomplishing the task, for reaching the goal. Okay, so for learning new plans, Nars will use the alternative plans to manipulate them and trying to find a possible solution. Nars so will take in consideration these plans, so all plans that the agent programmer put into the plan library, and it will try to transform and manipulate them for letting agent learn a new one. Clearly, the context of a plan is used for checking the current situation to apply the plan. And this means that Nars has to take also in account these preconditions. Preconditions are important to create a proper plan and that they could be applied into the domain. The body. What is the body of a plan? The body of a plan is the easiest part of the plan to understand because it represents the set of action, the set of other plans, sub-plans, activities, messages, whatever the agent has to perform for reaching the goal. It is a generic, it is known also with the word formula, and each formula in the body does not produce necessarily n effectors. Should be, for example, a check of some engine into the robots. The body is the ultimate relevant part of the plan. And this is what this is the difference. When I wrote several plans, clearly, generally they change for precondition, but also for the body, because with the body I write the receipt, a kind of a receipt that I will respect, that the robot has to perform for reaching a solution. So Nars, when has to write a new plan, has to think about the triggering event, but also precondition and the set of actions or formula that has to put all together for realizing a new plan. And this kind of formula, the body, should be has to respect the precondition that Nars has selected, because Nars cannot write a plan that where the body doesn't respect the precondition. So it's a very complex system, and such a very complex system we should understand, and we should try to find a solution that fits with everything basically. So now I show the Nars-based method for composing plan during agent execution. So this is the agent speak control cycle. We see the reasoning cycle of a generic JSON agent. And we see the JSON control cycle. So if we change the point of view and we focus on the goal addition relation, so it means that we focus on reaching a goal, the JSON agent works in this way. It tries to find in its plan library an applicable plan. If a plan is found, it continues its execution, pushing the plan into the intention queue, processes the intention, and if everything goes well, it's fine. The agent achieved the goal, otherwise it failed. But what's up if the agent does not find a proper plan? Clearly it failed directly. So the agent is stopped basically. And this is not good, we said. So we have to modify this JSON control cycle, because we want that that the agent try to find a solution and try to continue its life cycle, producing some action that clearly are relevant for the domain. How we can do that? We can do that exploiting the characteristic of the JSON framework that are called recovery plan. So JSON let agent programmer to define recovery plan, but it's always the agent programmer that has to write the logic of this recovery plan. It's not the agent itself that try to find the solution. Generally, in a recovery plan, we can find something that could handle the error. It's a kind of exception handler, if you want to see in this way. But clearly, it's not sufficient for a nature I domain. So we exploiting another characteristic of the JSON framework that are the internal actions. We, through internal action and through recovery plan, extend the standard JSON control cycle, including another important characteristic for the JSON agent. That is, the internal action to invoke Nars. What means that? Learning JSON is not able to implement a method for revising its knowledge base and its plan library without clearly intelligent support. It's not able, JSON, to find an alternative plan through composition processes of its plan library and clearly or exploiting its knowledge. For implementing these, we need an external support. We put inside the JSON agent the external support, and this external support is Nars. Nars provided the needed support. So this is the Nars module appeared from looking from an external point of view. This is how it works. The Nars module is deployed into the architecture, and it is called invoking an internal action for the agent. So from a programming point of view, the JSON agent programmer has not to know nothing about the Nars and Narcisse. Has only to, when he found inside the code a critical section, he could write a recovery plan where the body of this recovery plan is only invoke Nars. So it's like to say, I don't know how to handle this situation. I will try to give this control to Nars, and if Nars is able to find a solution, it will give back and will push the plan into the plan library of the agent, and the agent will produce other actions that clearly aren't defined at the same time. So Nars take into account goal, beliefs, and plan library, convert the term, the agent speak term in Narcisse term, invoke the Nars planner. If it will face clearly no plan not found and the agent is informed, otherwise it reconvert the Narcisse term into an agent speak, create a plan, and push into the plan library the new plan. So the agent now has produced autonomously and without any external support, I mean human support, a new plan. So you learn something that no one has told it before. This means extending the control cycle in this way. So if we have to accomplish a goal and we don't find a proper plan that fits with this goal, we will launch Nars reasoning system, and after that, if a plan is generated, we push into the plan library that will be pushed into intention. Once we process this intention, what's up? It will process it, and we will inform Nars about the success or the failure. What means that? It means that Nars, informed by the successful of the plan or failure of the plan, could change its truth value, or better, the truth value assigned to the new plan. And once these clearly fall below a threshold, the plan is retracted from the plan library. So what this means? This means that if Nars is able to add a plan into the plan library, and this plan seems to be a valid solution that could be applied into the domain for pushing the objective and reaching so the goal. In the case of this plan is not good and it will continue to fail, the truth value of this plan below a predefined threshold that we measured experimentally during our execution, but we are working to make these threshold dynamic. If this plan, if this threshold fall below, it will retract because Nars will inform the agent that, sorry agent, but the plan that I generated for you, it's not valid because it fails, and so it's not valid. It's better to retract this plan. What it means that Nars is also able to delete from the current plan library all plans that are not relevant for the scenario that is facing. So we can manipulate, we can perform operations that are compliant with the domain and with the context without losing time, without waste time with the plans that are not relevant for the scope of the mission of the team and so on. So the agent learns what is good and what not for the current context through its direct experience. And in this sense, the agent learn new plan at runtime. For future work, we are integrating this system with an advanced simulator for letting agent and robot test their plans before executing them. We realized that the simulator based on a real engine for letting robot imagining its action, so to reproduce the action inside its mind and see before it performs the action to the real world if this action is valid or not. This, in some sense, should endow the robot with an imagination skill. We are conducting other study, and we are realizing other models. Also, Patrick said before, we are realizing a ROS module for letting the usage of Nars in with every robot, basically supported by the robotic operating system, clearly, and we are also investigating the possibility to realize a complete multi-agent framework that works completely with Nars, because Nars has all characteristics that support HRI in the large sense. I think that that's all. Thank you for your attention, and I hope that you enjoyed this talk.
Thank you so much. It was a very great talk. Let's see. Does anybody have any questions?
Yeah.
Okay. So then, thank you again. We will move on then to the next talk. Hugo Latopi, are you here?
Yes, can you hear me okay?
Yes, we can hear you great. All right.
Maybe
AGI in the wild is your topic for today. You can kick it out.
Sounds good. Hi, everyone. So we're going to talk today about some work that we've been doing for a few years with many of you, AGI at Cisco. Some of it will be applied. As we get started, I want to make sure that Oz is going to help me present some of this. Oz, are you there?
Yes.
Excellent. And you guys can see my screen, I hope?
Yes.
Can you see my screen?
Yeah.
Everybody? Yeah, okay. Okay, so when I say AGI in the wild, I literally mean I was in South Africa installing systems last year, which was great. I think I gave this update last year. We have systems that we are focused on open conservation, trying to apply more intelligence, video cameras, infrared sensors, a lot of other sensors, trying to prevent poaching of elephants and pangolins and rhinos and all of that. So that's actually out there working. This is kind of a high-level slide. I'm not going to dive into that too much, but we were doing some video analytics. The smart city work that we're doing right now, is it big enough for you guys, or do I need to go full screen? We'll just leave it. I guess you guys can see the screen fine.
Yeah.
Go ahead.
It's large enough, I think.
Sorry, Patrick, what did you say?
No, I think it's large enough. It's fun.
Okay, good. Thank you. So the smart city work that we started last year, Tony Lofthouse, Patrick was very much involved with this. The basic idea here was we had a video analytics that, using our own multimodal deep learning models. We wanted to add Nars to that, and the task at hand that we applied was, can the system automatically calibrate itself, learn what its field of view is, learn where the roads are, the sidewalks, all of that, and we wrote a paper on that. So Patrick was the primary author, so there's a paper out on that. This is an ongoing project right now, and it's actually in Australia. It's growing, and we're hoping to kind of re-engage. And my plan, so my personal plan is, and I do have approval, is to open source much of the video analytics that we're doing, open source the framework, open source how we're interfacing to Nars and all of that, so that we can get more of a ecosystem, more research interest. That would also, help us to kind of further develop social good applications. But in Australia, for example, what they're doing is they have complex intersection environments where you have trains, you have bicycles, you have pedestrians, as well as the vehicles. So there's a lot of safety concerns, and we want to apply just more adaptive, intelligent analytics that could start to understand when potentially you have an emergence of dangerous conditions. So that's a great use of reasoning in that space. One thing that we do, significant research with universities. This is some examples of what we're doing. Ben Gertzel, Pei Wang, Kristen, and hopefully more. I also have some things that are more focused on just the deep learning side, security related, and data fusion, multimodal scene understanding. It's quite interesting to see how you can build these models now with deep learning where you can, if it's multimodal, which means like you have sound and video, for example, you can generate one modality from the other. And the nice thing about one thing I've been pushing multimodal deep learning for quite some time is that you have the ability to, for one modality to implicitly label the other. So you don't have to worry about, they're unsupervised techniques in a sense, but not really, because one modality, so you have correlation and temporal correlation occurring across them. So that's a little bit of background on some of the things we've been doing. Some of the papers that we've done, some great work by Alexei Popov and Ben's team on re-identification across cameras when you're doing that kind of tracking. And there's more online. If you look online, and like I said, expect a lot more open source coming from us in this space. This is the paper I mentioned that Patrick was the primary author, but some good results there, and ongoing project there. And I know Patrick has done some great work with OpenNARS for applications, which we will be incorporating and updating that software probably in the coming weeks, to incorporate that. So as I get into like what we're currently doing, that's kind of more historical. I mean, and it is ongoing, but our current focus kind of evolved from that. I just want to give a little bit of about some of the biases, I guess, that we have, where we're coming from, so you understand. I built one of the first commercial semantic networks at a company, unfortunately, called Metadata. They tried to actually protect that back in the 1980s, but that really impacted me about focusing, about how do you represent knowledge, what is knowledge, and so even though I'm very interested in reasoning and other sorts of graph processing, and Korsivsky has a huge influence on me, so you're going to see that in what we're talking about here. Keep that in mind. Also, I like basically applying AI and these academic principles into the biggest real world systems that I can. So I have like 6 billion chips in the world that have been serialized and have my security technology on there. I have a lot of technology deployed everywhere from TV to mobile devices. So I like to kind of get my tech out there because I feel it's a great way to learn from just, actually, yeah, so it's one thing to basically have an AI that could maybe, identify one object in with reasoning. Can you identify it when you have a cluster of 1,000 or 2,000 objects that you got to figure out in real time? It's a very good learning opportunity for me and that's why impact is kind of a big deal. What we're going to talk about. A lot of bias, I have to say, OpenCog, OpenNARS, ERA. I really think those are huge parts of the solution. I don't see them as, and I don't want to make anyone angry, but I think that I see tons of synergies in lots of the components. I think everybody with the AIKR principle would agree. Cognitive synergy conceptually is excellent. I think that we're actually starting to see that in some of what we're doing. So this is some of the stuff, some of the background of what we're getting into. And for lack of a better name, the thing we're going to talk about where we're kind of getting some new results, kind of combining OpenNARS and ERA, we're calling it, excuse me, DFRE, Meta Model Deep Fusion Reasoning Engine. It's just a historical thing. It's not a real name. We're going to rename that. It's just internal, but DFRE is the name of it. So we have a meta model that incorporates this idea of how do you represent knowledge, right? So we'll get into that in a second. So last year, I presented this slide, and it kind of, at that point, I was still kind of more on the neurosymbolic approach. How do you combine machine learning, deep learning which has a lot of great things about it, nice pattern recognition capabilities. Obviously, a lot of problems as well. It's not going to get you to AGI. Symbolic AI, how do you mix it? So it was a kind of a neurosymbolic architecture, which we're still doing, with a middle layer, which Peter guarded for, is kind of hypothesized, and I felt was quite important as well, which was some mechanism, kind of a metric space, where you have you can go from discrete values in the knowledge graph. Red is apples are red, and red. Last time I saw red was episodic memory. There was blood, or whatever that is. To going to a sort of an analogical with a metric space, right? Where it's like, how red is it, right? Or how do these shapes evolve, and that kind of stuff. And so we started to kind of come up with the concept of or implement this geometric conceptual space and various ideas. So one of the things how this has evolved as we apply this to networking and other more challenging problems is maintaining the structure of knowledge is crucial, right? And so what is knowledge? We're writing a paper that is just being approved right now, but we're going to cover some of the concepts here. A few of the things really that Korsivsky talked about, back in the 30s are quite crucial in our view, and I think more people are kind of raising this again, which is the importance of distinction, individuation. This is not that. To me, to us, the framework of knowledge basically is anti-symmetric relations. So how does that work? So our meta model basically is very rigorous about these anti-symmetric relations and how you deal with that. You have levels of abstraction, which I think are crucial as well, which we've implemented. Korsivsky talked about that. He has a structural differential in his Science and Sanity book that you can, kind of see what he did there. Ours is a little bit different. And then also similarity, right? So then you have the symmetric relation. So how do you, at a high level, what we're saying is you have intension, extension, levels of abstraction, and you have to maintain the structure of knowledge, right? If you have any process that works on your net general knowledge base that is not aware of all these different things and doesn't have a way of really keeping them straight, then what we found is that you get what we call knowledge scrambling instead of building knowledge. But knowledge scrambling can be quite good. If you need creativity, there's a place for that. But there's a key place for just maintaining structure. Where this really comes from is quite interesting. It was some research, basically. Right now, when you think about intelligence, you obviously think about neuronal capabilities, neurons, and modeling those things. But a lot of the work that we're doing here basically goes even more primitive intelligence, right? So if you have any kind of cell, the cytoplasm, it exhibits tropic responses, right? Even plants, they like heliotropic, they'll go towards the light, geotropic, they go towards, they understand where gravity is, and they work in that sense. Cells exhibit the same thing. How does that work? I mean, they're exhibiting intelligence. They don't even have any, obviously they don't have neurons, they're single-celled organisms. So how does that work? And it turns out that a lot of what is happening could, the boundary between the animate and the inanimate, life and non-life, seems to be kind of quite an interesting place where you get some intelligent behaviors. And that's kind of what they call electrocolloidal or colloidal chemistry. Wolfgang Pauli kind of hypothesized that. He actually wrote a book on this, and he said this is kind of where a lot of the intelligence is happening. And interestingly, in colloidal chemistry, that maintains this knowledge structure. It'll have levels of abstraction. It has the knowledge. It has this individuation, symmetric, anti-symmetric. That'll even happen without a cell. It'll happen in just colloids. But anyways, that's a bit of background on what's happening there. Now, how would we apply this? These are some of the, kind of one summary slide. I don't know, Oz, you want to jump in and say something about this one?
Well, actually, this shows the capabilities that we can use with the FRE. We have we collect basically the sub-symbolic data from different sources. Could be retail, smart cities, or networking. And currently, we're actually working on networking and time series analysis with this architecture. And the set of services provides an agent the capability to ingest various data sources with different data modalities. This could be structured text. This could be programs, audio, and any sort of data. and the symbolic data is constructed. And the agent constantly creates the abstraction of this physical world at different layers. And by using expert knowledge, reasons on this data and constantly creates the knowledge graph. So we keep everything in the system as a graph, not only the knowledge, but also the reasoning steps and the results as well.
So it might be worth saying a word here on tools. I didn't quite, highlight that in the prior slide that, we're leveraging, we're not trying to reinvent the wheel. If we have AGI blocks, which we leverage, we'll use those. But also there are some other major blocks that kind of stand out here. The graphs, for example, like the graph, what we're finding that the highest performance graph database out there that from all the testing that we could do, it's in memory, so it's hyper fast and it's open source. It's the Redis basically Redis has grown into like an ecosystem. I don't think everyone's even aware of it. You think of it as a tag value database, but it's so much more than that. It does every kind of pub sub graph database. It has time series specialization support. It has AI built into for TensorFlow, PyTorch. It's just a fantastic platform for anyone that actually wants to build real working applied AGI. It's it's fantastic. So we use that quite a bit. But also, since we're doing a lot of graph analysis, I would probably give a shout out to Cytoscape as well, for the visualization from the bioinformatics and genomics communities that have been the guys doing the most work hardcore on large graphs, so Cytoscape is out there, open source, it's great. And probably one last shout out to NetworkX, which is kind of our internal, we use a lot of that for a lot of the internal graph processing that we do, which is not bad. There's a Python version of that you might want to look at if you want to get into this. So we mentioned some of the data sources. We can also do a lot of out of band, because we have this meta model, you could pretty much put everything into it, whether it's video or audio or, anything, so we have a lot of ability to social media data. Some of the applications we're looking at, this geofence concept, right, where, you look at all of the social media and other sensor data coming from a particular area as kind of another, geo-localized source, which gives you all sorts of cool things that you could do with that. And the time series I would just mention here has kind of become our de facto conceptual space. And we can turn anything into a time series. I don't know how much, if you have any background with time series, you'll know that you can actually turn shapes into time series and vice versa. You could pretty much DNA into a time series. And one other thing I would just say, is for time series, basically Iman, who invented matrix profile, says that it's like the world-changing technology for time series, and he's kind of a modest guy. I'm going to have to say that it's a very great building block, that matrix profile. So if you have any time series or anything that you could convert into time series, highly recommend that you take a look at matrix profile. So it's, we just use all these things, and we are adding our own elements as well. Anything here, Oz, that you want to say?
Yeah, this is one of the use cases we worked on, actually. So the agent, in that use case, agent is batch processing more than 7,000 time series. So time series, as Hugo said, is became our basis data, input data, and the system actually creates symbolic information based on that, like the structural breaks, anomalies, discords, and the spikes, square waves, etc. The idea is to create a symbolic language-like representation of the time series, and then reason on that. So this time series actually was based on Yang models, which is data representation language. It was also another source of information for the agent, not only the time series itself, but also we used information coming from Yang models. Hugo will show in other slides. I think it's on slide 6.
And right now we're interfacing. So this is, you actually get about 8,000 time series from a single box in a network, for example. So we're looking at getting a processing right now. We're interfacing now about 1 million time series live for like one reasonably sized environment, right? So, and we have a way of doing that, and you know, it's not unlike what Antonio was talking about, where you need to have a focus of attention, and that's where AGI comes in. Otherwise, the combinatorial explosion issues are really not manageable. Go for it, Oz.
Yeah, as Hugo said, the main one of the main communication between the services and the agent is provided by Redis. So Redis time series holds the data. For example, a Redis AI holds a trained MLDL models, and you can use the GPU to quickly forecast what's going to happen, for example, for a time series, and also Redis itself to communication among agents, because one of the demo is going to be about collaborative agents collaborating on a task. So
I'm guessing we're not going to have time for that one. We'll do one demo maybe. Yeah, but yep. Okay. One other shout out here, just because I see it, is that the Grafana is fantastic for time series. And what we've added to it is that you can have an AGI generated dashboards, which I know doesn't sound like a big deal. So what if AGI can generate dashboards? But if you're dynamically looking at, you know, millions or, you know, large amount of data, and then based on some semantic principle or semantic quality, you can say, okay, here are some dynamically generated dashboards. I mean, it's a world changer, really. So I have never seen anybody do anything like that, but it's very, very useful. Yeah, so here, yeah, go ahead.
Here, as I mentioned before, for example, agent works on the Yang model names and creates an extra information on top of time series, and this gives us a chance to you know, analyze time series in groups. For example, after detecting events across all the time series, we can say focus on event 1, and then as you can see, we have the structures preserved between the time series. So this allows us also to study the causality among the time series.
And what's really cool is that we can not only dynamically generate dashboards, but we dynamically visualize the evolution of the knowledge graph as the system is learning, which is very useful, actually. It turns out that you think it's just like, okay, what does this mean? But it actually tells you areas that you require more structure, you know, or that require some kind of connectivity or some creativity to, you know. So we have now, in a sense, an objective function about trying to build, you know, knowledge structures that have certain qualities where, you know, the visualization just helps you kind of understand what you have. This one is just, it's an initial attempt at some graph summarization. You know, there's you know, I think that Ben is really the master at different ways of doing this, but there's some new things out there that we found that are very useful. KGIST is a good grammar-based, you know, graph summarization and compression. And I would also basically say VOG is kind of old, the vocabulary base, but there's a lot of interest right now because the graph, but this is really driven more by people that actually have large knowledge graphs or large graphs, which is going to be more the bioinformatics guys at this point. But there's a lot of good work there that probably translates into AGI as well. So we're going to talk about one use case. I think really this is a bit of just a scaled out version of what Antonio already showed you. So what we're going to show here is that we built a system that the initial task was, okay, you know, in retail, you want to have a camera, just point it anywhere, automatically learn where the shelves are, where the products are, train itself on the products, you know, do rectification of the image, and then just start giving you inventory, right? Fully automatic. We built that. That was in November. Right after we built that, then we got the direction to say, well, no, you probably want to focus on networking. So this never really went anywhere. It might become something later on, but at the moment, we'll show you briefly what it does. But the interesting thing here is that we learned a few things when we went from applying Nars, say, where you have rules that give you one object, so suddenly you have thousands of objects, and we'll show you some how that worked. And that changed the dynamic a lot, and it really kind of forced us to have focus of attention, a mechanism for, you know, maybe like a semantic decomposition of the problem in some way that you can handle these issues. So all of that kind of built up to where we are now with the DFRE meta model. Do you want to say anything on this slide, Boz?
Yeah, so like the row bounding boxes, when you create a world based on just boxes, which and then convert this into some semantic, like visual semantic representation of the world, like containment information, which box is on the left of what other box, etc. You end up with thousands of premises. When we convert this to Narcisse, for example, you end up in thousands of premises, but which required, as Hugo said, the employment of focus of attention mechanism.
And something like a semantic decomposition of the problem, right? Which just kind of came out of the DFRE meta model.
Yep, exactly.
So go ahead if you want to say some more, dive into the some of this.
With a very simple ontology of just 4 statement rules, and we were able to process the knowledge graph and achieve very close to 100% success rate in categorizing what's a product, what's a shelf, what is not either of them.
I'm going to say that we were 100%. I mean, it was just most runs would be 100%, but there's some non-determinism, you know, that I believe it was in Nars, but we never actually verified that, and that caused it to occasionally go slightly less than 100%. But you're being very tough on the system there, but okay, that's all right.
Okay, 100% success rate. Yeah. The good thing about one thing also that we should mention, that the nature of the symbolic data processing and the seeing the world in boxes in this case introduces noise, like counter evidence. So Nars was great to deal with that, taking into the noise consideration and the counter evidences into consideration, and given the focus of attention, a time to process all the information, we were able to get the 100% success rate, identifying what's a shelf, what's a product, and what's not either of them.
So how much time do we have left? I think we're at the 12:30 point. Should we wrap it up, or do we have a few more minutes? We could show a little bit more.
No, you can actually show a little bit more. The max you can add to it is 30 minutes.
All right, but so is that 5 more minutes?
No, I said the max that you can add to it is 30 minutes.
Oh, wow. Okay. All right, so this is good. No. Well, let me bring up, let me see if I could, so I'm not a Zoom expert here, but I want to bring up a video to show you guys. How does that work? Stop the share, I guess. Okay. And then share. Now, this is going to be a very boring video, but it's interesting for discussion, because something something startling happened here. So I'm just going to play this. So it's a video of this retail system, and initially it's going to be kind of operating on the, and I'll jump around on this, but it should start showing something here in a second. So first it did the rectification. The camera angle was at an angle. Here's kind of all the raw output from some of and you can see there's a lot of false positives, happening here. And then we ran this is about 10 times slower. We have a real-time translator that goes from the Nars log file into a graph and bidirectional. So we typically interface external systems with this bidirectional mechanism that allows us to have a graph representation, in both ways. This one we slowed it down just for visualization here, but it runs quite fast. But as it runs, you can see it's not really making any mistakes, right? And it'll do the whole image. That's fine. And to be honest, we didn't do anything to train specifically for this. I mean, the rectification logic was parameter free. We tried it in a lot of cases. There was nothing specific about this. And to get 100% was a bit unusual. So what we decided to do was say, okay, well, let's give it a different image that's a little bit unexpected. Like that, here this was built on a concept of shelves. So I wanted to say, okay, let's take an image where it's all blurry, plus there are no shelves, to see what it does. And it got like, I think it was about 90% accuracy, where it wasn't completely blurry. So that to me is a different regime of operation, right? If you're doing MLDL, you know that you have to, to get these kinds of results, you're very lucky, and you have to, and you have to be very concerned about, that your new data set matches the prior distribution, right? That what you're doing now is very, very similar to what it was trained on. Here we purposely said, okay, we're not going to even do anything. And it just started, and we saw that it was really working quite well. And we gave it a few more examples where a different one here, okay? We just random images. Can you rectify the image? Can you find the products, etc.? And it did a really good job on multiple cases. And I was quite excited about this, because I know it doesn't seem like a very big deal or big problem. I mean, again, this runs in real time, so it normally would take a few seconds to give the actual results. But what was really fascinating about it was that it works so much better. I built a lot of machine learning, deep learning systems, and it's just, you never get to 100%. You have to work super hard to get into the 90s. And then if you give it something that's way outside of the training data set, it's not going to work at all. And here, it's like we couldn't really break it. and it's not, and I admit, what's the big deal? Rectangles, right? But it's an indication that we have something useful. So I'm going to show you, maybe you could say something. I'm going to bring up the cumulative learning demo.
Yeah. Maybe I can tell about the semantic decomposition. So one way to tell the agent to do it, maybe based on color. So okay, focus on the regions based on, let's say, where you see the red pixels more, just like human being, or the contrast. Here in this example, the examples Hugo showed, the system was focusing on the creating decomposition of the problem as the largest non-empty rectangle. Okay, find me the most crowded area and then work on that. Once you are done, move to the second most crowded one, and so on and so forth. With such a simple logic, we were able to deal with the combinatorial explosion actually, and give the reasoner time to think about it and reason in a detailed way.
So the next example, when we were still IoT last year, we won't be able to talk too much about like where Cisco really is using this, which is going to be for networking, security, the core business. That's where it's going. Obviously, it's going to be, we're already getting some pretty amazing results. When you do have the meta model, right? Because now it's like the first real formal. I mean, what we see, it just appears to be a great empirically proven approach to representing knowledge, and you use this as your basis while you have all these different learning engines running. What we noticed is that for free, you basically get cumulative learning, right? Because they're all basing, typically you have the same seed ontology, if you will, or you have the same, the ontology doesn't have to be just in Nars. It could be pretty much in any language, or it could be an actual standard ontology. There's a lot of ways of getting the ontologies in there. We have our own DFRE script as well. But if you have an ecosystem of these things, basically, we're going to show some cumulative learning that just comes out of the box, which is also very cool. Hopefully, a lot of this will be open source soon, because again, I think that we have approval for the IoT-related smart city stuff to become more of an ecosystem that we just support in the background as we focus on networking. But maybe Oz, if you want to talk about this, you can go get into that. The use case.
Yeah. In this scenario, there is a hit and run situation. So each camera actually, or each agent has its own camera. It's better to say each camera has its own agent. So one agent witnesses a hit and run situation, sees the accident, and then another car runs away, and then raises an alert. So in this use case, the focus of attention mechanism actually triggers the other possible agents that might see a clue about the running car. So the focus of attention here knows the location of all the other cameras, and actually one of them sees another car.
Your audio is kind of fading there. At least it was for me. I don't know if it was for everybody else. But one of the key advantages of Nars in this case, by the way, is the adherence to AIKR, right? Which means that, so right now, Cisco has adopted the video analytics that we built. They're on camera, right? And you need to have the Nars run on camera, which it's very, very efficient. So the AIKR really is making a big difference on these kinds of applications. Here's the overall architecture. Oz, if you want to say a word there.
Yeah, so this use case actually is a simulation of collaborative learning. So each agent has its own, might have its own ontology, but also they together construct a knowledge graph cumulatively about a car running away, causing an accident. Yeah.
So at the time that we built this, we didn't have the real-time ability to visualize the evolution of the knowledge graph, but it would be very cool. As I know it's not our focus right now, but hopefully this kind of work that we've done in IoT will continue on. I think there's a ton of potential, you know, right now, so many applications. But what the new framework we have applied to this problem retroactively would be really significant. Do you want to say something here? I'm going to bring up the video too.
Okay, so, well, actually, this summarizes what we use for visualization. So the main database.
We're losing your audio. So basically, in the demo, we have these 7 agents, and you know, it's kind of a basic. Again, it's not very exciting. It's like the last demo. You know, we could pretty soon actually we could show some videos of this stuff working live in Australia and other places, but that'll be maybe next time if you guys decide to call us back. I'm going to stop sharing this and. That's strange. It's not showing up as a sharing option, unfortunately. Give me one. Okay, it's there. You can't see. You don't see anything on the screen, correct?
Right.
All right. I'm gonna try one last thing. There seems to be some issue here. Okay, sorry guys, it's not coming up, you know, but for whatever reason, it's not that application is not showing. The video won't show. It's not showing up. But it's in essence what you were going to see was just this implementation of all these agents coming, basically doing cumulative learning, right? So I think that's in large part what we wanted to show you. And this is the tip of the iceberg. You know, when we're able to have more discussions into what's really happening with the time series, the combination of having the static information from, you know, that you learn from all these different ontologies, and Oz, when he got his degree with Pei, was focusing on I think WordNet and ConceptNet. I mean, so we're ingesting all that stuff out of the box, and there's other ontologies. We have a lady at Cisco and a team that have been working 20 years to build a Cisco knowledge graph. That's in here, obviously now. So things are happening pretty quickly, and we're looking at a lot of other ways of bootstrapping the initial knowledge, and also, you know, with the input being time series, the sky's the limit. I mean, it's just such a generic way of inputting knowledge about the real world in real time that yeah, I think it's quite promising what we're seeing here. But thank you for your time. I mean, and for all the researchers that we're working with currently, you know, you're making this possible. We're very thankful for all the support and ideas that you have. And like I said, we're pushing to do more open source. And I think we're going to be publishing some papers on this, and hopefully we can jointly do extend some of these ideas as well. But with that, I'd just like to wrap it up. Thank you.
All right, thank you very much for this talk. Let me see. Does anybody have questions?
I have a question.
Hey, Patrick, long time no see.
I have a question about the visual attention mechanism you use. Because it seems like you're processing only small parts of the image, right?
in the product identification. It's only
yes.
What is the guiding principle here? Which what data priority we are to look at?
Right. So basically, we have the DFRA meta model where you have all the rectangles go inside of there, and then we have a small amount of logic that basically gives you spatial semantics, right? And so for the spatial semantics, you have the basic things you would imagine, containment relationships. You have several other very basic things, and we're able to basically. That was a very easy problem of using kind of what I would call like a semantic decomposition, although it wasn't a clean partition because there was some overlap in the partitions, but that was okay. It didn't matter. It gave us enough of a decomposition that we were able to completely address combinatorial explosion issues. And right now, if we had 10,000 rectangles, it would be no problem. So and that's an area right now that we're thinking more about, like different, we'd like to have more generic decomposition mechanisms, and that's where we're finding some pretty useful things happening in the graph space. To find like graph, if you look at graph compression or graph summarization, ways of finding fundamental structures that are in the graph to describe the graph, those are likely ways of decomposing the problem as well. And because we have the layers of abstraction, that also helps you. The layers of abstraction give you, a nice structure of knowledge that you can use to decompose problems. And it is fairly compatible with Nars intension extension, but not 100%. So, but it's very synergistic. And one area that I would say that Nars looks very, very promising to us is when you have, say, you have an existing meta model graph, very complex, and you the problem requires that you connect two distant pieces of knowledge. Right? How do you do that? There's evolutionary techniques. There's other techniques, plausible chains of inference that connect ideas that you couldn't see before. But yeah. And by the way, thank you so much for all the support, Patrick. We're hoping to bring you into the Australian project.
Sure. And I think this very interesting. Also, a visual attention approach is a good candidate to be generalized in a general vision system, which can also work for other domains.
It's completely general. The basic spatial semantics could operate on anything. So it could be. There's a lot of other domains, and currently the design that we had was trying to actually represent images as time series. So to all the shapes, the edges, all that kind of stuff would be a time series, so that we can apply our time series of, but because we had a very limited time, we just ended up using like a YOLO, the latest version of YOLO, and we just basically made it so the confidence was like 0. So it gave you every possible rectangle, right? So you had thousands of rectangles, but with reasoning, and the spatial semantics information, you were able to get good results.
Wow, that's interesting.
We could, I think the non-parameterized image rectification may also be interesting for some of the work that you're doing in robotics as well. There was, there's something to talk about later, maybe.
Maybe I'll let someone else ask a question now.
Yes, I have a question, Hugo.
Yes. Hi, Antonio.
Hi, Hugo. Thank you for your talk. And there are many contact points between your vision system and my proposal of focus of attention. However, I think that you consider rectangles. So in any case, it should be useful to take into account even the three-dimensional aspects of an object, for example. The fact that if you consider, instead of considering rectangles, you consider the full 3D aspects, and more the fact, for example, that a system, just like a robot, may navigate through the scene. You have a more rich vision system.
Yes.
This is my view.
No. So we agree with that, and that's why we like the meta model. That we didn't dive into too much. But what the meta model allows you to do is to have n-dimensional representations and connections in the graph space. And so what you can do is you can say, okay, so now give me a focus of attention that incorporates this particular attribute, this particular dimension, you know, and so we call this, internally, this is kind of the L2 more abstract space where you can kind of have many overlapping, you know, abstractions and hierarchies, you know, so 3D, 4D, it all fits with what we're doing, definitely. And to be honest, right now, like I said, we're really focused more on multidimensional processing of non-visual data. I feel kind of sad that we got to this point that we couldn't do it, use it for anything, which is why I'm trying to get it to be open source. So hopefully we can do much more. But really, the work that we've done with the meta model and the graph space and all that, I think that could be quite useful for a lot of projects, actually. Very high performance, by the way. We're seeing, you know, the Redis time series. I don't know how many millions of data points per second. It's huge. I mean, very, very fast.
Well, in our use cases, we had 1.2 million, but I think it can go up more than that.
Yeah, and you were using the batching, right? Like processing 10,000 time series at a time, something like that.
Yeah, it was like 25 million points, actually 25 million data as a batch process. But we can.
I would just recommend against trying to build like new fundamental components like that if you have if you don't have a real very solid need for it. And the way that Redis is built, if you want to customize it, they have a Lua interface that you could build into the engine itself. So it's very hard for me to justify doing not using Redis right now for a lot of things.
Okay.
Okay.
Thank you.
Thanks, everyone.
Thank you.
All right, thank you very much. Our next speaker is Robert Johansson. Robert, are you here?
Yes, I'm here.
Hi, welcome.
Hello.
All right, your talk will be on the scientific progress in AGI from the perspective of contemporary behavioral psychology.
Yes, that's
good luck.
Let's see if I can share my screen here. There, you can see it there, right?
Yes.
Great. Okay. Okay. Thank you for having the opportunity to talk at this event. And I'm very, how to say it, grateful to talk among all these people who do this great work. And let's see if I can. Okay, so yeah, a bit about me. I work as an associate professor of psychology at Stockholm University, and I have specialized in clinical psychology, and a lot of my previous research has been in that field, especially when it comes to designing various treatment programs, very much through the internet. But I've always had this interest of behavioral psychology and especially models of cognition from a behavioral psychology perspective. And I found out about Nars because I have always had this interest in AI and the possibility about studying processes from the perspective of relational frame theory. For various reasons, Nars seemed to be a very interesting candidate. And since 2017, I have tried to follow along what happens in the Nars community. And at the moment I'm working on this thesis called Arbitrarily Applicable Relational Responding as Non-Axiomatic Logical Reasoning, together with my supervisor Arne Jönsson, who I see is listening here. I just try to switch here so I can see the participants' view. There you go. Okay, so the purpose of the talk is to provide a perspective on science and scientific progress from behavioral psychology. And psychology as a science clearly needs to reflect on its subject matter. And I tried to reason about this also in the AGI field. And I try to provide some examples of how behavioral science has progressed recently and try to discuss if this is applicable in the field of AGI too. This talk is based on this paper, Scientific Progress in the from the perspective of behavioral psychology, that is available on the Open Nars conference page. So very much what I'm saying is based on the theory, relational frame theory, which is a attempt to understand language and cognition from the perspective of behavioral psychology that has been going on since the 1980s. And the major book came out 2001, and the latest description is in the handbook from 2016. I also based this talk from very recent developments in the RFT community. This is the 2017 paper by Barnes-Holmes and his group, and also the 2020 update of RFT. So I tried to reason about this progress in this talk. But why study Nars from a behavioral psychology perspective? Why combine these domains, so to speak? And for one reason is simply there is some strong conceptual similarities. I would say that the definition of learning from the perspective of behavioral psychology is as ontogenetic adaptation. And as everybody here knows, how Pei Wang defines AI is adaptation with incomplete knowledge and resources. And this simple fact is an important foundation in the work that I try to do, to really look at learning among human beings and in Nars are two forms of adaptation. And another interesting thing, another similarity, so to speak, is regarding the semantic model of Nars, that is, as you know, based on the experience-grounded semantics. And this kind of semantics is also very similar to how one can say the acts of meaning approach that is in RFT. So what is science from the perspective of behavioral psychology? Okay, first, any science should define their units of analysis, like cells, proteins, genes, elements, and atoms, and field, etc. in biology and physics and so on. But what are the units of analysis in psychology or in AGI? And I will use various types of units of analysis to try to describe a path for scientific progress. And the first candidate, so to speak, that has been the unit of analysis defined in behavioral psychology in the 1930s is the discriminated operant. So what is that? So operant behavior is something we could call purposive behavior, or you can describe this using some kind of formula with a discriminative stimuli elicit some kind of response that potentially could lead to reinforcement. And this kind of unit is simply a way to analyze behavior in context. Behavior is preceded by some kind of antecedent and is followed by a consequence. So this overarching spatiotemporal contextually defined analytic unit is what defines this kind of the discriminated operand. So for example, if a rat in a cage learned to press a bar in the presence of a green light, that's an example of an operant behavior. That's a behavior that we can analyze with this unit. Or another totally different thing in a way, when a child get the temper tantrum to escape a demanding task, can look like a totally different thing, but on the principle level, they really share something. There is something that happens in a context A, leads to behavior B, and has a consequence C. And importantly, the rat can press the bar in many ways. So it's not really about one behavior, it's really about a class of behaviors that happens in the same context and leads to the same consequence. But importantly, the actual unit that is analyzed in this way is the probability of this operant behavior to take place. And so let's say that the rat is in the cage and learns to a rat, when it runs around in a cage, it typically does a lot of behavior all the time. So it will try out to press the bar, it will try out to do whatever it can in the natural environment. So if we don't provide any feedback, there will be a natural probability of the space bar pressing, let's say a probability of once per minute or something. But the actual, we can show that we have reinforced the behavior by food, for example, if we can increase the probability of the spacebar pressing behavior to happen. And this can be studied using match to sample experiments. For example, the match to sample experiment is you are shown a symbol like A1 and have an option to choose left or right between B1 and B2. You should pick that one and get some feedback that, oh, that's correct. So people can learn relations between A1 and B1 through this kind of match to sample task. And maybe learn that A1 is connected to C1 and A2 to B2 and A2 to C2. So that's an example of a matching to sample task where it's possible to study this kind of operant behavior. So one way to study this in Nars would be, I played around a bit with Patrick's recent Open Nars for applications, where the system has this natural capacity for motor babbling. Or actually, Patrick, I think you only yesterday or the day before extended the model with curiosity and play. So as an example, let's say that the system can do the left and right operation, and you have a motor. Actually, in these experiments, I removed all the other operations except left and right and increased the motor babbling. So the left and right will happen with a natural probability. And in the context of, for example, light is on and the system has a goal, G, exclamation mark. The behavior right will increase in probability if G happens after the right operation. So that's an example how G functions as a reinforcer in that context. So let's say that the light is on and the system has a goal of G and we wait for 10 seconds. Maybe the system, remember we want to reinforce right. So the system tries left by motor babbling and we only provide time, but if the system makes a right response by chance, so to speak, we can provide the context of G afterwards. And given that knowledge, given that experience, the system will learn then, derive that, if light is on and I will do the right behavior, that will lead to the consequence G with a certain confidence. And with more examples, more experience, the confidence of this, how to say it, reinforcement experience will increase. So that's an example of operant reinforcement in the open Nars for application. So that's an example of something we can analyze in Nars using the unit 1. And there's lots of interesting research you can do with that. For example, Skinner wrote a 600-page book only about schedules of reinforcement. How will we provide the reinforcement? Is it on a fixed ratio, or is it more like, the jackpot machines? You don't get the reinforcement every time. It's because of the randomness that people become so crazy about it. So there's a lot of interesting research you can do that. But of course, the unit also has limitations. And one example of a behavior we can study in Nars that highlights the limitations of this unit is when we study stimulus equivalence. So let's say, as before, the system learned that A1, it learns to pick B1 in the context of A1, and it learns to pick C1 in the context of A1. Then a human being typically also derives that B1 is connected to A1 and C1 to A1, and also these two. And what I mean with that is, actually I can show it like this. If we have learned this thing that I showed, if we then reverse the sample and the left and right option, and C1 is presented as a sample, and the system needs to pick between B1 and B2, it can act on the derived relation. So that's stimulus equivalence, which can look like this in Nars. Given this experience, and you ask the system, is C1 the same as B1, or is C1 the same as B2? And this is also open Nars for applications that answers C1 is similar to B1, but C1 is not similar to B2, or it doesn't provide an answer. Okay, so it seems like this fact that stimulus equivalence is defined by this emergence of untrained responses, and which is a very key thing for symbolic reasoning. And importantly, it's not possible to analyze this behavior using the first unit of analysis, because it's not a fact that we provide a context A and a behavior B happens that leads to reinforcement. This is an unreinforced behavior, so to speak. So this unit has limitations when it comes to symbolic behavior. So the whole point about relational frames is a more abstract alternative to unit 1. And arbitrarily applicable relational responding, as I mentioned, is really this thing about talking about cognitive processes, symbolic thinking from the perspective of behavioral psychology. And my contributions to last year's AGI conference was about describing this in Nars. But an example of this behavior. So let's say that A is worth more than B and B is worth more than C. You hear that in some kind of context where you don't know about these currencies. Then we can automatically derive that, oh, okay, C is less worth than B, for example. And we do that derivation without any experience like the size or how they look or something. It's only purely based on the verbal information, so to speak. So this contextual cue of is worth more than is what controls the response. So that's why we say that this is an arbitrarily applicable. The pattern is arbitrarily applied. If there had been another contextual cue, like these are similar in worth, that would have triggered another response. Not more than less than, it would have triggered the same response. So this highlights the fact that these abstract applications of relating is controlled by context. It's only the keyword more than, less than, or more than that actually triggers the abstract application of the more than, less than frame compared to the same keyword, the contextual cue that triggers the same relational frame. So how symbolic behavior is viewed from the perspective of relational frame theory is that it's something we call a generalized operand. So it's this abstract unit. For example, in the case of sameness, it's a way to coordinate stimuli, which children learn at typically 2 years of age. And this is extremely important, that the whole point of RFT is that the contextual factors involved here operate on the abstract unit itself, on the frame itself, rather than its instances. So in the left-right example, the system learned something very closely related to the left and right operations. But from the perspective of relational frame theory, this applicable pattern of relating is something that can become reinforced by itself. The context operates on that by itself. And I will say a bit more about that, but briefly, there are a lot of different patterns that we can study from this perspective, like opposition or things over time or hierarchy. So what we mean with this arbitrarily applicable relational responding is these very abstract applications of these patterns of relating. And we say that when we say something like that's a cat or that's not a cat or that is faster than a cat, that is how we specify these relational functions. Like these are example of sameness, distinction, or some kind of comparison. But when we say something like that feels like a cat or that sounds like a cat, that specifies something we call behavioral functions, like, for example, perceptual functions. So when we say that feels like a cat, that's both the relational functions are sameness and the behavioral functions are some kind of tactile functions specified by that statement. So the relational frame is this abstract unit of relating and transforming functions through these relations. And this is something I reasoned about in last year's workshop. This is also an example of open Nars for applications. Patrick's example of symmetry. I think it's a very nice example of how the system learns by the operation happens on the frame itself. So given lots of examples here that A is like B and B is like A, C is like D, D is like C, E is like F, F is like E, and so on. And in this example, Patrick asked the system if it has derived this abstract knowledge. So this is really the system in this abstract knowledge doesn't have an experience of, this abstract knowledge doesn't include A or B or C or D. It's really the abstract knowledge. So these operations are on the frame itself. So the system gets more and more confident in this abstract knowledge. So this is an example of when the context operates on the frame itself. So this is a behavior that requires the second unit of analysis, the relational frame, to be able to analyze from this perspective. But there have been critique on how to use the relational frame to analyze such a broad range of behaviors. For example, does it really make sense to analyze something, a very simple child behavior, to a very advanced comparing and contrasting of large narratives? So that's one critique. And another critique from within the community is that a lot of research has been on demonstrating the relational frame is present or not. It didn't study the dynamics of this, like how does this vary? And there have been quite challenges in going from this lab research to real world applications. So the unit candidate number 3 is something called the multi-dimensional multi-level framework. And this is the 2017 version of RFT, where the Barnes-Holmes group described 20 units of analysis, which looks like this. And on the y-axis, there are levels of relational development. And there are also some dimensions described there: coherence, complexity, derivation, flexibility. And I will very briefly mention this. But the whole point of this is to get a more fine-grained analysis of this kind of relating. So what is levels of relational development? So in the example we just had there, Patrick's example, that's an example of mutual entailment. If A is larger than B, then someone can derive that B is smaller than A. That's a mutually entailed comparison response. And this is something I published in the last year's conference paper. This is an example of how Nars does these things with the opposite or more or less than relation. And when it comes to relational frames, for example, if I learn that A is larger than B and B is larger than C, then someone can derive that C is smaller than A. So that is a bit of a transitive response. It's a derivation in multiple steps, so to speak. So it's children typically learn this about 6 or 8 months after they have learned mutual entailment. So it comes later in the relational development. And this is also something I talked about in that paper. This has been a problem to have it work stably in Nars, but the system can do it under certain conditions. And examples of the higher levels of relational development is to provide rules and instructions is on the level of relational networking, and reasoning about analogies is relating of relations. And the highest level is understanding and producing large narratives and doing advanced problem solving. But an example of level 4, relating of relations. So let's say that you have 2 frames of coordination established, like A1 is the same as B1 and B1 is the same as C1 and C1, which yields C1 is the same as A1. So that's a transitive response, so to speak. And also at the same time, someone learns that A2 is the same as B2 and B2 is the same as C2, which yields C2 is the same as A2. People can then, by analogy, reason that, okay, C1 is probably to A1 as C2 is to A2. So that's a quite advanced lab-based analogy that children cannot do when they are 4 or 5 years old, but they can follow rules and instructions. So that's evidence for that this is some kind of age-related phenomena. Children can do level 3 at this age, but not level 4. So dimensions. So this is a suggestion from the RFT people how, like, dimensions of responding that make sense. So coherence is, for example, to say that a car is larger than a truck is typically something that lacks coherence given a normal history. And complexity of response is that generally we can say that if I respond B is smaller than A, if I have learned A is larger than B, that's a more complex response since it involves 2 relations, smaller than and larger than, compared to the sameness relations, which are the same relation both ways, so to speak. So that's an example of a more of complexity. And levels of derivation is how many times has a response been derived, so if the system makes a behavior for the very first time through derivation, then that behavior is very high in derivation compared to if it has done it very many times. And flexibility can be of a response if how easy is it to respond to please respond wrong. So this is an attempt to understand contextual factors to move from the can someone do a response or not, and really go to the dynamics of responding. And in the case of AGI, for example, it's really, how to say it, moving from can machines think to moving to the dynamics of thinking. How can we understand how contextual factors influence dimensions of coherence and complexity and levels of derivation? And a few examples from the literature on behavioral psychology. So participants in an example, in an experiment, when they tended to derive coherent relations when they were presented with an ambiguous relational task. So when people basically don't know really what to do in a relational task, they tend to provide a response that is more coherent with the history. And this might be of interest, I think, to some kind of autonomous systems that needs to operate in real time and make decisions also in ambiguous scenarios. Another example is that more complex responses seems to take longer time to emit under time pressure. And another thing when it comes to following rules and instructions is that people tend to be different in their persistence in staying on following a certain rule. And this seems to be very much affected by how many times a rule has been practiced. So if the rule following is high in derivation, that is, it hasn't been trained much at all, people are less persistent compared to if they have practiced the rule many times. And of course, there are multiple ways you can reason about different domains through this. For example, gender bias can be something that is understood, that people respond coherently with a history of some stories. Yeah, I think we can leave this. So this is an example of a study from 2020 where they really dig into the details in derived fear responses. So if somebody learns to associate spiders with nonsense symbols, there have been some evidence that the more steps for, if it's a transitive response, if a spider is associated to a symbol and the symbol is learned to be associated to another symbol, the fear responses seem to not transfer. And this was shown to be affected by increased levels of derivation, for example. So this is an example how you can approach something like derived fear through this perspective of the MDML net framework. And something about this and Nars is that it seems like Nars is, without question, possible to operate at level 1 of relational development, but as I mentioned, had some troubles with level 2, given the current implementation. And I think coherence and levels of derivations are very interesting from the Nars perspective, because it seems to tap into the frequency and confidence truth values of Nars. And complexity also seems to make sense. Potentially also flexibility. Okay, so there are still some limitations to the MDML framework. It can look very much like only abstract reasoning. It becomes very focused on the relational properties, and this reasoning about what is aversive or appetitive becomes more implicit. And also some very recent research has showed that the relating and the transformation of stimulus function, these features can interact through an experiment. So RFT has very recently suggested a new conceptual unit, the hyperdimensional multi-level framework. So this is the 2020 update of RFT, more field than frame. And very, very briefly, it is that at all of these analytic units, it's not only these relating properties, it also combines with something called orienting and evoking. And I will briefly say something about that. So from this perspective, the row is the unit, and the row is this combination of relating, orienting, and evoking. And relating is what I have talked about before, and orienting is attending or noticing events. And evoking is this aversive responsive or appetitive responsive, like, yeah. So fear is typically a negative evoking response. And of course, Nars is very much about relating. And I think it's very interesting that, as I understand, that there is a lot of focus now in the Nars control mechanism on the attention mechanism. And this seems to be connected to the orienting part of Nars, or the orienting. That's basically studying orienting in Nars. And Nars has this emotion model that already now can have different emotional states, so to speak, that can be evoked. And I think it's an interesting task to see how these can interact. So just an example. Let's say that you enter a forest with a guide who says, watch out for black spiders with a red triangle on the back because they are quite aggressive and highly venomous. So that's an example of the order relating, orienting, and evoking. You hear something and think about it. You maybe start to orient to the spider and have an evoking response. Compared to if you're out walking in the woods without the guide, and you, for natural reasons, start to orient to a spider, and then you start to think about it. Oh, okay, this is probably something that I need to be a bit cautious about, and then decide to leave the forest. So I just mentioned that it's no fixed order between these operations of relating, orienting, and evoking. And just an example of how the context affects this, that, for example, when I was on the bus today, I noticed that when somebody on the bus is coughing, I immediately oriented in that direction. And that kind of behavior, I can assume, has a lot of people has noticed the latest months. And another example is, how is water deprivation affect orienting and the evoking functions of water? Yeah. Okay, so RFT suggests by 2020 that this row is a unit that can be analyzed, that aims to capture basically all of events that human psychology takes place in. And they ask in this paper that, or encourage psychology as a field to reflect on its subject matter. It could be an interesting task for AGI science to reflect on its subject matter. And this is some quotes from the paper that I think is nice. The paradigm shift we propose involves removing the person or individual as an active agent from the analysis of psychological events, leaving nothing but complex clusters of behavioral functions defined in terms of historical and current contextual variables. There is no person or individual in the row unit in general. Instead, the psychological events is presented as a field of verbal interactants. The individual elements do not exist independently of other interactants. Rather, they are actualized by their participation in a field of interactants. There is no person as such contained within the field. In a sense, the person is a constantly changing or actualizing field of verbal interactants. So what happens when we remove the person or the individual from psychology? I think that opens up for the question if we can have a shared unit of analysis between AGI and psychology. And maybe this can be viewed as moving from can machines think to what experiences in the life of the machine will affect the relating, orienting, and evoking. And can units of analysis from behavioral psychology be candidates for a shared unit between psychology and AGI? And what progress will that lead to? And briefly at the end, I will mention something that might be a bit more unique to AGI compared to psychology. So this is a sea lion that performs the generalized identity matching task, which is basically that it sees an image in the middle, a palm tree to the left there, and then the task is to select the same image. So it trains on this, but the hard thing is then when it showed a new image in the middle and it can choose between that image and the image it has chosen before, will it then act on the identity matching, or will it choose something that was reinforced before? So this is something Patrick implemented in the Open Nars for research. And yeah, this I described the experiment. And Patrick talked to me about this at the AGI conference last year. And he said to me that, yeah, his model, ANSNA, it could do the generalized identity matching. But he realized or discovered that when he didn't have the Nars layer 6 in place, his model couldn't perform the generalized identity matching. And Nars layer 6 has this capacity for introducing variables for generalization. Yeah.
It seems to be a bit related to Turing completeness, maybe, I have no idea. Because in the moment you introduce or give the system an ability to have variables in terms of, so that it can substitute different terms which fulfill the relationship, you can pretty much describe everything like in Horn clauses, like in logic programming. So I also see to some degree where there are some relationships which might not be easily expressible in other ways and which seem to demand variables. And it seems to be even abstract patterns like transitivity. It's difficult to describe transitivity without using variables. All of you might do it with combinators probably, but you need something like those two things in place for this to work.
Yeah, I think that's extremely, and this is really what I mean with scientific progress in AGI, to have this kind of discussions that probably this thing is needed for this behavior to take place, or this is a really key feature of Nars for various complex behaviors to be able to happen. So I think this is a really nice example from your work, Patrick. I think you show that, okay, this functionality was crucial for this behavior to take place. And one could take this reasoning further. I think that that you have maybe more advanced experiments than the generalized identity matching task, and you can vary a lot of different functionality from the Nars system, other layers or maybe subcomponents. And I think that could lead to interesting answers to what functionality of Nars is needed for this experiment to be for the system to be able to succeed in that experiment. And of course, I think the detail of the unit 4 that I talked about and some of the details in those experiments are really interesting, I think, to really understand what is needed in Nars for some of these things to happen. And that is really one way that I would think it would be really exciting if AGI could progress.
Robert, let me add a few words here.
Yeah, sure.
Because we actually discussed this before in our team, actually more than one meeting. If we really have the time, we may want to be able to change Nars, build some special version which make it more like animal. That is, the current open Nars, maybe we can take out some of the inference rules and simplify the control mechanism to make it closer to animal level intelligence, which is closely related to what you just.
Yeah.
Currently, we are not working in that direction, but that's clearly a possibility.
So I think you're saying, for example, keeping the temporal reasoning, but leaving out, for example, introducing variables and things like that.
Variable is one thing. A compound concept is another key. If we take those things out, you will see it's basically animal level. It can still do conditioning. It can still do basic learning, but it's not going to be able to abstract from next year.
Yeah, I think that's a very interesting path, and maybe even simpler animals too, like some kind of one-cell organism that only can do habituation or something. What would be needed in Nars for that things to happen? Okay, so last word here. Units of analysis may provide some kind of valuable discussion on how to approach the subject matter, both in psychology and AGI. And I think behavioral psychology in itself may be interesting when you talk about scientific progress because of this strong focus on experimental tasks, for example, using the match to sample task when you study symbolic reasoning. And I think a shared unit of analysis between these fields could really be interesting. And as we spoke about, very exciting research when you start to remove or add layers. So I would like to end with a quote from Pei Wang here, something that is from the summer school 2013. At the same time, you need to be a very good or reasonably good philosopher, psychologist, mathematician, maybe logician, computer engineer, and maybe mechanical engineer at the same time. That's why AGI is not an easy job, no matter your educational background. So hopefully this perspective from psychology could be of some value to you people. Thank you.
Thank you very much, and it indeed offers a very interesting perspective. Let me see, does anybody have any questions? Okay, I think that then we can move on to the panel. So the panel on the roadmap of Nars and discussion. I just checked and we have all the panelists here, so I think we can just get started with that.
Yeah, I think I will coordinate this panel. First, thanks to all the speakers who share with us their very, very interesting recent progress and opinions and comments. What this panel is about is more about the future. But we don't really have the time to really do a detailed roadmap or anything like that. It's more like I want every panelist who are just basically the speakers of today to very briefly summarize what you plan to do in the near future. starting from me, okay? I give you, also actually I will post it to the chat window, a list of things that I'm working on recently and also going to continue in the near future. The first thing is recently I finished a conceptual design document for a new version of OpenNARS. Now we call it OpenNARS 3.1, and the team now is coding it. The major change is a new architecture, which is going to split the previous input buffer into several buffers for multiple sensory motor channel, as well as an internal experience channel. And also a refined conceptual design for the control mechanism, which you all know is the current bottleneck of the system. We hope this new version will do better. Another thing I'm working on right now is another design document for compound operation, which will be related to several things. For example, it's directly related to the robotics cooperation we have with the Glamour team. Also is related to how to solve this so-called self-programming or planning functionality, and also to improve the reliability and efficiency of the control mechanism. That's one part. Another thing I'm drafting is a memo which I already shared with some of you recently about how to do axiomatic reasoning within Nars, which is non-axiomatic overall, but you still need to do axiomatic reasoning as a local, smaller scale. For example, you need to teach it math, right? Teach it logic. What I tried is teach it, say, propositional logic, using those rules and do binary deduction and do it right. So I will continue to work on those things, as well as something already touched in recent discussion, that is natural language processing and vision, okay, which we have started, made some progress, but there are a lot of additional issues to be resolved. That will be my near future task. And also, of course, new application possibilities. That's me. For the others, who want to start first?
Should I continue?
Sure.
Yes. For me, the main focus was this open NAS for applications recently. Clearly, it has a focus on agency and autonomy. So I personally, also for my thesis, I want to push towards robotics use cases, and I want to show that this system can make a difference in for autonomous systems which have to deal with new situations and where the knowledge or the procedural knowledge which is given beforehand might not be sufficient to deal with new circumstances. And so this is also, I was often, many years I was concentrating on procedural learning because I was always a bit convinced that such a system needs to be able to deal with multiple goals in parallel. It cannot just learn a single state action mapping like a reinforcement learner, but it should be able to change its behavior dependent on the goals which it has. So this was always a large, my main focus, so to speak. And now I want to make this succeed for robotic applications. This will entail several things like building proper sensory channels. Here I'm very open to use the best technology which is available, including ConvNets and maybe other approaches from robotics like simultaneous localization and mapping. So I want to find ways to to utilize those technologies and to make the most of the system in terms of how much it can add for autonomous system, so that it can deal better with novel circumstances. And for OpenNAS for application, this also means for me to make it scale better. Currently, the data structure is not yet perfect for its memory, so it's a bit slow for event processing currently. And I wanted to be able to handle much richer event streams, and so it's not allowed to take too much time per event. Even though this has been improved in the last version, or last two versions actually, but there is still a lot to do to make it really scale. This is one thing. Yes, and personally, I'm also very interested in what Robert just described with relational frame theory. I think what he found here is really a crucial component of learning, or that the stages of learning he described are essentially, I also experienced them with working with this system. So you could have something like simple conditioning between events A leads to B, B leads to C. But then you also want to be able to expose the internal structure of the events. For instance, the system can learn if this object and this object has the same color, I want to use a different behavior than when the color is different. This is a really abstract pattern. So it's the equality of the color itself becomes a stimulus to respond to. And this is the good thing about non-axiomatic logic is that it allows for such abstract patterns to be formed via variable introduction. And the only thing is it's not easy to control it properly. So it puts a lot of strain on the control mechanism to make sure that those implications with variables can properly form, and that the relevant and successful ones will remain in memory, so that the system can fulfill the relevant goals. And here it's also a key thing here is to make sure that that the useful representations survive in memory. And this is something in previous versions with the Java version so far, as Bay mentioned, we did not take too much time for the control mechanism yet. But I think this is where we really have to change some things to make sure that the right representations survive in memory. And with this new C implementation, from a control perspective, I think it's superior to the Java implementation, but not because the structure is better. It's mostly because so far it has a very simple attention mechanism, which is easy to tune, which you can easily configure in a way that it will work well across different tasks. But it does not yet capture all the aspects which the Java version captures. So it will be relevant for us to compare those control mechanisms and to see, for instance, what we miss in the C version, but on the other hand, also what do we capture in the Java version, and how can we make sure that the Java version exhibits the right dynamics as well, so that it will not get stuck in attention-wise to focus on something which is not relevant anymore. Currently, the Java version has a lot of attention issues, and those need to be resolved if it should work in a cumulative way like the C version currently allows. This is one thing. So control mechanism is still a large thing to work on. But at the same time, I want to push towards robotics applications, and this will include to finally work on things we also ignored, which is mostly sensor processing. How can you get a lot of, say, numeric data and make sure that you find some relevant patterns in them, which you can then reason about, so to speak. So you need some kind of sensory channel or something which can work with the scale of information. And I think what Hugo did is really relevant for us as well. Especially the visual attention is something we always wanted, but we never had much time to work on. Oh, my cat, sorry. We didn't have much time to work on visual attention yet, although we think it's a key component of an AGI. It needs to be able to focus its foveal to spatially to objects of interest. It cannot process the entire image as a whole, but has to incrementally look for interesting pieces, which in the end are also related to the goals of the system. What does the system want to achieve? And so it's, yes, this is what I want to work on.
Maybe I can add just some brief things. Yeah, thanks for that, Patrick, also what you said. My plan to work on is simply to try to make some of these experiments possible. And I, as you saw, started using OpenNars for application and have emailed Patrick a lot about the representation of these experiments. And I think I mentioned at last year's AGI conference that I would like to connect these to psychological experimental software. The goal would be to use the same software for human responders to experiments as Nars in a way to increase the validity of the results from Nars. But as Patrick mentions, it would be really interesting to have this bottom-up approach to study more and more advanced experiments. And yeah, I would simply like to continue to work on that. Thank you, everybody, for the great work you do in the Nars community.
Thank you. Maybe what I should also mention, because we have this collaboration with the Palermo team, and this is really good because
yes, so we are, in a sense, we are, both myself and I think Francesco, we agree with Patrick on the need to implement the Nars systems in a robot or in some kind of embodied system. Both from a practical point of view, of course, there are many I know that there are many problems in the integration of ROS with Nars and so on. But there are even theoretical point of view. For example, the good old problem of symbol grounding or whatever. We discussed a lot in the last weeks about the symbol grounding and about the role of the focus of attention. And all those things, when you implement this kind of Nars in a real robot, in a real embodied entity, in some sense, we are able to change our view because the robot give a different sense of reality. In a sense, in this way, even the theoretical aspect of symbol grounding change the aspects because there are cameras, there are moving effectors, and so on and so forth. And so I think that the implementation of Nars in a robot will be useful both from a practical point of view, but even from a theoretical point of view. And so I greatly push toward this goal. There are other aspects which are, I think, that are interesting to considering in Nars. One aspect is a really hot topic today in neural network in learning theories, and it is related to the big problem of bias. In a sense, a typical neural network today, there is a lot of discussion in these days on the problem of bias, of race bias, of gender bias in a typical neural network. I think that a system like Nars may be more able to cope with the problem than using a classical deep learning network or whatever, in the sense that it's more possible to understand the problem, it is more, essentially Nars is more flexible, it's more transparent, and so it's more easy to cope in a sense with this problem. I think it should be an interesting field of research. So the problem of bias in learning, considering Nars with respect to a typical neural network, gender bias, race bias, and whatever, may be an interesting field of research. And a related field of research, which is interesting, in my opinion, it is important in an autonomous system, is the role of ethical constraints. Today, the problem of ethics is a huge problem, which is related in some sense with the bias problem. But the problem of ethics in an autonomous system is a huge problem. And we all know the problem of Microsoft Tay, for example, the chatbot Tay or whatever. And maybe the fact that in Nars, it is possible to implement, to clearly define the ethical constraints in forms of rules, in forms of symbolic constraints and so on. Maybe another field that it could be interesting, in my opinion, to take into account. So to summarize, my interest in future version of Nars are the integration with robots and with sensor and actuators. The problem of bias and the problem of ethical constraints. In my opinion, those are three important fields of research that I would like to see in the future developments of Nars. Thank you.
Yeah, I will fully agree. We have already talked about this robotics thing, integration topic. The other two, I completely agree, and I would suggest that, in our current weekly meeting, we can find a future time to just focus on those topics that we can talk about in the context of that. Yeah.
I want to add that also important the fact that with Nars we can implement systems that are transparent and explainable. And in terms of robotics and HRI, this is very, very important, because if we can justify some action to human or in general, we can know why the agent adopt this kind of behavior. So I think that with Patrick we are trying to define a proper package for letting all the robotic platform use Nars. So we will see.
I guess I'll jump in there. Next time it might be nice if someone just kind of selects people. It might be easier than waiting. But so as you know, I'm more about applied because I'm working at Cisco. So we're trying to do bring business value. So that's a high priority for us. So from the applied AGI side, I think that there's a couple things that could be important that we could all work that might be useful for all of us. Is we've very briefly covered the value of this meta model, the structure of knowledge, and some of the concepts that I think are very crucial to get to the next level in AGI. Last year, I was asked at the AGI conference, when do you think that we'll start to see real AGI, like human level intelligence? I said 5 years, which means we have 4 years left. So So here's my strategy. I still want to do that. I'm sticking to that, but I think we could do it in 5 years. And that's going to require, I think, a lot more funding, a lot more. So on the funding side, what I'm thinking right now is what we're showing today at Cisco with what we've done together with Smart City, with you know, the open conservation, with the new stuff that we're doing with networking. I think could be quite big. IoT, retail, all these things. If you put it together, I think we're getting to the point soon that we can make a case for a lot more funding across all these different approaches that we're talking about. And I think that's why it's particularly important that. Yes, I'm kind of on mic. So that's why I think it's really important that we have some kind of framework that allows us to tie all these things in together and show results today, right? So I think we can do that, and I'm looking at a month or 2 months, but the capabilities that Oz and the team that what we're showing right now within Cisco, I think will allow us to start to do a lot more with all of you, and that's including probably other researchers we don't know yet, but also including, you know, definitely there's a lot we can do with the OpenCog work and ERA. I think they're all crucial components as well as the Nars piece. We see how all these things can fit together quite nicely. So yeah, getting that meta model in a better shape, I think is key. Concretely, Oz, do you want to what's your wish list? We're doing so much with time series. I'm sure there's something there that you would like to mention. Or maybe he's not around. So yeah, go ahead.
Yeah, especially with the integration of time series in the model will allow us will give a system easily integrate different data modalities without you know, a lot of parameter settings, etc. So that's one of the keys.
So I think you know, I mean, from a high level, we can get into more of our research objectives, but certainly more open Nars for applications. You know, from the open Nars side, I think that's crucial. Maybe it would be useful if we were to open source. I have to get approval. This bidirectional interface between, you know, kind of knowledge graphs or other graph systems and Nars. You know, I think that might be something that could help move the bar forward for everybody. If we can agree to some sort of a graph-based representation, along with tools to analyze the graph, tools to visualize the graphs, that could probably, you know, and then that way you can try all your various, you know, approaches to AGI and techniques, and you would have one common platform that would have the basic tools of managing the graphs, growing the graphs, distributing the graphs, cumulative learning. Different ontologies could be integrated by default into that thing. Dynamic visualizations, you know, there's just, I mean, there's a lot of fruitful things we could do by just thinking what's something in common that all the approaches have that could benefit, that they could all benefit. I think, you know, representing knowledge in a graph we can all kind of agree to in some sense. And I know that in a sense, Nars has an internal graph representation. We just have to kind of pull that out and generalize it a bit more. But those are some initial ideas there.
Yeah, shall I go next?
Sounds good.
So just to summarize briefly what my team and I are working on and will be probably focused on for at least the next 2-3 years. Well, I've been writing a book for a couple of years, and it's coming along on the role of understanding in AGI and how the two are related. So that is on the horizon in the foreseeable future. We are using a combination. We're hedging our bets by using both Nars and ERA and trying to learn something from that contrast and comparison. In part because I do think there are some new systems in the future that we will have to design to really move forward. And I really look forward to making some progress on that. We're already making some progress. Of course, it can always be faster. we just finished, one of my master students did a really fantastic job on creating a new tool for evaluating learners, and you'll see a presentation on that tomorrow. Leonard Eberding, called SAGE, Simulation Environment for Autonomy and Generality Evaluation. And so we're currently just trying to cram as many learners in there and as many tasks as we can, move as fast as we can to produce data, because we can create more systematic comparisons of learners and results than ever before. And that will allow us, I think, to get a handle on something that is very dear to my heart, because I think we really need it, and that is some sort of a task theory, something that we can call a deeper understanding of what tasks are and how they become complex or simple by changing them for particular learners and learning styles. We are also very heavily focused on self-explaining systems. So we're beyond explainable systems, and certainly black boxes, although they do have their place still. Self-explaining systems are systems that can not only explain themselves and their actions and their plans to others, preferably humans, but also explain it to themselves and use that as a way to get better at learning. On the back burner, hopefully moving to the front burner soon, I really would like to concretize a project in cognitive perception, the interface between cognition and perception, because I think there's a lot of really interesting things to be discovered there. And I think the work that the Nars team and Cisco have been doing in combining vision and Nars is just a tiny little sliver of the top of a giant iceberg in all sorts of really, really interesting topics, and probably necessary topics to be solved for making progress towards truly useful proto AGIs or real AI. And that kind of also points in the direction of my fifth bullet here, which is applied AGI, because I really think that's a nice way to drive the work. So that's my short summary.
Can I ask a question? I mean, I think we mentioned basically not really beneficial AI, but since if we are going to have AGI working in say 4 years, we probably need to think a lot more about really like regarding goals. You know, how do you tailor these so that it is beneficial and that sort of thing? I think that there was a recent presentation with Stuart Russell, focused entirely on this beneficial AI idea, but privacy, making sure that we're not giving governments and institutions and the whole framework systems that potentially could become oppressive. You know, just we have to be very careful. You know, so there's a lot to think about there. I mean, I do like the French idea of like surveillance, right, where everybody watches everybody else, right? So there's no advantage to any one party, but all those things of safety of this technology, I'm pretty convinced it's getting quite powerful, and it will be much more powerful in a couple of years. So beneficial AI, I think, is something we really need to dive into.
Well, I think that there's a really important corollary here with, the abuse of technological advances, which of course human history is rife with examples of. And a lot of the solutions aren't actually technological solutions. They're, for instance, agreement of mutual transparency between nations and so on. And these are, while they are very important, I think it's, well, I'm not willing to, let's put it this way. I have been active in really thinking about this a lot in the last 10 years, but I'm not really willing to slow my research down to become an activist. So I think it's really important for those who actually do see this as an issue and have a conscience to figure out ways that researchers can team up with responsible activist bodies and oversight bodies and governments that we have a greater tendency to trust than to distrust, and really, you know, address this like responsible researchers.
Yeah, yeah. Big problem that you see right now with the beneficial AI and privacy preserving AI and all of that is that they're typically people that can barely spell AI or AGI, right? They're just politicians or non-technical folks, you know. But like, I love what you're saying, right? You need an allegiance between the two. And unfortunately, at this point, the state of it is that most technical people that know anything about this field will probably not get involved. It's a problem.
Yeah, and there's a huge educational challenge that we have also with everyone becoming an expert in AI now.
And in my view, by the way, certainly legislation, some government body that says, okay, we're going to regulate AGI. All that does is basically makes it easier for the bad guys, you know, to have their AGIs do whatever they want. It'll be all, you know. Well, it's. I don't think it's like you said. It's not. It's a very complex issue, but maybe there's a way to maybe like you said, get the researchers together so that the first AGI's job is to, besides getting smarter, is to control the other AGI, the evolution of the other, you know, and that one is controlled by good people, like such as yourself, Chris.
Yeah, yeah, it is a complex issue, and it's a global issue, and it's certainly, in my mind, not as simple as let's just make the AIs really friendly. That's for sure.
That's a good point. I'm actually curious what others think about this as well. Like, how should this be approached, and what are possible solutions?
Well, I have to say I have tried several years to avoid this discussion. Not because I don't think it's important. It's just because I think this is a very deep problem. And most of the active voice I have heard so far, I think they get the problem technically completely wrong. And also, I don't think I can convince them just at this conceptual level discussion. So you'll see that I have tried to avoid this. Even though I think, on the other hand, I fully agree, this is crucial and we should make our point clear. Actually, we did something, you know, with Chris a couple of years ago, we write a short paper at the AGI conference to basically say that the basic argument is if you really want a beneficial AGI, the key issue is not in design, it's in education. Okay, many people still don't see it. They think they can design an AGI with a super goal, you know, just to be friendly to human beings. That's completely wrong. But I don't think I can convince those people, even though I write a paper on this in a previous AGI conference at Oxford, just directly talking with those group of people who is talking about super intelligence, blah, 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 blah. But it seems they don't understand what I'm talking about altogether. So I think, you know, if you spend all your time on this, it doesn't get you anywhere. So I'd better, you know, go back to the technical stuff until we really make something impressive, then people can begin to listen to it.
I think with the advent of applied AGI right now, it's another factor, right? I think, you know, you've been doing it over 30 years. A lot of people here have been really researching AGI for a very long time, and it's not something you really have to think about too much. But if you get a company, a big company, and more companies are going to be doing this with products that have AGI elements or applied AGI elements, probably it's not something that we can avoid thinking about anymore. So it may be time, you know, to kind of get serious, even though it's a very distasteful, complex, and it's gonna. There's no. You're not going to be. It's a thankless job basically to do this, but something that has to be done, I think.
I agree.
I agree with you. Essentially, but there are some small problems that are most interesting and in some sense related with beneficial AI. So, for example, I mentioned before the problem of bias in learning. It is a problem. It is a technical problem, but there are social counterparts. For example, if you use a huge data set, typically the data set of faces are typically white American people and so on and so forth. So minorities are, in some sense, they may have problems. So it is not beneficial AI, but the problem of bias in a training set is a technical problem that has some social content.
So believe it or not, I was able to get a patent at Cisco on debiasing AI, because you can actually visualize the bias quite easily by visualization techniques, and if you could visualize the bias, you could debias. I think that the issues with MLDL are kind of insignificant, really, compared to AGI. The issues of AGI. That's when it's really kind of beneficial AGI, if you will, but or for lack of a better term. But it's when you get into these hybrid systems of machine learning, deep learning, and artificial general intelligence, symbolic AI altogether. That's really difficult. But I think the pattern recognition side, I think that's less of a problem, but it's definitely worth looking at.
Okay, who is next? Peter?
Right. Besides what we agreed, to carry out the improvements on the architecture, I think I will focus on the simplifying an attention mechanism, because currently attention of the control is one of the bottlenecks. It needs to be better understood and simplified. Later, now we have the Patrick system, Nars. So later, in the close future, near future, the metrics has to be developed. And now we can compare it to, of course, use meaningless comparison between the CNARs and JNARs, but at least it will let us know in what way to tune or how to influence it. Additionally, what I would like to do is, actually with Patrick discussed, we need to find some domains to compare different AGI systems, to have them like on a board and to see how they perform. And those metrics, it also leads to my future research for the procedural learnings, for all of the goals planning, goal conflicts. It's a very, very helpful. That's for the next future, like half a year.
Okay, now we have all the panelists out, and we only have 10 minutes left. But the good news is we will be around in the next couple of days. So, and even after that, you'll see we can continue to discuss online, if not in person. And I noticed Hila has raised hand for a while. So I think, and who else in the audience want to say something, or you can post, or you can raise your hand.
Sorry, Pei, that was a mistake. Please ignore my.
Okay. And sorry, we didn't give much time left to the audience. It doesn't mean we don't want to, okay? Because this is already the longest session in this whole conference. But yeah, if anyone wants to say something short, please.
When is the face-to-face? Is it going to be a face-to-face work session of some sort? I know we were planning to do something prior to all the the situation there.
Yeah, I would love to, but no idea what's going to happen next.
Next year?
We will see. Hopefully before the next year. We don't know. You see, this AGI 20, they still hope to have this physical conference to be held in September, but let's just see whether it can happen.
Right. Another procedural one. The presentations, are we going to have those somewhere. I mean, the actual slides, some of the slides decks were very interesting. Is there a plan to collect those and to make them available?
Yeah, why not? I assume this whole workshop has been video recorded. And also for the speakers, I will suggest all of you to email your PPT file to Peter. Then we can probably put them all together in our website or somewhere. How about that?
Mm-hmm.
Yeah, I guess since we have been a very long meeting for the people who have been here from the very morning, we will still we will just stop as a schedule and leave the discussion for the next couple. How about that?
Sounds good. Thanks, everyone. Goodbye.
Thank you. Just a quick reminder. So tomorrow it is on underline.io, and before the conference starts, you also get an email with all the details. Okay. Well, that's then the end of the stream. Thank you all very much.
Thank you.
Thank you.
Bye.
Bye. Thank you.